Welcome to APEC. It's August 31st, 2024, and I am your moderator, Tim Ventura. I want to thank everybody for joining us on today's call, along with everybody watching us on YouTube. We have a really exciting series of presentations today. We're starting out with a big one by Dr. John Brandenburg, who's going to be discussing gravity modification experiments based on the GEM theory. And after that, we're going to be talking to Jose Alexandre Tigre Da Silva, who's going to be describing an extended Michelson Morley experiment. After that, Eric Reiter is going to present a serious challenge to quantum mechanics. Michael McDonnough will be talking about BioGraphene for structural components and hopefully asymmetrical capacitance as well. And Gerald is going to describe his work with EM coils and transverse gravitational waves. So a couple of quick notes before we get into things about what has been going on, I guess, in our community. I've been working pretty closely with our lab teams. I'm really excited about all of the progress that's going on. Things are surging forward, both in the UFO community as well as our experimental community, as well as the theoretical physics community as well. So there is so much, but a couple of things that jumped out at me are, in the last week, I believe Jim Woodward and his team with Curtis Horn are looking at upgrading their vacuum chamber, and they're also looking at making some other modifications there. So if you remember, one of the things that we had talked about was the peak thrust versus average thrust, 2 millimeter versus 1 millimeter piezos. They believe that they can create even better results with that, and this vacuum chamber is kind of a step in that direction. So also, Mark Sokol has obtained a metallurgical microscope, and he is doing ARTS parts UFO wreckage analysis based on that. Again, this is a verified piece of ARTS parts. We do have a complete chain of custody there. So he has been doing high-res photos with that. He has also fully completed SEM microscope analysis, and we're looking at doing Raman spectroscopy on that sample as well to try and identify some of the chemical bonds that are there. Also, Jared Yates is continuing his work on the Friedwart-Winterberg archive. He is looking at doing a lengthy presentation on that coming up in the next month or so. Again, Friedwart-Winterberg was a contemporary and close friend, as well as a colleague, of Dr. Edward Teller, Werner von Braun. I mean, many of the heavyweights that really established the current scientific paradigm that we live in. So these are just a few of the many, many things that are going on. I don't want to leave any out, but there's just too much to cover quickly. So before we really get into things today, we are broadcasting on StreamYard. We are through the Alt Propulsion YouTube channel. You may also be watching us on Jeremy Riz Alien Scientist channel or Bernie's channel. So we are multicasting across a few of them, but our claim to fame here is the Alt Propulsion YouTube channel. If you haven't subscribed to that yet, please do so now. You can ask questions using the live chat feature on the right-hand side of the page during the live webcast. And we will try to ask them to our presenters depending on time constraints. Also, to be honest, we have a lot of those comments and questions scrolling up the screen. Sometimes we do miss them. You can also always view conference replays, details, and speaker info on our website at altpropulsion.com. Just as a very quick aside, what I've been doing is loading these YouTube basically presentation archives into the page themselves. So if you go to the website, you can see it there. You can also see it on the Alt Propulsion channel. One of the other changes that we have made is, instead of breaking these up into a series of videos, we are basically putting timestamps into the video. So if you go to the time bar on the video, it should show you where each presentation is, and we're listing that on the pages as well. So I know that is a lot, but that starts us out again for August 31st, 2024. I want to launch right into, again, so exciting, Dr. John Brandenburg, gravity modification based on GEM theory. He's going to be presenting the results of a recent gravity modification experiment based on GEM unification theory, which combines gravity, magnetism, electricity, and other forces into a single controllable force to power aircraft, spacecraft, and other vehicles. So without any further ado, let me bring Mr. Brandenburg in, and I will put up his presentation as well.
Always a pleasure and honor to be on your at your APEC conference, especially presenting.
Well, John,
thank
you
very
so much. I should tell people, just again to archive this. You called me earlier in the week, and you were figuratively jumping up and down. You were like, "This is so exciting, so exciting." So here we are.
After years of being told to be quiet, I've suddenly been told, "Show your stuff."
Okay, well, so I'm managing the slide deck, but just give me a back or forward, and I will do that. And I'm going to take myself out and hand things over to you.
Without further ado, welcome to the age of laboratory gravity modification. I'm going to present experiments that you guys can perform in your garages or laboratories yourself. You can see for yourself. And like I said, 2 weeks ago, I was waved ahead to start presenting all of this stuff and publishing it. So without further ado, laboratory demonstration of gravity modification by EM fields through gravity unification theory. And Ken Doyle was my chief technician. A lot of these slides are taken from a DARPA, a presentation to DARPA, where they told me, "We don't want you doing any experiments, only do theory." Yes, sir. Please sign my check. All right, forward. Okay, I'll talk about just myself very quickly, just so you know who I am and my kind of license to do this sort of work. Okay, we'll talk about evidence of gravity modification and context in terms of the GEM theory or unification theories, the requirement to search for a unified field theory of E&M and gravity, Einstein's work. I'll talk about this stuff very briefly. We're going to get to the experiments as quickly as possible. Summary of the GEM, and then we're going to talk about the basic equation coming out of the GEM, which is called the vacuum Bernoulli equation for gravity modification. Just like the aerodynamic Bernoulli equation gives us flight, this will give us flight even in a vacuum. So then I'm going to talk about demonstration experiments at length. I'll spend most of my time doing that. And then I'll discuss a new report confirming Jack Sarfati's metamaterial theory in connection with this gravity modification. Then I'll summarize it for you. Forward. Okay, since 1981, when I got my PhD at Lawrence Livermore Lab, and by the way, I had the great pleasure and honor of meeting Frederick Winterberg several occasions, and he came to the lab, and I remember him arguing with my thesis advisor about stuff. It was great. Anyway, so I've worked on, I was trained to do fusion, but I'm doing plasmas, and became an astrophysics. Plasma physics and astrophysics are just Siamese twins, and then unification theory, and then of course on Mars. Next. Okay, yeah, just anyway. So okay, I've had a long career in aerospace. You know, as a aerospace contractor to the Defense Department and Department of Energy, and even to NASA. So on we go. Forward. Okay, now gravity modification for unified field theory. Okay, we know we have four forces operating in that we know about in the universe, the cosmos, that explain most 99% of what we see in the cosmos. You can't ever explain everything. But there's the strong force that leads to nuclear power, nuclear weapons, nuclear reactors, fusion reactors. That's what lights the stars. Then we have the weak force that also works together, and those are guys that are short range. They're realm of action is about the size of a subatomic particle. So they're short range. Then we have the two long range forces of in the universe, the electromagnetic force and the gravity force. They're long range. They go all the way across the universe. Now we also have a universe that is dominated. It started out as a vacuum, and then 1 second later, it was an expanding fireball composed of hydrogen, which is two particles, the two stable charge the only two stable particles in the universe, subatomic particles, electrons and protons, and they're both charged. So we went from having one force and a vacuum, a Planckian vacuum full of Planck masses and antimasses. Then 1 second later, as near as they can reconstruct, we had a expanding fireball of hydrogen with gravity and E&M forces in it. So Einstein attacked this problem. He thought he was certain you could isolate the two long-range forces. And he also said somehow hydrogen is the key to understanding matter, which is, of course, the source of charge and mass that drive the gravity and E&M forces. Next. Okay, here's gravity, the gravity constant, big G, two rocks out in space. They attract each other with a force that's 1 over r squared. And the product times the product of the masses times big G. Big G is arguably the most important number in the cosmos. Next. Okay, now it had been reported by Kozyrev, a Russian scientist in 1968, that when he spun gyroscopes with E&M Tesla three-phase power, if he spun them so they were spin vector down, they lost weight. If you spun them at 90 degrees to the gravity vector, they lost half their weight. They lost half what they did when they were spinning down. If you got them spinning straight up, they didn't lose weight at all. So it was a half angle spinner relationship. Very strange. We got some money together because, and Hayasaka and Takeuchi in 1989 did the same experiment, and they got the same results. We got some support to repeat the experiment in as much detail as we could. We did everything exactly like Hayasaki and Takeuchi reported, and we got the same result. So this thing is real. Now, there was a guy, some smart aleck from University of Colorado, took a gyroscope and spun it with compressed air and got no results. And therefore, he said, this is nonsense. No, that's called, he was a professional debunker. Same place that produced the Condon report. Next. So we know we can do this in the lab. Okay, unification theory. Einstein's great quest. Hey, Al Einstein, he was a really smart guy. So if he says something can be done, who are we to argue with him? But he didn't like quantum mechanics, but it turns out quantum mechanics is the key. Next. Planck scale is determined by quantum mechanics. You have a length, and it all depends on big G and Planck's constant and the speed of light. So there's a Planck length, Planck's, defining length scale, and then you've got a Planck mass, and then you've got even the Planck charge. Next. The basic gem theory is that gravity fields are equivalent to arrays of what's called E cross B drift. That's from plasma physics. You can look it up on the web. And it affects all particles, regardless of charge or mass. Even though it's a pair of E and M fields, it looks like gravity. because it affects all charged particles, regardless of charge, regardless of mass, the same. Okay, also, the second postulate is that gravity and E&M exist because electrons and protons exist. That is, electrons and protons separated from the Planck scale became two separate charged particles at the same time that gravity and E&M appeared as separate forces in the Big Bang. So those two things were correlated. Next. Now, I'm a plasma physicist, and I became aware of this effect in plasma physics called the E cross B drift. It's also can be written in terms of the Poynting vector, which is the radiation pressure vector of E&M. And you can, if you have two plates and a magnetic field coming out of the page, and you put an electron or a proton or a charged zinc atom, whatever you put in there, they'll all end up moving at the same rate in the same direction. Now, if you take the plates and tilt them with each other, they'll actually all accelerate at the same rate. You can do that with a simple computer simulation. It's in the limit, though, of the magnetic field is much stronger than the electric field, which corresponds to non-relativistic. So this is a non-relativistic model. Next, you can do the same thing by making a time variation between the plates. Rather than having them change spatially, curved spatially, they are curved in time. So if the two plates have electric fields between them, electric field, by putting a voltage ramp, keeping the magnetic field constant, and then having a voltage ramp, a sawtooth, you can get everything to accelerate at the same rate in the same direction, regardless of charge or mass. It looks just like gravity. So next. So that's based on a physical model. You can also understand how you can get gravity from radiation pressure. If you put two bright objects in a dark box, say you're up in the space station, no gravity fields, you got two bright objects in a dark box, they repel each other due to mutual radiation pressure as a 1/r² force. Now, if you take the box, heat it white hot, put in two cold objects, they will attract one another with a 1/r² force because they mutually shadow. So this is the basis for the what's called the Sakharov put-off model of E&M gravity unification. You all know Hal Puthoff. He's not just an expert on remote viewing. He is a superb scientist. And he has a theory that's very similar to mine in this respect. And the results of my theory can also be derived from his theory. Next. One of the things that happens is we know from quantum mechanics, we're surrounded by a sea of electromagnetic energy called the zero-point fluctuation, the ZPF. In my theory, that vanishes. It self-censors. So in a sense, the E&M fields that are creating all of this energy around us also create anti-gravity, so the universe doesn't collapse into a black hole. So there you see, merely by the fact that we have the existence we have, that E&M and gravity can neutralize each other. Next. Okay, so then there's a second gem postulate. That's the separate appearance of electrons and protons being correlated with the separate appearance of gravity and E&M. Move forward. I'm not going to go into this in detail, but it's there. You can see it in the literature. Next. Here's the correlation that the mass, the square root of the mass ratio between electron and proton is correlated with the logarithm of a fifth dimension that expands out from the it's a Kaluza-Klein fifth dimension that expands out from the Planck scale. The key number to the universe, by the way, is 42.85 because that's the square root of the mass ratio. Next, you can invert these formulas and get formulas for the proton mass out of the vacuum, leading to hydrogen, and then also the strength of the gravity constant. Next, I'm just very quickly summarizing this. The resulting formula for the gravitation constant is the most accurate formula known from a physical derivation. I mean, anybody can, if you put enough diddle factors into an equation, you can get the gravitation constant. But this one does not use any diddle factors. It's a physical derivation. Also, you get the mass of the proton. You can get the mass of the electron too, but the mass of the proton is the simplest, and that comes into within 4 parts per 1,000. And the G you can get to parts per 10,000. Next. So this theory is solid. It also says that just like you can bend starlight, which is electromagnetic radiation, with gravity, in this theory, you can also bend gravity with starlight. Next. You can derive from this theory using this E cross B drift model, time with a time variation on the E cross B drift speed to make gravity, and then Newtonian gravity theory, and because we're doing it in a non-relativistic limit, then also the Poynting's theorem. And you put that all, mix it together in the pot. Next. You end up with this top equation. You can integrate that in time with the condition that the magnetic field is constant in these little cells in space, and you end up with what we call the vacuum Bernoulli equation. It has a static pressure, which that's the gravity field energy density, or an energy density that can be associated with gravity. And then you have the Poynting field and the electromagnetic, and those two things vary together in order to, so that there's some of this, the difference between them is a constant. Next. Now, what does that mean? It says that if you create an intense field of Poynting vector, like radiation around an antenna, or the field around a coil, just a coil that's charged with AC, it will create a zone of strengthened gravity where the Poynting field is strong, S squared is strong, gravity will be slightly stronger, but that makes it pulls the gravity fields out from the coil, so the coil gets lighter. So that's it. The coil, which drives everything, feels less gravity, but the air around the coil, when you energize this coil with AC, so it has fluctuating Poynting vector, the air around it gets slightly heavier, but the coil gets lighter. And you can visualize gravity lines of force at a distance, just like around an airplane wing. You have the same static atmospheric pressure, but close to the wing, the pressure varies in order to give you lift. Next. Now, how do you do this? How do you see this in the lab? I'm going to give you a cookbook on how to do it in your own garage or study or laboratory. Get out your chef's hat. Let's start with the cookbook. Okay, buy a toy motor, probably rated up to somewhere between 9 volts, 12 volts, so it can handle that kind of voltage. build a little enclosure, hang that, take a 3-lobe, we took a 3-lobe armature, disconnected 2 of the lobes. So there's just 1 lobe active. And then we powered it by thin wires, just thin copper wires, insulated copper wires. And we hung the whole thing beneath a balloon inside a light enclosure to shield it from air currents. And then we powered it with, and this is crucial, you have to power it at 400 hertz or above and at 12 volts or above output voltage from that amplifier. Take a nice electric guitar amplifier and power it at 400 hertz or above. There apparently was threshold effects. So if it comes on, this effect appears as voltage squared. And if you don't supply enough voltage, you won't see anything. You have to get that voltage up there above 12 volts or above output voltage. And you have to have frequencies at or above 400 hertz. Next. Okay, to create an enclosure, we just got some PVC pipe and put clear plastic, painting cloth wrapped around it and secured by tape. So we would have a nice phone booth kind of sized thing where there would be still air. Could be isolated from any air currents. Next. Okay, go down to the store, get helium balloons, probably 2, make them Mylar so they'll keep their helium for a couple days. You want that just in case there's any trouble. Like any experiment, there's a certain amount of futzing around before you get the thing to work. Okay, as I said, buy a toy motor, rated at like somewhere between 9 and 12 volts, and take the 3-lobe, basically one of those 3-lobe little armatures, and disable 2 of the windings, just so you just have 1 winding, and then connect it to this powerful source of 400 hertz or above at 12 volts. Next. Okay, place the balloon coil assembly in an enclosure in equilibrium away from the walls, and it'll form a nice equilibrium where the coil is connected with the wires, and the wires are being pulled up off the floor. So the balloon will pull the coil up until there's enough wire weight to balance so it's supporting the weight of the coil plus the wires dangling beneath us. So it finds a equilibrium position. Okay, let the air become still. Just let it sit there. Then energize at 400 hertz or above and voltage 12 volts or above. The coil will rise instantly. This power is applied and sink instantly when the power is withdrawn. It'll try and find a new equilibrium, pulling more wire off the floor because the coil gets lighter. And you turn it off, the coil gets heavier and it sinks back down to put more wires on the floor to find a new equilibrium position. And I'm going to show you a video of that. Next. All right. You see on the left, there's the helium balloon and the nylon fiber dangling beneath the coil, dangling beneath the balloon. And you just have a coil there with 2 thin wires. And it's all in an enclosure. Now, we're going to hit it with, we're going to show you the video. Let's see if this works. How about that?
Sorry, I'm muted. John, why don't I do this? I'm going to take down the talk and
just put up the videos I sent you.
Yeah.
Or just link directly to the videos. Yeah, I'm sorry, this is just not.
No, that's okay. That's okay. We'll get you taken care of here. So
We're
let me see.
still in the stone age of actually doing these conferences. A lot of stuff that we'd like to do doesn't work first time we do it. Okay, yeah, put up the video.
Okay, okay. And so share screen, GEM test 2. Okay, and
yep, there we go. Okay, here's the voltage. Watch this thing. Watch the coil. Turn on the power, it rises instantly.
Power on.
Up to 12 volts. Turn it off. It drops. Repeat the video. Here.
Here. Sorry about that.
That's all right. No, now I got it.
Power.
You can see from the lines on the paper behind it, the coil is rising.
Power on.
When the power is on, it drops when the power is off. This is you're looking at changes only of about 10 milligrams. It's a very sensitive way to make it's a cheap but very sensitive way to measure weight changes, is to dangle things beneath balloons like it. Did everybody see that?
Yeah,
Good.
we ran through it twice. So why don't I, John, you want me to go to the next one?
Next one. Okay. Now, that's with just single phase. The most efficient way to do this is with 3-phase. You have a rotating electromagnetic field. It's not just going on and off or oscillating back and forth. It's rotating. This forms what's I call a Tesla pointing vortex. If you do this in a motor case, this is called an induction motor. This is invented by Tesla. Now they're making these very nice, very powerful motors for model aircraft and race cars, and you can get these things off the net. They're very cheap. I'll show you the ones we've used. And what you do is you take it apart, take off the rotor. You don't want the rotor. The only thing you want spinning is the fields. You want a pointing vortex, a Tesla pointing vortex. Next. Okay. Now, if you put this on a sensitive chemical scale, here's what you're going to see. Go launch.
Okay, let me take that down. And this is GEM test 1. Hopefully this is the right
test
one.
That's it. Okay, now see, now I want you guys to notice there's a negative sign here. It's losing weight.
There you go.
Okay, repeat. Okay, here, I'll repeat it. You turn it on. We're using liquid metal contacts. It loses, we turn it on, it instantly loses weight. And then you turn off the power, it regains its weight. I'm going to do this one more time. Yeah, there you go. Okay. It's that simple. We also suspended the coil by a nylon filament above the scale and ran it. It didn't affect the scale at all. There was no electromagnetic interference on the scale. And the earliest results, you saw the balloon thing, that was entirely mechanical. So it can be done right in your lab. Now these are small changes. Okay, now people complained that we were running the coil on top of a electronic scale, which was the most sensitive way to do that. So what we did is we got a load cell. We built a framework using plexiglass. We got a electronic load cell, and we got one of these coils from these brushless motors, took out the rotor. So we just had the coil with the spinning, the pointing vortex in there, Tesla pointing vortex. And we also connected it by liquid metal contacts, so there was no forces between the forces. There are no forces, or only very tiny forces between the electric contacts and the actual coil. We also put the whole thing under a plexiglass dome to isolate it from air currents. And so now the idea is that we were isolating the weight measuring device, the load cell, so it's far away from where the fields are. And you can make that wire, that thing, as long as you want it. We had to make everything fit under this dome, so we made it. But we have a T at on a plastic bar on top of the load cell end, and we dangled two fibers, nylon fibers down to hold up the coil and support it as it dangled its three-phase current connections into the liquid metal. We use Gallistan liquid metal. I don't recommend anybody using mercury unless you want to get mad as a hatter. So here's the results. Next. Oh, I'm sorry. Here is the motor we used. It's a Gould RC brushless motor with ESC waterproof brushless motor combo, 34 kV brushless motor for 1/10 RC truck motor airplane. And I'm sorry, I don't know what that VI anyway. So you just go on Amazon.com. You can order it for like $40 and it comes with its own power supply. It runs on 12 volts. Now, there's only one problem. This thing is optimized to run model aircraft or model trucks, cars, so that when you raise the power, it has a power buffering system. So the power does not come up to maximum except after a time lag, and that's to prevent breaking gears with high torques or spinning tires, things like that. They didn't want that, so there's a certain amount of power buffering, so you don't get instant results. I'll show you the results in a minute, but anyway, you can get this right off that. Okay, here's the load cell we used in the experiment. Load cell sensor part RIPG 300 gram. It was a 300 gram capacity load cell, aluminum load cell. And okay, here's the readout, the data readout for it. Next. You can buy this with it. I think this thing was about $150 altogether. This stuff is inexpensive and widely available now. So Lodestar, I would recommend just don't try to be imaginative unless you've got stuff sitting around in your laboratory that does similar things. I would try to duplicate what I'm showing you exactly, because you never know. There's always hidden variables in these things. Next. So that's the basic hardware. Now, we would wait for this thing to be nice and quiet. We kept everybody out of the room. So there was not only do we have it under dome, but we kept everybody out of the room for 2 hours before we actually started it. Then we fired it up and it started losing weight. And then we would turn off the power and it would regain it. You can see that sawtooth. So it rides up back to its old weight. And we did that twice in this experiment. And we ended up losing 150 milligrams, a tenth of a gram type weight losses. And you can do this for like about a $200 experiment. And it's nice and clean because the load cell is well separated from the coil. So no one can claim that the load cell is talking. There's electronic crosstalk between the load cell and the coil. And all of this stuff is very standard. So I'm telling you guys how to do this yourselves. And please don't let anybody complain, oh, Brandenburg doesn't know what the hell he's talking about. Unless they have repeated this experiment. And the balloon experiment is even cheaper. All you need is a guitar amplifier, electric guitar amplifier, to give you that 12-volt output at 400 hertz. So next, we also did a no result experiment where we supported the coil. So there was just a little bit of weight on, there was still only a tiny amount of weight on the load cell. And we turned it on and off. And this is just the standard noise we saw. So we saw no effect without power. So friends, we now are living in the age of demonstrable gravity modification in the lab. These experiments are simple, they're straightforward, and they don't cost very much. So I urge you to reproduce these results. Get your own bragging rights. I was waved ahead on this. These results are like 2 years old. Suddenly, the people I talked to, like at DARPA, they said, we want you to publish it. Something has happened. The government wants it out now that electromagnetic gravity modification is now possible. After years of ridiculing anybody who reported anything like this, and even hooking up false debunking experiments like running stuff with compressed air rather than E&M, like in the case of the gyroscopes. Now, suddenly, it's all out there and you can all do it. Now, you can do this for like about $200. Just imagine what Uncle Sammy can do if he throws $100 billion at this. So I am quite confident now that the US government has mastered anti-gravity technology and we have our own flying saucers flying around. So we have achieved a fundamental level of parity, technological parity with some of the people visiting here. Now, we haven't got warp drive yet, but hey, we don't need warp drive right now. We, by the way, my theory, the GEM theory, says that if you want to modify gravity, that's bending space-time. If you want to get warp drive, you can twist space-time into a pretzel. That's warp drive. It requires more power, but the power level should not be prohibitive. We should be able to do this, just like Captain Kirk in the Enterprise. So, friends, next. The picture you're seeing is the Sikorsky Cipher. It was flying around in the 80s. It's obviously a flying saucer, or rather a flying donut or torus. And it was based on the aerodynamic Bernoulli equation by a very skillful use of that and use of modern materials. Now, we now have a vacuum Bernoulli equation, and it can give us flight even in vacuum on the surface of the moon. So it has the same, if we look at the Bernoulli equation, it's got a static pressure and a dynamic pressure, rho v squared. It's got P plus rho v squared. That's constant. There's a plus sign between them. In the case of the vacuum Bernoulli equation, there's a negative sign between them. But that just means you have to rearrange things slightly. There's nothing that it's not an impediment to developing flight technology at all. So it can be done theoretically, and now you could do it in your own garage, your own laboratory. So please don't let me hear a chorus of complaints about Brandenburg. Oh, he misspelled words in his presentation. Oh, Brandenburg's just a plasma physicist. What does he know about gravity and electromagnetism? You know, no. Repeat the experiments as I have described them in detail, and you will see these same effects. And realize that we now live in an age of gravity modification technology. Because if you can do this stuff very simply and cheaply, just imagine what the US government has done already. Apparently, the government has had this technology now for decades. So we have a fundamental level of technological parity with the ETs, good and bad. Now, another thing that has happened simultaneously with this was published in October. We made the first presentation of this, by the way, back in 1998. And we were basically told not to talk about it anymore. So we didn't. Yes, sir. Please give us more money. They didn't give us more money, but they told us if you want any more money in the future, don't talk about this. Now, people have been putting glasses of water, blocks of ice, and quartz crystals on top of sensitive scales, like the one I used for the GEM experiment. So now we are dealing with highly active materials electromagnetically. Quartz, water, both have very high dielectric constants. They simply irradiated it with a 5-watt laser. Now that's a powerful laser. That'll blind you. So be careful if you do a repeat of this experiment. But look at the weight losses they got. Once again, we're using pointing vector, that's the laser, to modify local gravity. However, this is extremely important. My theory, the GEM theory, and the experiments I did were basically vacuum. Everything was derived considering there was a vacuum. It was the vacuum Bernoulli equation. Jack has added material to his theory. He calls it metamaterial. Metamaterial basically just means it affects the speed of light, local speed of light. So in honor of him, I call this the J factor for Jack. J for Jack. S is already taken. That's the pointing vector. So J for Jack. It turns out it appears as a term when I have just quickly tried to redo the Bernoulli equation type derivation, but we get a negative sign due to the Sarfati factor, big J. So once again, we're seeing, though, pointing vector affecting local gravity. But in this case, it's been amplified considerably by Jack's metamaterial factor. So, hats off to Jack. He's shown the way, basically, to make this a much more powerful effect. But I'm going to leave it at that. Next, Okay, summary. Gravity modification directly by E&M fields can be predicted from the gem theory. 3 experiments can be performed easily to demonstrate small-scale gravity modification. Now, these are in a kind of vacuum limit or just air, you know. Gravity modification directly by E&M fields is now a demonstrated reality. We have it, guys. We have it. The human race has now control of space-time structure. And you can see it in a small way in your own laboratory or garage using easily obtained equipment. Now, recent reports indicate Jack Sarfati's metamaterial theory can very greatly amplify gravity modification. This is very important. We got into the entryway of the house of gravity control. Jack has now ushered us through the main door into the main part of the main living room of the house. Okay, now, people have told me, Brandenburg, you don't know Jack. I say, yes, I do know Jack. That's why I call him the Wolfman. But Jack is a smart guy. Everyone should listen to him. He has made a major discovery involving amplification of gravity modification through the right choice of materials, not vacuum. So, next, that's the end of the talk.
John, you are a rock star. Thank you. Thank you, man. Perfect.
Hey, I'm
timing,
practicing my air
delivery.
guitar here. I'm just doing my job. I'm just
yeah.
doing my job.
No, that was amazing. That was amazing. Let me bring everybody in here. We have got to give you an enormous hand. I'm going to bring everybody in that we've got. Okay, that's the whole gang.
Okay, guys.
Everyone,
I'm just doing my job.
Giant applause for John. So we've got about 5 minutes left.
I like it. I like it, Jeremy.
So what I'm going to do, I'm going to take myself back out, but if you guys want to discuss, if you have questions, I will be right back. And we've got about 5 minutes left here, guys.
All right. I wish I knew what you were doing. Is that motor spinning around with its inner and outer part there? And
no, it's just the center part, the coil with the copper windings. Yeah. That's stationary.
It's
the rotor part on the outside that you remove. You take that out.
Well, I don't understand how it could spin without the outside removed.
I'm sorry. It's Eric. It's the field that spins now.
Oh, it's the rotor inside.
It's only the field that spins. It's a vortex of pointing vectors.
Okay. Okay,
that's
coil
the secret.
there.
You don't throw away the rotor. It's got some nice magnets on it, But anyway, that part is discarded. All you care about is the coil, and the coil stays stationary. It's only the fields that rotate.
Well, I don't see why the field would rotate if there's an oscillating field going into it. It's an oscillating magnetic field. I don't understand it.
It's Tesla three-phase rotating fields. It was invented by Nikola Tesla. This is the secret for an induction motor.
I just don't get it. I don't get it. The rotor is not rotating.
Everybody. If you run in big industrial motors, they don't use two-phase. That's just wall current. They use three-phase, and it makes a rotating electromagnetic vector. You put a piece of metal in there, it rotates with the electromagnetic field.
Yeah, I think Brett,
Tesla.
John,
look up Tesla three-phase. Yes.
Yeah, so that's the circuit,
I just don't get it, and I'll let you go.
Yeah.
I don't know if my voice is coming through, but yeah. Hey, Eric, it's been a while since I've seen you, but you may remember me from the Foundations of Mind. But yeah, John. So it sounds like what you're talking about is just it sounds like you're rotating the ether. I mean, that you're creating.
We're rotating the ether here.
Yeah, that's what it sounds like to me. Yeah.
We're creating a
Which is
vortex in the
exactly-
ether.
Yep, that's exactly how Tesla saw it. So that's really pretty cool.
Oh, well, Tesla was talking just before he died about a unified field theory where he could change gravity, but he died before he could publish anything on it.
John, it's Curtis here.
Yes.
So, I've been working with Jim Woodward, and one of the variations of his experiment is
Jim would give him my very best regards.
Hopefully he's on. I sent him the link, but today he was actually going to the lab, so he might be actually working. But
of course he's working. You heard I was doing stuff. He thought, Brand, I'm not going to let Brandenburg do this. I'm going to be in my lab working.
So I'm just curious. Have you heard of the MLT drive, which is a Mach-Lorentz thruster? One of the elements in that is
yes, I know there are a variety of things that are, I basically developed this theory, and what kind of fell out immediately was the Tesla rotating the ether vortex thing.
Yep.
So I went with that. Well, actually, we saw the laboratory. I had the theory, and then we saw the laboratory experiments spinning the gyroscope with Tesla three-phase power. So we just pursued that. So we had a laboratory full of three-phase generators, and we were using that for everything. So there are other ways to exploit this that I haven't. Look how many different ways you can use the aerodynamic Bernoulli equation. There's helicopters, there's autogyros, there's plane, low speed, hang gliders, there's airplanes, there's jet fighters. That's how many ways you can use the aerodynamic lift principle of the Bernoulli equation. Just imagine if you're able to change space-time with electromagnetism. In fact, don't imagine it. I've seen it, and others have too.
Yeah.
Once you do this, you'll realize all sorts of technology is now available to us.
I actually used Bernoulli in some of my early presentations. I mean, everything you're saying fits perfectly with the way I see the
yes.
ether model.
I'm not surprised at all. Not surprised. I tried to come up with a cool name for it, and I thought, well, I got to connect it with flight immediately, and it looked like a Bernoulli equation. So I said, let's call it a vacuum Bernoulli equation.
Yeah.
So John, one question for you on the motor experiment where you did it like clockwise and counterclockwise or whatever, where you got the 150 milligram loss. There was a slight variation.
Yeah.
There was a slight variation between forwards versus reverse, and I was wondering what accounts for that slight offset there.
That the slight. Unfortunately, the power supply was just not an instant on, instant off thing. It had a power buffering system to avoid people from breaking gears in their little models and stuff and spinning tires. So what they did was, so what you saw was a longer pulse. I mean, my chief technician's very talented guy, Kenny Doyle. He was running this thing, and he just. Here's another bit of phenomenology. If you run the thing too long, the Gallistan liquid metal, starts getting hot and it expands. And believe it or not, it creates a tiny difference in buoyancy force. It's got copper electrodes in this thing. And it starts pushing it starts pulling the electrodes down deeper into it. So it doesn't return to its former weight when you turn it off. So we just learned, had to do short pulses, no more than 8 seconds. And the other thing we found was, so we had power buffering issues. So it wasn't instant like it was on the case of the balloon experiment and the electronic scale. And then we had also buoyancy effects on the liquid metal electrodes, stuff we never thought we'd have to worry about, in a sensitive experiment. But so what we always wanted was a very clean experiment where you turn it on, it loses weight, you turn it off, and it goes back to its same weight. And we wanted that to be clear and unambiguous. And that means using short pulses of no more than like 8 seconds, using at least
John,
this hardware.
I think one of the things that you're doing is really very similar to, Jim has that basically the piezo stack.
Oh yeah, no, Jim's got the real effect too.
So it's really like he's adding like
I had the pleasure of working with Jim.
Right, he's adding the mechanical.
I had the pleasure of working with
also
Jim.
What's that?
Oh, I actually worked with Jim for about 9 months. It was great experience.
Oh yeah. So basically, he's kind of doing a similar thing with the deep
Yes, he is.
in terms of electrical, and then in addition,
Yes.
he's having the stack mechanically vibrate, and then the differential masses. So what that does is when things are like weighing less, they're pushing and pulling at different times, and that's what ends up giving him that thrust.
Yes.
And then when we do the null test, which is 2 equal masses, the thrust goes away. So, but fundamentally, it's tied to the effect that you're describing. It seems,
guys, we're at the top of the. Oh, we're at the top of the hour. I don't want to push us. This is my fault. I did too long of an intro, but I want to try and get to. I want to try and get to Tigre next. So, but everybody, again, John is. I got my rock star. I have a prop here. John is a total rock star. So let us give him another giant hand. John, thank you so much.
Hey, I'm just doing my job, you guys. I'm just doing.
You got to come back and do updates. Come back and do updates.
I want to see updates from you guys. I want somebody to try this shit. Okay, pardon my French.
Well, you have to stick around till the end then when we're in the lab.
Make me a liar.
Okay, well, guys, I'm going to take everybody out. John, thank you again so much.
Thank you so much. It's been a great pleasure and honor addressing you all on this. Put on your chef's hats.
Okay, well, everybody, thank you so much. So I want to introduce for you, let me see, Jose Alexandre Tigre Da Silva, and you're just going by Tigre, right? So, okay. I will try and work with that. So you sent me over a ton of files, and I have the original extended, Martin Gruznik's original extended Michelson Morley. Do you want me to play that to start out, or?
Sure. Yeah. That would be nice.
Okay. Yeah. Let me do that then. I will. And you can share screen as well, and I'm sure that you probably have a ton of stuff that you'll share, but.
Hello, my name is Martin Grusenig. I'm from Germany, and I would like to introduce 2 experiments to you, which I have conducted with a modified Michelson interferometer on August 14, 2009. I'm using a simply constructed interferometer designed after Albert Abraham Michelson for the following 2 experiments. As a light source for the interferometer, I'm using a small battery-operated laser in green with 5 milliwatt power and a 532 nanometers wavelength. Positioned in the middle of this interferometer is a laser beam splitter, a small glass plate fixed by 2 aluminum segments. In addition, I have installed 2 mirrors, both equipped with vernier adjustments, as well as a plane lens, which will allow us to view the interference pattern enlarged when transmitted on the opposite position screen, made of plywood. The entire apparatus is mounted on a stable tripod and freely rotatable. A camera is installed over the center of the pivot axle to record the on the plywood screen transmitted interference pattern during the rotation. We are now viewing the plywood screen through the onboard camera. At the beginning of the first experiment, we have to adjust the mirrors by the vernier adjustments to the point that we are able to see a clear and good visible interference pattern on the screen. Like Albert Michelson and Edward Morley, over 100 years ago, we are now moving the entire interferometer into a horizontal rotation. Because of the camera, we are now able to nicely view the interference fringes during this rotation. As we can see, there are no shifts in the interference pattern when a complete rotation of the apparatus by 360 degrees occurs. We now conclude the first experiment with the same results as discovered about 100 years ago and take some time to make a few changes to the interferometer for the upcoming second experiment. Just as in the previous experiment, we are now starting with the vernier adjustments of the interferometer until we are able to see a clear and good visible interference pattern. The only difference between this experiment and the previous one lies in the positioning of the rotating plane. This time, the rotating plane is positioned vertical to the Earth's surface. We are now moving the entire interferometer in a slight vertical rotational movement and are watching the projected interference pattern on the screen. You are now able to clearly see a movement of the interference fringe pattern. If we look closer, we are also able to see that when a complete rotation of the interferometer by 360 degrees occurs, a complete standstill of the pattern movement happens at 2 points. After each interruption of the interference fringe pattern movement occurred, it will proceed and move in the opposite direction. I would like to explain this process on hand a small simulation. We are now able to see the construction of the interferometer at the point where the interruption of the moving fringes occur. The second point, where a stillstand of the fringe movement happens, is positioned at the opposite side of the 180 degrees mark. If we look closer at the construction of the interferometer at those two positions, we will be able to notice the beam splitter is positioned horizontally to the Earth's surface. The two mirrors, typical for Michelson interferometer, are positioned in an approximate angle of 45 degrees to the vertical axle. Between those 2 points, we are now able to see a shift in the interference fringes by 11 to 11.5 peaks. This means that a bright beam of constructive interference is moved during a 180 degrees rotation of the interferometer by 11 to 11.5 complete places to the right or the left, depending on the direction of movement. I also would like to mention that a slight variation in the strength of the fringe pattern movement occurs during different times of day. According to my knowledge, we are looking at a completely new discovery and never before explored phenomenon. I hereby would like to say goodbye and thank you for your time and attention. Sincerely, Martin Grusenig.
It still gives me it's still thrilling to watch that video, 15 years after it was published.
Sir, yeah, and I know you have a wonderful presentation. Let me apologize for taking 10 minutes, and if you run over a little bit, that's okay. Let me take myself out. I will hand things over to you completely. I know that you have stuff that you want to present, and
I would actually a back and forth conversation because I don't have that much to talk because the Martin did already the work. But yeah, sure, we can.
Okay. Okay.
Thanks.
Do you want me to stay on then, or do you want to just do a run through?
No, I can do it, and then you jump in later
Okay.
if you want.
Okay.
Thanks. So, hi everyone. I consider myself a friend of Martin because back in 2009, I was actually at the end of a long search. I've ended up researching Nikola Tesla, and then when I came to the conclusion that the Michelson Morley experiment was basically the determining factor in everything we know nowadays, from quantum mechanics to general relativity, it was the basis for everything. They've assumed this is what got me. When I've read, we assume the ether moves parallel to the Earth's surface, something snapped, because I've always read previously that the ether would be involved with gravity, inertia, the entire electromagnetic spectrum. So basically, the ether was the cause of all phenomena, and this is known throughout the entire history, probably for over 2,500 years now. Even the philosophers spoke about this. So the ether is basically the cause. And when I hear, my main problem right now is with language, because there's this oxymoron going on that we mistake cause and effect. So when people talk about gravity, what are you talking about exactly? Are you talking about the phenomena? I was just Googling the definition of gravity is this force that pulls things down. And I'm like, yeah, you're describing what it's doing, but what is the cause of gravity? And if we keep repeating, I mean, all I'm proposing is just repeat Martin's experiment, because we can actually rule out. I've seen some of the comments, people saying, "Oh, yeah, what if the apparatus is bending in its own weight?" We can actually test that. We have interferometry. We have instruments advanced enough to detect any sort of force being applied to the device, so we can rule out. We can actually understand that what's happening is a replicable phenomenon, because this is science. Science is actually the replication of an experiment, and then we can come up with a theory later. The theory comes afterwards, but I am absolutely convinced the ether exists. It is the cause of all phenomena. The ether is basically the scaffolding of the entire physical universe, and everything that we watch and see and experience is a result of this ether. And one of the main topics of all conversations is actually the propulsion system for UFOs. And my guess is the universe is their resource, because one of the words I have a problem with is energy and gravity, because what are you talking about when you talk about energy? But I do believe in resource, and the resource is available in the entire cosmos. They can pull the local resource from wherever they are. And when we come to inertia and gravity, these are all side effects of the ether. It's obvious, this was all, this was made by us. And there's another subject that I would like to touch upon, because everything is sort of interconnected. There's a book that I highly recommend that I need to pitch, which is called Alien Interview, published by Lawrence Spencer. And according to him, he received the transcripts from the nurse that interviewed the surviving pilot of the Roswell crash. 60 years later, he received the transcripts. So check it out. Check on YouTube. I can actually leave a link for an audio version, which explains literally the entire history of the cosmos, not only humanity and why we're here, why we're not visited. So Nikola Tesla, his role. So, this is all our creation. And the problem is science and religion, because science worships matter and religion worships a creator. And meanwhile, I'm an atheist, okay? Let me be very specific, very clear. I'm an atheist. I'm the worst atheist you can ever imagine, respectfully to those who believe. But if we are immortal spiritual beings, then this is all our creation. And we're just in a never-ending cycle of reincarnation, amnesia, and repeats. But the story of our planet is a little darker than we would like to believe. And Earth is actually a prison planet. And we're just, everything makes sense when you think about the pyramids, who built the pyramids, the technology. And so it's all in this book, Alien Interview. Please check it out. And I will urge you to bring Mr. Spencer, Lawrence Spencer, to be interviewed, because you know, there's you can actually find online on YouTube some of his talks, and it's amazing. So back to Martin, right? Back to Martin Gruznik. I've actually exchanged emails with him for about 3 years, from 2009 to 2012. I was here in Brazil in 2009, and then I moved to Canada in 2010, and I kept contact with him. So the last communication I have, I've actually saved the emails. You know, I usually throw emails away like most of us do, but I've kept all our communications. I've kept, and he sent me photos. He sent me other experiments he was doing. He told me he was being threatened. By the way, just I forgot, Martin, wherever you are, I owe you. We all owe you a debt of gratitude. You've done your work. Okay, you've laid the foundations for everything that I'm about to research, you know, and it's amazing. I mean, when you look at that experiment, how obvious it is. And I've searched the literature. I contacted dozens, hundreds of universities showing them this experiment, and nobody's interested. They all say, no, we know our physics, you know, it's been done before. Had it been known, you know, we would have known, but there is no literature about a vertical Michelson experiment, except I'm actually, because I'm finishing college right now, I'm doing a university degree, a bachelor's degree to become an English teacher. It is required at the end of my course that we do a kind of like not a dissertation, but a thesis. And my thesis is on Martin's work, and it needs to be replicated. So this is science. It's replicating a known experiment. And when you talk about the ether, I was actually, during my research, you can research the Sagnac effect. I hope I'm pronouncing correctly. The Sagnac interferometer, which is actually used in navigation for aircraft or satellite navigation. It doesn't require an external source. It is so sensitive that you can actually detect one rotation every during 7 days. So it's a very sensitive equipment. So there's the Sagnac effect that basically goes against the relativity. And during my research, I even found a paper from an Israeli physicist, and he says, I've never heard about the Sagnac effect, which basically contradicts relativity. You know, if you're moving an interferometer and you're having this shifts moving, this fringe movement, something is changing the speed of light. And if we keep repeating this experiment and pointing the interferometer upwards, and something is slowing down the beam of light, we need to know what is slowing down. And it's not enough to say, oh, it's gravity. But what are you talking about? What is gravity? You know, you're describing the effect as the cause. And this is our main problem. It's language. You know, it's almost like newspeak. You know, the Orwellian newspeak, where war means peace. You know, ignorance is knowledge. I mean, what is gravity? Are you talking about the cause of the effect? You know, so my take is gravity is an isotropic flow of the ether towards the center of mass, and this is universal throughout the entire cosmos. And I even remember an episode of Friends where Phoebe is talking to Ross, and she even mentions, I'm not so sure about gravity because sometimes I feel being pushed down. And I remember laughing, and because I've been thinking about that for so many years, and my take in gravity is basically this, that gravity is a side effect of the ether, and so is the entire electromagnetic spectrum. I mean, there's something I want to show you guys in a little while, which is a phenomenon, a very old phenomenon. Let's see if I pronounce correctly. It's a German phenomenon called Heiligenschein effect. This is amazing. You guys are gonna love it. This phenomenon you've probably seen it if you're flying on a plane and you look down towards the shadow of the plane and you see that like a light halo around the shadow of the aircraft, and it's beautiful. And when you look at the definition, they say it's because of the dew, you know, the humidity in the atmosphere that causes this effect, like a lens effect. But there's only one problem. If you look at the photographs from the moon, the astronauts, they see the same halo on the moon. If you look at footage from Ingenuity on Mars, the shadow of the helicopter has the same halo around. So you're going to tell me that this dew is present on the moon and on Mars? And I'm pretty sure if we do an experiment, let's say you place a big sail in orbit, right, in a vacuum. Well, you can even do it here on the surface of the planet, but just because it's vacuum, and you put this huge tent, and then you project an image. I mean, you photograph the shadow of the camera over on this tar, whatever, this big canvas, you're gonna see the same halo. So what is that? What is that halo? I mean, how is that happening? That is, for me at least, is proof of the ether, because when you think about this particle wave duality problem that we have, even with the double slit effect, they don't. There's no model unless the wave model that justifies. How can we see distant light from distant stars, light from distant stars or galaxies? I mean, what if there is a particle of hydrogen or an atom, a particle in mid-flight? What if that photon collides with that particle? We would never be able to see. And so what happens, my opinion, is the ether basically envelops because it's the medium itself. Light is the effect of the ether. There is no such thing as light. There is no such thing as gravity. Everything is a side effect of the ether. We're just describing. I mean, when we talk, we're living in the dark ages, in my opinion. Black holes, dark matter, dark energy. Step into the light. It's there. It's been known throughout our entire history. The luminiferous ether. There's even I remember there's a Dr. Pepper commercial from 1880s talking about the ether was a sea of energy that surrounds us. But the model they used to think it was the Earth was basically like a ball floating inside this ether. But it's completely absurd, because it would throw celestial mechanics away. How would the celestial bodies move inside this sort of medium? So basically, what I think, it's kind of like that painting from Van Gogh, if I pronounce it correctly, Starry Night, when you see all those swirls around. So basically, the ether is kind of like when Sir Alec Guinness is describing the force, which is this energy that binds the galaxies. That's the ether, It's basically this scaffolding of the entire physical universe. And we're just beginning to figure this out right now.
Okay.
Sorry, Tim.
Oh, no worries at all. No, that was a great rant. The reason I popped back in was you have a ton of videos that you sent over also. Now, did you want to share
just photos,
those?
Actually? I did one experiment, yeah. One
okay. Okay. Or do you want me to share those? I can try and share those.
Absolutely, yeah. There's some photos from Martin Krusnik.
Yeah, so let me do this then. Let me see if I can do this correctly.
If you let me just do a little bit of screen share, I also might be able to show something, which is just everything I'm talking is public domain. There's nothing hidden here, guys.
Yeah, no, just click the present button, and and when you're ready, actually, when you've wrapped things up, we'll bring everybody in and we can discuss this too. But just click the present button and do share screen, and it'll give you a bunch of different choices there. So
okay, let me see. Okay, beg your pardon.
And I think with this one, if you're in Google Chrome, it should allow you to do it. I believe that it will share the entire screen.
The entire screen, okay.
Yeah.
So I'm gonna show for now just a few emails from Martin, this is from way back in 2010. This is June 30th, 2010. According to him, his experiment was in, August 14th, 2009. So this was a little bit after. I remember exchanging some emails with him, and then I've deleted some, and then I kept the rest. But he was actually working on a Van der Graaf generator, and he described, he mentions on the email that he doesn't need ground, so he can actually produce like a pump that generates these particles we call electrons. And then we keep going on. He sent me a stationary interferometer that he can actually detect the movements of the moon, the planets. He took like 30,000 frames over a period of 1 month. I was hoping that he did a video on that, but he never published. Basically, our emails were mostly just talk. We talked a lot about the fact that he was being threatened, which I found not surprising. He was being threatened, and he said his computer was hacked Mine was they changed my password. I thought it was so funny. And something really, really interesting happened around 2011, I think, which goes right up to the kind of crazy level, like tinfoil hat. I remember I was living in Burnaby, which is in Vancouver, right next to Vancouver, BC, right next to Boundary, which is a road that divides Vancouver in half. And it was in the middle of the day. I was actually talking to him, and then I hear this helicopter circling around my apartment, and I was like, "Oh my God, this can't be happening." And then I go outside towards the balcony, and I look at my neighbor. He's looking up, and I said to him, "Don't worry, I'll get rid of them." And I just waved to this helicopter, and they took away. And this, it was just surreal. The most incredible helicopter I've ever seen in my life. Black, it looked like a toy helicopter. I don't know, maybe I'm crazy, but that happened. But I'm still here, and I just wish I knew what happened to Martin. The last email he sent was he was complaining that he was sick. This can you see this image here right now? The Heiligenschein effect.
So right now it is still showing his email.
I beg your pardon. I have to change this screen. Sorry.
Oh, no, that's cool. Yeah, again, StreamYard is a little bit different. I love it, but it takes getting used to. So
yeah, but this Heiligenschein effect is basically this halo that appears, and if that happens in the vacuum, what's the explanation? I mean, it can be tested.
If you click the present button, and then let me see. Yeah, oops. Sorry about that. Click the present button and then share screen, and it'll have Chrome tab. It'll let you do a tab.
Okay, let's see which one I can.
Yeah, and what you can do, this is kind of the cheat for it, is you can just paste a new URL in.
Right.
So let me see. I believe that's the Chrome tab you have. Yeah, Heiligenschein. Okay.
Heiligenschein. So this effect, if you guys ever need a smoking gun, my opinion, this is worth a Nobel Prize. I mean, suddenly we discovered that this effect is, it can happen in the vacuum, and then we'll explain how the light from different stars get to us, because the ether is fluid dynamics. There is no mystery, and it's being studied and compared to fluid dynamics. When Tesla was doing his experiments, I've also researched a lot before 2009. I don't know if you ever heard about Borderlands Science Foundations. You can see presentations from Peter Linderman, all of those amazing folks, and they would talk about Tesla patents, and most of Tesla patents talk about the ether and this medium that he could actually feel through a Faraday cage. He could feel the pulsations, and everything would get electrified. And when his Wardenclyffe Tower got demolished, he was actually ready to commercialize this ether. I mean, there was no meter. That's the problem that's why JP Morgan, ordered the whole thing to be demolished, because there was no way to put a meter on. So this is it. We're talking about the ultimate. What's the word I'm looking for here? Sovereignty. We're claiming our sovereignty back. And I know I kind of went on a tangent about this book, Alien Interview, but everything kind of ties together. Why we're not visited. That's probably my biggest wonder. Why? I mean, we are visited to a certain extent, right? We know about. I mean, I was in the Air Force for 4 years, and I held in my hands documents related to UFO activity. They were picked by radar. They were close to airports, so they would scramble jets to check them out. So it is real. It is a real phenomenon. We all know that. But the reason why we're not visited might have to do with this book, Alien Interview, that Earth is a prison planet. And they even tell the story that this civilization called the Domain, they've entered our galaxy about 10,000 years ago. And they tried to set up camp here, and the old civilization, they nicknamed the Old Empire, was already here, using the planet as a prison. So they ended up losing like 3,000 of them. There was a war, And the funny thing is, it's kind of documented throughout our history. And this is probably the reason why we're not visited. I mean, not probably, this is the reason why we're not visited. It's a prison planet. So they dump everything here that is not wanted anywhere else. So now it's our problem. You know, that's why we deal with psychopaths, murderers, geniuses, you know, people like me. I'm probably one of the worst ones because I want to free all the crazies again. I want to send everybody back. So, you know, this is it. It's our right to evolve. Nobody's going to tell me, oh, you don't have the right to evolve. No, I do have the right to evolve. And we're doing right now. You know, we're trying to figure out. And if you leave to the academia, for example, they're not going to do anything about it because it's not in their interest. You know, it's going to screw their funding. I mean, one of my communications with Martin around 2010 was about this. You know, he even mentions that Germany was buying gas from Russia and then selling double the price. You know, so if you talk about, oh, suddenly we have a new way of generating our own power and energy, you're starting a hornet's nest. So, you know, he even advised me, if you're ready to do something, do it so they can stop you. And coincidentally, I'm publishing because of my college work. You know, I have to publish this, so it's going to be on academic papers. So there is it. But it's everything is public domain. There's nothing hidden. You know, this effect is Heiligenschein. You can test over and over again. The Michelson the Gruzinik effect, right? The vertical Michelson interferometer can be repeated as many times as you want. So, you know, you can do this on a desktop. It's not something exotic. Then we're going to figure out the theory after that. Yeah.
Okay.
So here we are.
Yeah, no, that's wonderful. Well, so why don't I do this then? Why don't I bring everybody back in? So I'm going to, let me see. And we have a bunch of folks that are watching, so I'm just going to bring them all. I got the whole gang here. Everybody give Tigre an enormous applause. Enormous applause. Thank you. And I was dropping links in. I was doing research in the chat. So for folks who are watching this, if they didn't get those, I dropped links into the chat, and I will also put those up. I put like a file area up at the bottom of each page, and so I'll put links to those in there as well. So again, thank you so much for running through that. And I would love to get you guys, if you guys want to do kind of an open discussion, I would love to have that about this experiment because Tigre, I read the same criticism that you described. They said that there was microscopic wobble in the mirrors, right? When it tilts.
Yeah.
And
I know.
But
it can be tested. We can rule that out. I mean, there's even nowadays we have direct energy deposition, which is 3D printing. You can 3D print on a what I call a base plate. There's this you can buy from Edmund Optics. This is from Edmund Optics. I actually bought it when I tried to do it in Canada. So you can actually mount on a titanium bed and just mill the parts. You can use direct energy deposition and build everything, mill the parts that you don't need, and attach the instruments there. And you can actually measure if there is any error. So we can rule out if there is error. We have instruments for that. So if anybody says, oh, it's a deformation of the device, we can rule that out. We can use interferometry to rule that out. We can do experiments. We can use satellites. We can put an interferometer in a satellite and time the time that the laser, not the time that it goes back and forth, but you can time when it hits the satellite and returns back. If the laser returns faster, it's further evidence. You know, we can time both ways. So yeah, we have several ways to do science.
Well, and it seems like a really foundational, big experiment, right? And something that just kind of got overlooked, and you know, and now I mean, it seems like this is something that needs more work done. It needs to either be fully validated or fully invalidated, right? Because right now it's kind of hanging out there. And so, you know, the work that Martin started, again, I did see a lot of criticism online, and the majority of that came back to this experimental error idea, but that's something that can be ruled out. So
I have two questions for Tigre, if it's okay.
Yeah, go for it, Jared.
So the first question, in the rotating Michelson Morley thing, we were talking about the Sagnac effect, do you know the east-west, north-south orientation of the rotating device for that test? Because if it was north-south versus east-west.
Sorry, the Sagnac effect is actually a different device. I've actually tried to, I've actually used ChatGPT to show me what's the difference between the Sagnac effect, the Sagnac interferometer, and the Michelson interferometer. But the whole point is, if you rotate the device towards what I believe is anisotropic, what is the anisotropic ether, then you're going to notice a difference, which is what Martin's showing us. So I don't think the orientation, if it's north or west, I know there's regions of the planet that gravity is lower, but I would love to see a test, for example, in the ISS. I'd love to see what's the result in orbit, in microgravity. But as far as I can tell, the experiment shows that there is something slowing down the speed of light. Something, not gravity. Gravity is the effect. We need to find out what is the cause, and it is known throughout our history that the ether is the cause of gravity. So if people, as I said in the beginning, my problem is language. We need to understand our language. We need to understand the difference between cause and effect. We can't say, what is a human being? Oh, a human being is the capacity to dance. No, a human being is a human being. Or blame, what is the wind? It's the atmosphere. It's not an entity. It's not a separate entity. And as far as I can tell right now, when people talk about gravity, I get like my eyes roll. Like, what are you talking about? What is gravity? Are you describing the cause of the effect? You can't say gravity does that. I remember if you go to a science museum, you see like that big sheet, and then there's a ball, and then people say, oh, look, this is curved space-time. And I'm like, oh, so you mean God is holding a sheet in space? I mean, Tesla used to make fun of this. How can you curve something that is empty? I mean, if they claim the space is empty, how are you curving something that is empty? What is being curved? You know what I mean? Nothing makes sense. So it's like we're living in this sort of a dystopian nightmare where people are talking something, but they don't even know what they're talking about. It's just regurgitating like some sort of, I don't know, regurgitating.
Yeah, I would go with that. So my complaint about I know what you're talking about, the basically the rubber sheet model, right? And where you have the rubber sheet and the ball's pushing it down.
Yeah, ball,
and in some ways it's representative, but one of the things that always bothered me about that was it's self-referential, right? You're describing gravity using something that is warped by gravity, and so it's
or acceleration, right?
Yeah,
I said gravity, acceleration, the same thing. Yeah, but how? How can you prove that? If you don't know what's causing inertia, and inertia is tied up. I mean, one of the explanations why, I mean, we all talk about this, the maneuverability of UFOs. How can they break the laws of physics? It's just that we are basically illiterate. We don't even understand. I mean, if the ether is not included in the model, we're missing 99% of the universe right now. We are we're going to be remembered as the Dark Ages, because we didn't even understand the reality of our own universe. Sorry.
If I can ask my second question.
Go ahead.
All right. So to conclude the Sagnac effect, it matters whether or not you have a signal going east versus whether it's going west. That's that. Let's just put the Sagnac effect on pause. We're going to disagree about it.
Right.
The other thing, if you wanted to test another version of this, which has been tested a lot, if you send a laser pulse to the moon, there's reflectors on the moon that we've put there that can reflect it back, and the moon is moving around the Earth, right? Well, in the phase of the moon where it's moving towards the ether versus away from the ether, we can see whether or not there is a lag or an increase in acceleration on that bounce. And it's not just the moon that you can do this with. You can do it with radar pulses off of other moons, other planets in our solar system. Tesla figured that out way back when. So all of these reflection experiments to test the ether are also things that have been tested. So you would hope that we would see.
They haven't, because you have to time the laser hits the sensor. So there's two different times: the one that it goes up and the one that comes down. You can't just measure the bouncing, because you're just adding two different values. It's like it's A plus B, but A is different than B. So the time it goes up is slower, and the time it comes down is faster. And you've mentioned that it's been tested before. The Michelson has been. I've searched the entire internet. There's not a single paper that relates to the vertical interferometer. And the Sagnac effect is different. You don't need an external reference. The Sagnac effect is completely self-contained. It actually goes against general relativity, because if you're moving the interferometer in any direction, it doesn't matter if it's a rotation frame or inertial frame, it's the same movement. There's even this argument. So there is no paper. I think I'm going to be the first one to publish a paper on the vertical experiment. That it has never been done. And I think it's kind of strange, isn't it, guys? I mean, the most obvious thing is hasn't been done. I mean, I remember sending emails to Stanford, to Yale, and they're like, yeah, it's been done before. And I would say, can you please send me the peer review paper? Silence, total silence. So it hasn't been done. Martin is the first one. He even says in the video, I believe this is a brand new phenomenon. Nobody has ever replied. In 15 years, nobody has ever replicated. I mean, I've actually put a Patreon page. I tried to put a Patreon page because I don't know, Edmund Optics sells that for what, $5,000, a interferometer. That's it. Just buy an Edmund Optics interferometer. Keep doing the work. Keep doing the science. Sorry.
Yeah, I've been wanting to ask a question for a while as well.
Sorry, go ahead.
Yeah.
Yeah.
Do you want to go ahead first, John? That's fine.
Oh, I'm sorry, and I had to step out, take care of something. And I apologize if somebody raised this issue before. You know, there is a gradient of pressure in the room because of the gravity field. How much does that affect the index refraction of the air? Just the fact that there's a pressure density gradient.
I'm sorry,
you know, and
John,
I don't know the answer to that.
With all due respect, I don't know. I don't have. I'm not a physicist, you know. But
I think
do know that
it can be calculated. And I'm saying this as your friend. You know, I'm just saying, check that. You know, that's important homework that must be done. How much is the change of density in the air due to? Because I've seen experiments at science fairs where people can easily measure the gradient in pressure.
Well,
you know, which is at sea level is basically a difference in density of the air column.
It can be ruled out. Everything that we're talking about can be ruled out. You know, we have instruments sensitive enough to detect. I mean, we use interferometry itself to measure any variation. Though, I mean, I think the shortest wavelength is the ultraviolet, so we can use that.
Yeah.
One of the problems with interferometry, if you use a green laser, there is an infrared hitchhiking inside that green 530 nanometer wavelength.
Oh no!
So it's kind of dangerous. But you can polarize. One of the things I discovered, for example, Martin's experiment, he used glass, right? Yeah. He uses one exactly like this. Right, I bought one too, but the cube is better because the cube beam splitter, it's only one little. There's a tiny little sliver in between, and you only have one projection. His has two because each surface of the glass projects a different image. So everything can be ruled out. You know, you can build in a vacuum if you want. You can put it in an orbit. You can put it on a moon. But we've never done it. There is no. I mean, of all the experiments taken to the ISS, nobody has ever taken an interferometer up there. Wonder why? Sorry, guys.
Well, yeah. I'm sorry. Next question.
Yeah. So you just happen to know the experimenter that performed these experiments, because I would like to talk to him, because there's a lot of questions about, like, you know, how long the path length is. There's a wide variety of issues that could lead to, and okay, let me make it clear that I'm very strongly for the ether, but I actually have found that this experiment looks like there might be some experimental error. And so that's just been my experience so far, which is why I'd like to talk to him further and get more information about it, because it would be interesting to find if there was something else there. But at the current moment, there's a lot of questions that we kind of need the technical details for. But yeah, you made some great points about Sagnac effect and things like that. And also, by the way, Jared, I would like to ask you why you think about the difference of east-west with the Sagnac effect, because I mean, with a Michelson-Gale experiment, yeah, there's an interesting east-west thing there, but I'm not sure why you believe it's there with the Sagnac effect. So we might want to do that another time, but that is an interesting thing I'd like to hear.
Well, I could jump in really quick. So I got, and I believe it was from Tigre, I got a couple of emails for Gruznik. I did some hunting online. I was unable to find him. Now there was some question about whether it was spelled Groznik with an O or Gruznik with a U. And I found that in an online discussion forum. And I ended up trying emails with both, if I remember correctly. Did not hear back. But, again, he conducted this. He did this experiment and put the video up in 2009. And so in a lot of cases, folks like that kind of move on, I think.
Yeah, I think it needs to be, it's science. We're talking about science, we can replicate this to our heart's content if you want. But this is science, then we can come back later with the theory. So, but the Sagnac effect is a total mystery. I was researching for my paper, and there's this, I think he's a physicist from the Haifa University, and he says it contradicts general relativity, because the Sagnac effect shouldn't happen. It
contradicts
in any direction.
Yeah, the issue is that people will describe special relativity as though it is a classical theory whenever they start to try to say, "Oh no, it fits fine with special relativity," and it really doesn't. There's a wide variety of ways you can re-express it. Like, for instance, one of the things I have in one of my that I'm putting in one of my papers is the round the universe or around the galaxy Sagnac interferometer, which is the idea is that by the time you make an interferometer big enough, that's the Sagnac type, then it's pretty much a straight line, and so you can no longer use any of the idea of the curvature to describe why it would have that effect. But the thing is, it has to do with the edge rotation speed and not the radians per second. So in other words, it's actually getting edge speed, which means you would still see the Sagnac effect in a round the galaxy experiment, even though you're practically traveling in a straight line. In other words, you would see light going a different speed in each direction according to the way in which we understand the Sagnac effect in mainstream, literature, etc. Which, that is the way in which you have to describe why you can't, say that this does not, violate special relativity's typical tenets. But there's a misunderstanding there.
What about this Heiligenschein effect? Nobody has ever researched that. What if, you can actually watch videos from Ingenuity on Mars, and you can see the same halo effect on Mars. You can see the photographs from the astronauts on the moon's surface, and you see the same halo effect. You go to Wikipedia, you go to American Meteorological Society, and they say that this effect is caused by the dew in the atmosphere, but you can get the same effect outside the atmosphere. And it can be tested. So this is for the evidence that there is a medium. Tesla was always referred to as the medium. And everything that we do right now is basically using effects from this medium. My main beef is the inability that we have in our language to separate cause and effect. When we talk about gravity, we talk about the cause of the effect. Because if you describe gravity as a force that pulls down, you describe what it's doing. You're not describing the whole process. So, it makes total sense. How can a craft, a flying saucer, go from one galaxy to the other, as we are kind of suspect? Because they're using the local resource. There's something I wanted to show you guys. I'm sorry, with the share screen I didn't show, but there is a video on YouTube from 2000. let me just have a look here because I have said the name of the video is "Why We Haven't Gone Back to the Moon." This is the video from 7 years ago. It has like 812,000 views. You can search on it. Why we haven't gone back to the moon? And I've written like a rant saying the reason why we're not back there is because the hostile alien presence on the moon. Even this book, Alien Interview, talks about that the far side of the moon was used as a base. So look at what someone wrote here. The Soviets agreed to a technology for resource swap to be able to use ether, but negotiations hit a snag over the landing zone. And frankly, nobody was very happy about all the crap left on the lunar surface. Nixon decided to ignore what was happening and went ahead and built a runway and complex on the backside. The alien ultimatum: either Nixon goes or we do. Sadly, 25 engineers and scientists had to be stranded at the moon base because of the 5-year low orbit embargo imposed. They were able to survive almost for 2 months longer than they calculated just on dogged ingenuity. You can honor these brave Americans at their unofficial memorial, the LBJ Memorial Grove Monolith. I think it's in Potomac River in, where is that, New York? So there's even like an official monument, which it's a big rock that was brought from the moon. So I mean, can you guys believe that? What if this is amazing stuff.
Well, and
that's crazy.
That takes us into conspiracy theory territory, which we try and stay out of to some degree.
Sorry.
No, that's cool. That's it. But going back to, I mean, some of the things that you've really focused on are like this incredible need for like real experiment with extended
science. Science.
Yeah.
Let's do the science.
Yeah, and then if we can nail those things, that may show us more. And one of the things that I've seen is, I know this sounds odd, but even people who don't believe in the aether per se believe in the aether, right? Like someone the other day was talking about a preferred reference frame in the background of space and time, and they were jumping around using all sorts of language, and I was like, okay, come on, you're gonna say it, you're saying it in your head,
So, they won't say it. It's a dirty word. It is a dirty word. You'll get so much trouble for saying. Yeah.
It's
conspiracy theory until it's conspiracy fact.
Well, it's not
in some cases, right?
It is. So it's the curvature of space-time and quantum foam, and
there's a million different words they'll use, but they can't say ether.
It's the ZPF.
Yes, the 0-point field. Yes, yeah. Yeah, and
it's full of particles and antiparticles, and supposed to weigh, 1 cubic centimeter is supposed to outweigh the universe.
You want to research
this is standard quantum theory.
Do you remember Dmitry Mendeleev, the Russian father of the periodic table? There is a document on Cornell University. He actually wrote a very very interesting document about the chemical composition of the ether. They calculated the mass of the ether as being 1 followed by 16 zeros gram. So it's 1 quadrillion.
It's got to be gold.
And it's chemically inert. So, I mean, the father of the periodic table has a document about the ether.
Tigre, I'm sorry. There's chemical analysis. Well, now you're getting into dark matter, right?
No, I'm not. I'm trying to stay away from anything dark.
Love this dark matter stuff.
No.
There, it explains everything, but we can't find any.
No.
Well, and that's the dark matter is the watchword of the day, right? So if you say that dark matter or dark energy is the aether, then basically, I don't know what would happen then.
Or is dark energy the flow between aether and
there's no
and the dark matter, right?
There's nothing dark. We haven't done our homework. We need to rotate the Michelson interferometer vertically. That's it. We need to do the homework. That's it.
You gotta check the air density. Check the air density.
Doing the vacuum. I don't care. Doing the vacuum.
Vacuum.
Yeah, you could do it in a high. You could pressurize the room. You could do it in a high pressure room. That would,
do whatever you want, but we need to do it over and over again until we get different results or no results at all, and then we can rule out.
But by the way, the reason the Michelson Morley experiment was done horizontally is because they're floating the entire thing on liquid
I know.
mercury.
Yeah,
This made Michelson actually have a nervous Mad Hatter breakdown after he was done.
because of the contamination.
Absolutely.
Yeah,
And
I can imagine.
this has
I
always been a big problem working with mercury.
You know,
Yeah,
it would be wonderful. It would be wonderful to see universities do things like this with college students. This is.
I'm going to do it.
Yeah, I mean, these are the perfect kind of experiments for university students to undertake, right? So
Yeah, they do them all the time in universities in a vacuum, but there's certain things that they don't do. Like, for instance, the fundamental way in which they do them will be in a vacuum, and if, like, for instance, Lorentz either is correct and there is a shortening that happens, then as soon as you put it in a vacuum, you're not going to be able to detect a difference. That's one of the problems with the way in which they currently do it. Also, using laser light, like I don't know if you noticed how easy it was for him to get those fringes. Getting fringes that easily only comes from what's basically a lock-in effect is what they call it, or phase locking. It makes it very easy to get very stable fringes because of the way that lasers work, but that ease of getting the fringes actually makes the experiment not work as well. And so there's a variety of problems with there's a variety of problems with the way in which we currently do them at universities, and you will always get very stable fringes, and you will very quickly get very stable fringes, which you shouldn't if the experiment actually is functioning properly. It should be just incredibly difficult to get a stable fringe pattern that would just be knocked out by literally a voice in the room will make it completely be destroyed. You won't see
any movement you can detect. It's so sensitive.
But the thing is, there's a variety of ways in which it'll they make it easier, and it also has basically fundamentally eliminates any ability to detect an ether because of the simplicity of the way in which they perform the experiment. But they do these replications at every university, every physics program. They'll show you a little interferometer experiment and show you that it's null. Well, I mean, they can do it. Well, I guarantee you they could do it a vertical one that'll be.
They can, but they've never done it. There is just Google it. Google right now.
I'm pretty sure that there's a guy. There's an experimenter called let's see, the conspiracyoflight.com. I don't know what his name is, but I'm pretty sure he did that experiment. I'm pretty sure he replicated it, and he is. I'm pretty sure he's actually pro ether, but he did the experiment, and I'm pretty sure he replicated that particular one, and so that's I may be wrong about that, but he's a good independent experimenter that we really ought to probably connect with at some point. But yeah, I mean, I love the idea. Here's the thing. I mean, I am 100% on board with ether, absolutely 100%. But there are very specific things when it comes to the way in which to test it, that there'll be certain issues that you have to overcome.
I know.
Yeah,
we need to do our homework. It's what makes us what we are. We need to test. We need to double test. We need to check with other people, different countries, different experiments, do it on orbit, because it's science, it's not that hard. And science is replication. Science is replication. It's not a one-off thing. So as far as we know, Martin's work is one-off. We need more verification. We need more science. I'm actually, as you guys can see, I've actually purchased from Edmund Optics, and I even sent an email to them. And they say we don't publish information on experiments. And you guys have everything. You have have the experiment. Just do it. Just rotate it. No, we don't do that. Which I find very strange.
Well,
I mean, you want to talk about conspiracy?
On that note, John, why don't you go, and then we're at the top of the hour. So John, go for it, and then we'll wrap it up.
I will mention, that the government for a long time has viewed sort of stuff like this, anything having to do with gravity modification, as basically bordering on classified territory. And they have gone out of their way to make sure that it's a subject of ridicule. And, they have an entire organization dedicated to debunking stuff like this. Like somebody says, oh, I spun this gyroscope with Tesla three-phase power. And then a guy goes out and spins it with compressed air and claims that that's a reproduction of the experiment. That's
John,
that
I
is-
know
that is-
exactly what you're talking about. It's like YouTube literally promotes certain channels that intentionally always misreplicate trying to
I know.
reproduce these claims.
They
and
don't
then it's like,
reproduce
oh,
it.
debunked. But it's like, no, they're not following certain procedures intentionally just to get these bunk results. And it's like it's getting promoted by the system and just promoting bad science.
Yeah.
They're bunko artists, not bunko scientists.
Well, guys.
Yes, exactly. Bunk artists, and it's not real science. Yes.
Guys, on that note, so we're at the top of the hour. So Eric is next. So let's do this. Let's put our hands together one more time. Give Tigre a giant applause. Thank you. Thank you so much for running us through that. You gave us 5 or 10 really big ideas to follow up on. I did drop links to all of these in chat. So anybody who's going through can reference this. They can learn more about the Sagnac effect, the extended Michelson Morley, the alien interview video that you mentioned, and a ton more stuff. So thank you so much.
Thank
sir.
you.
Okay, so let me bring in Eric Reiter. Eric, welcome, sir.
Very nice, thank you. I hope you can see my screen share.
I can. So I
Yeah.
have that up now, and
Yeah.
and you are in control of that, sir, because you uploaded
Right.
it. So what I will do is
Right.
I will take myself out, hand things over to you. And you have, so I guess we could describe this as an independently developed theory, right? And so
That's
you're going to be running
correct.
us through that.
Independent experiment and theory.
Well, thank you so much. Thank you so
Yeah,
much.
well, thank you, Tim. So it's a serious challenge to quantum mechanics. And these lecture slides are rather detailed, but I implore people wanting to dig in and see what I'm doing better to get the PDF of it. And everything about what I'm doing is available on my Threshold Model website. So my challenge to quantum mechanics is by history, theory, and experiment. But this lecture emphasizes the experiment, which looks something like what's here on the screen. So as far as the history, it's important to know that someone will say, well, what about such and such effect and whatever? And so I've handled quite a bit of it, but it's in another lecture that I have prepared. But this one, as I say, is emphasizing the experiment. So this passage is the best I've been able to find about the wave particle paradox and the photon model. And by Bohr in this book, which is about the Einstein-Bohr debates, I'm going to read this sentence. If a semi-reflecting mirror is placed in the way of a photon, leaving two possibilities for its direction of propagation, the photon may be either recorded on one and only one of two photographic plates situated at great distances in the two directions in question, or else we may, so this is part two, there's two parts, by replacing the plates by mirrors, observe effects exhibiting an interference between the two reflected wave trains. So it's a two-part model, and Bohr explains straight away that it's no way to visualize this idea. And so I'm saying the best way to handle it is to understand that this is a model and that the photon is not a thing. It's a paradoxical model from the very beginning. But it does seem to be consistent with the experiments that say things work that way. But I'm going to show that it really doesn't work that way. So the realization of this passage is like I drew out here. Other experiments have done this. There's a particle part, which is a beam splitter. They use detectors. The detectors make pulses, and they try to see the timing between the pulses. The idea is that energy is supposed to be quantized such that their photon energy will magically deposit itself one way and not the other. This is a form of entanglement. It's a one particle entanglement. The other part of the the photon model is that you leave it on over time, you collect a bunch of pulses, and you could see an interference pattern. So we're going to show that it's this first part of the model that fails. So other people have written about this. Heisenberg understood this straight away, that the first part of the photon model implies reduction of the wave packet, entanglement, and it implies the wave function collapse. So he describes those ideas like entanglement way early. It's readily apparent. But to take this as truth, people have done these interpretations of quantum mechanics. It came up with all sorts of weirdness that you may have heard about. And I'm saying that this is not the way to go. The way to go is to understand what was wrong with the experiment. Look at the experiments. De Broglie did at the very same time a understanding of this beam split coincidence experiment, and many have. So let's go back a little bit. In 1900, Planck's equation, derivation of the black body distribution, you'll see in all our textbooks, they'll say Planck quantized light. It's just not true. His quantization was in the resonators of material resonator energy, not in the electromagnetic part. And so I marked this all up so you could read it on your own and see for yourself. So let's get that straight. There are derivations that show the black body equation where they do quantize light. My point is you do not need to quantize light, and Planck did not do it that way. So 1911, Planck had a second theory, which is what I embrace. I build upon his second theory. So he had this nice graph, which is in a book of later years, but he had this whole idea back in 1911. So it's about that there's a preloaded state where upon absorption of radiant energy, there can be a loading up and then a sudden quantized-like release of the energy. And so you can look at the algebra and see that what this is about is that Planck's constant is about a maximum, that there's sub-H action that loads up. And other people, Sommerfeld and Debye, embrace this theory. What's important also is that in this derivation of the black body equation, that he came up with h nu over 2, half of photons worth of energy. And this is used in low temperature physics, but this is very important. It shows that the average amount can be quantified this way. So let me go on. So there were many experiments done early on to try to see, well, can this loading theory, it was called the loading theory in various books, and I give references. Can that be seen to be true experimentally? They did it with these time effects. They look at the element of time in the photoelectric effect, and they see, oh, it responds really quick. Well, it's a homework problem in most of your textbooks that'll say that the loading theory just will not work because it takes too much time to load up like this. However, when Millikan did his rework of the photoelectric effect around 1916 in his physical review paper and his book, he did not like the photon model. He explored the loading theory, and he came up with this idea that there could be, it could work with only a minute addition needed to make the emission of light. The photoelectric effect does not need to have this loading time, so it could respond instantaneously. And all of these experiments with the Compton effect and the photoelectric effect that look at these quick times, they were comparing to a non-workable loading theory. So this is why the loading theory is not accepted. It was falsely compared in all our textbooks and a bunch of other books, and I give the reference for it. So there is another way around. And so I did a perfection of this version of the loading theory. So to review, there's Planck's first theory, where it's quantized absorption, quantized emission. There's continuous absorption, Planck's second theory, continuous absorption, quantized emission, and this minute addition, which I will now call a threshold model, where there's a threshold and then it just takes something to make it go off, and you'll be able to see that effect. So I drew this little cartoon. It's like filling cups, and you only see what happens when the cup is full and then it all spills over. So take the case of one at a time, h nu emission, Planck's constant times frequency. Notice I'm saying it's an h nu and not a photon. So I'm avoiding the photon model, but we still embrace that there's such a thing as an h nu. It's emitted as an h nu, but then it can spread classically the light, and that the energy can load continuously to a threshold and then show itself as an h nu. That's the threshold model. So with this model, we can see that we could have what looks like a 2-for-1 effect. One emitted, two responding, but it's not making energy from nothing. It's showing that there's a preloaded state that could be set off to trigger two detections. To do this experiment, it requires timing resolution and pulse height resolution. And so let's look more. These are the kinds of geometries that I'm going to explore in doing this experiment, and who did what. The beam split coincidence experiment has only been done by others. That's the first part of the particle model, to show that quantum mechanics is correct. It's the most fundamental test of quantum mechanics. It's only been done with visible light and one poor test with X-rays where they did not have pulse light resolution. And then, so it could be done with this beam split method and with a thin detector in front of a thick detector. And I'm the only one to do that. And then there's this control test that I'll explain later, which is to say if you have a one at a time source. But anyway, so there's visible light, there's gamma rays and alpha rays. I'm the only one to do this experiment with gamma rays. I did it with both of these geometries. And with alpha rays, I did it with the beam split geometry. I tried, but it was too hard to do here. And so I see what I call the unquantum effect, where I get 2-for-1 successfully, more often than accidental chance. So looking at what other people did on this experiment, this is the data of John Clauser. Clauser is famous for recently in the Nobel Prize for all this entanglement stuff. But he did the 2-particle experiment, but his analysis of it is based on this is a 1-particle experiment, one starting, and you see if there's a split. So Clauser did both experiments. It turns out he did this one later, but his analysis was thinking that this is a probability wave to start with. So this is the model of quantum mechanics, that what goes across space is a probability wave, and that it will show one way or the other. That's all straight out of that first sentence I showed. And they did all various ways. Different experimenters said, well, are they going to look at a weak source? Are they going to use atomic beams to see whether they have one H nu at a time or triple coincidence? They did a bunch of tricky things to make the argument that they're starting with one H nu at a time and then seeing if you get one H nu at a time with this beam split coincidence experiment. So the way it's done is you put together this histogram of the time difference between the clicks of the two detectors. So if it goes click, clack, then you'll get a point on the left of this histogram. If it goes in the other order, clack, click, you'll get a point on the right side of the histogram. If it comes together in time, you'll have a buildup in the center of this histogram. So this is the all-important part of the test. Everybody does this histogram. The past people who've done these experiments, these people, they use this idea of the time difference histogram. So I'm doing it their way, pretty much. So I'm showing you this was an earlier experiment. You could see the beam split, and they look at pulse height filters. They insert a pulse of light classically to test out to see if they get a peak in this time difference histogram. That's nice. That's a control test. The real test, when they dim the light here, they get a flat band of noise that indicates quantum mechanics. And they admit that if there's any peak here, they'd have to rewrite quantum mechanics. So they had the idea to do this experiment right. And they used this chance equation. They didn't do the experiment right, because I'll point out the problems with it. But at least they had the idea to do it with the chance equation and the pulse height histogram and the beam split, all that. The chance equation, I'm going to show a lot more later. This is the only important equation in all of what I'm trying to say today. There's a rate in the first detector, the rate in the second detector, and the time window, the time over which we're going to count that shows up in the peak of the histogram. And that's a chance rate. So we're going to be able to calculate what shows up by chance. And then there's these other people. So here's Aspe. He was also given the Nobel Prize for this related work. But again, this is a one particle coincidence experiment. They were given the Nobel Prize for the two particle experiment, but their reasoning about the two particle experiment is based upon what they understood from the one particle experiment, which is about that it's a probability wave to say it goes one way or the other. And so there were problems with how they did this test that I'll rattle off here. But what's important is that at least they understood to test quantum mechanics, to test both parts, the particle part with the beam split, and then to put it back together and see if you get an interference pattern. Now, I agree and they agree, everyone agrees that there's going to be an interference pattern. It's this first part that I'll show argument with. So what is it about visible light? And I mentioned gamma rays, but there's a pulse height distribution that any detector of visible light will have, whether you cool it or the newer solid state detectors, they all have this distribution with monochromatic light. So when these pulses appear out of a photomultiplier, they'll say, oh, a photon hit there. And they'll think, oh, they're all the same energy equals h nu because it's monochromatic. Well, there's this problem. There's all this noise here that you have to throw away. That'll just wreck the experiment. You don't want to look at a bunch of noise. I know they use those pulse height filters. I just showed you earlier where you could see them in their schematic. So but nobody says where do they set the pulse height filters to eliminate the noise. They leave that out. I keep looking for it. It's very funny. So if you were to take away these noise pulses, then you're eliminating too much of the data to make any kind of a energy budget for what's going on to try to make a 2-for-1 effect. You just cannot do the test with visible light. So straight away with this argument, which I expect you'll have to look at again later, but everybody does the experiment wrong. They all do it with visible light. Visible light does not have the ability to make the distinction between the threshold model and quantum mechanics. But with gamma rays, you do not have that problem. You get to see energy resolution, pulse height resolution. There's no pulse height resolution up here with light. There's no energy resolution. There's pulse heights, but they don't talk about energy. Like I said, they think that's all the same energy. So we'll use these pulses. It's called the photo peak. In this case, it's cadmium 109 emitting 88 keV and it's reading on a sodium iodide detector. So we're going to look at these pulses. This is the pulse height spectrum. So let me review. Pulse height is proportional to the electromagnetic frequency of the gamma ray, and it's also proportional to the h nu energy of detection. And I expect everyone is going to agree with that, but everybody else will call it a photon energy. And that's where there are problems, because they're putting the cart before the horse to say they're analyzing, describing their experiments with photons to wonder if there's photons when they did those other experiments. Anyway, with this sort of gamma rays, you can make the 2-for-1 argument. In a way, we're avoiding reading half height pulses. So we set the thresholds up here. So we're not going to see anyone saying, "Hey, Eric, you're looking at half height pulses. How can you get 2-for-1?" No, we're not doing that. So gamma rays also give us this property of using a better way to determine whether we have a single h nu emitted at a time. Very important. So it's this test, the one at a time emission test, that a great deal of nuclear physics uses to determine what our atoms are doing when they emit a gamma ray. Is it emitting 1 or 2 or what? Upon spontaneous decay. So you sandwich a radioisotope around 2 detectors, and you use the pulse height filters and such, and you see if it goes one way, but not both ways, and it'll make this band of noise in the delta T timing histogram. And they see that and they say, oh, it will emit 1 at a time. Everyone agrees on that. If it makes a peak in this test, they know it emits 2 at a time. And so they do it. And so this is from nuclear physics labs. They'll say, oh, yeah, it's 1 that is emitted in this isotope I use. And importantly, it decays to something stable. It does not go to another radioisotope that will then emit to make another thing to mess up our argument. 1 at a time sourced. The other isotope I use, it's 1 at a time sourced. These 2 pathways are not the same time. It's like one way or the other. They say that. They're not in coincidence. So with this test and these sources, we know we're emitting 1 at a time. So the sequence of doing my experiment is, all right, we do this, we see we have noise, it's 1 at a time, that's nice. Then we rearrange the detectors and ask, well, do we see noise? Does it go one way or the other? or does it go both ways? And we'll see if we get this peak that says it's 2 for 1 more often than chance, and that will refute the photon model. Like they said earlier in that Nature paper, if they see a peak there, it refutes photons. So, all right. So I do the one at a time test, and it's a good test of the chance equation, which I'm going to revisit here, the rate in the first detector, the rate in the second detector, the time window. That's how many that happen in the histogram of which we're counting. How many are we counting here? So you multiply all these together, you get some number, and then you compare, well, how many do we have here? What's the rate? And you take the rate, the experimental rate divided by the chance rate, and it should be 1, and it is 1. This is the true coincidence test to see if it's emitting 1 at a time. And so I do it. That's great. The chance equation works. Also, we don't see a peak here. That works fine. Then we do the real experiment. And, oh, what's this? The great big peak. Well, let's take the numbers. This is in a 300 nanosecond window. We're going to put that time into the chance equation here. We read the rate that we're using in rate 1 and then rate 2. When we put them into the chance equation, we get some number, just like before. Then we read how many are happening here over the time of the experiment, and that comes right out of the oscilloscope, the total and the duration. And you get that rate, and you get to compare the chance rate, the experimental rate divided by the chance rate. And lo and behold, this came out to 6 times chance. Sensational. Quantum mechanics only allows for the coincident click rates to reach the chance rate. And everybody agrees on that in both theory and other people's experiments. And so by exceeding chance, we refute quantum mechanics. So it's not a special case. I do this many different ways. This way, I'm using the other isotope, cadmium-109. I'm doing in the beam split geometry. Let's see, before it was the through a thin in front of the thick. Now we're doing it in the beam split geometry. And it makes this great big peak. We calculate it the way we did before. We get 3 times chance. Wow, that's pretty good. And you can see, oh, all the pulses are nice. You can see the spread in the time of the other detector and so on. We record in my experiments, I am able to record the pulse height distributions of both detectors, the analog pulses to see that they're not demented pulses, that they're well behaved. And we get to see the timing pulses that we're using, and we get to see the time difference histogram all at the same time. And I developed this method of using the LaCroix oscilloscope to do this experiment, to see everything. Let's see what else we have. This is what the experiment looks like. So there are these formal nuclear instrumentation amplifiers and pulse height filters. I do it the same way they do with all these experiments. And the LaCroix oscilloscope, you can see this great big peak here. This is the thin detector in front of the thick detector. It could be done open air or inside of a lead shield. It could be done either way. This one ended up with 22 times chance, really good. I have videos of this experiment, 17-minute video. We may want to look at this if we have time. And I also have a 1-minute video. These are easy to see straight off my website or the link, just clicking it from this PDF of this. Oh boy, now what? Oh, fuck.
Oh, Eric, is everything okay?
Sorry about that.
No, it looked like it was bringing the video up. If you
Yeah,
want to
yeah,
play
that's
that.
right. That's right. You can click it to advanced slides, but I had a link in there. Anyway,
And just very quickly, I should let people know I dropped a link into chat, and if they visit the page for APEC, it is linked. We have Google Drive set up for all the presentations, so they can get those videos there from your PowerPoint. I put the PDF version up.
very nice. Thank you. So here's another version of my experiment. Here's a giant lead shield that I put together. It's a foot in diameter with great difficulty to eliminate gamma rays from outer space and the environment. There are some experiments I did that were more sensitive than others. I wanted to make sure. So what you do in all these experiments, you have to subtract background. So that's, I didn't explain that earlier. On all the experiments, there are coincidences that could happen from background radiation. And so you take that rate, you subtract it from that experimental rate that's within the peak of your time difference histogram. So this is another way to build the experiment. You can buy this detector with a hole through it to get, it works better with this thin detector in front of a thick one. And so I give the instructions of how to process this so you can use store-bought components. That other thin detector I showed, that was a custom job that I paid quite a bit to have made for me. But it works either way. This works great, 8.6 times chance with store-bought detectors to see it defy quantum mechanics. So why was this effect not previously noticed? You have to know what you're doing. There are only two radioisotopes that have the properties such that it has to emit only 1 gamma per decay. It has to decay to stable. It has to have a reasonable half-life. My radioisotopes that I use, they're typically a year. So I've been doing this experiment for like 20 years and they wear out on me. But I still have it going. I could demonstrate this in real time in my lab now. But anyway, they have to have, some of these will only last seconds. Anyway, they have to have a reasonable half-life. This is the most important thing. They have to have a high photoelectric effect efficiency for the detector that you're using. So this is a graph of absorption versus the pulse height in the detector. And other people have worked out that there's two processes inside the detector where it would respond by the photoelectric effect or by the Compton effect. What I discovered is that the photoelectric effect it helps. It makes it so you can see the effect, my ion quantum effect, readily, if the photoelectric effect dominates over the Compton effect. And so that's why I say there's this sweet spot here of where the gamma rays should be in the absorption graph of the detector. Now down here, you can use another isotope and it gets noisier. I've done it, it's harder to do. So you get into noise problems down here with the isotope that's in your smoke detectors. Up here, this will be in many textbooks where they'll say, oh, let's look at the gamma of CZ137 and see, we're going to look at that later, that if it has just in the spectrum, do you see anything special going on? Anyway, the Compton effect dominates over the photoelectric effect. So up here, you will be very hard pressed to see what I call the unquantum effect, like this 2-for-1 effect. The other reason why this effect is not seen before is because of what I showed earlier about not understanding how to compare the loading theory to quantum mechanics. They used a broken loading theory, so they threw that out. And they thought everything was quantum mechanics, so they were convinced by it. There's a momentum of thought about photons. Who would expect to use what seems to be the most photon-like kind of light, gamma rays, to show how the photon model fails? So that's what I did. I actually had a little help. I explained this to my friend Ken Kittless about the whole theory and the beam split experiment, and he said, "Oh, do it with gamma rays." And so I tried it at first. It didn't work with the wrong isotope. I kept working on it. This was around year 2000. I've been doing this for a long time, hundreds of times. So anyway, if we can see a 2-for-1 effect, why not more? Well, I do. So back here in 2002, I'm doing the beam split geometry. And in this test, I'm looking at the pulse height distribution of this first detector triggered by the second detector. So what happens is, here's the normal pulse height that will show up. This is a logarithmic graph, which helps on these tests. If you get a peak here, you'll think, oh, well, there's a H nu click that happened there. But there's also the other one in coincidence. So this is 2-for-1 from just this peak. Over here, this peak is twice as big as the first one. This, to make a twice high peak, it takes these and adds them up in the detector. There's 2 within the detector that makes the pulse twice as big. The flash of light inside the scintillator would be twice as big. And then you see a peak here in the pulse height histogram. And then there's a hint of 4-for-1. And I've seen more than these in other experiments. Anyway, 2, 3, 4-for-1. Then there's the other detector, the high purity germanium detector. This is the best high resolution detector. And in this coincidence mode, I do see my effect. But first, let's just look at the pulse height spectrum of this, the singles, whatever shows up in this detector. There's this sensational 1 bin peak at 88 keV gamma ray. And then down here, we don't see the effect. This is linear, even linear. But in coincidence, the pulse height spectrum brings up this twice high peak. So that's a 3-for-1 effect in the other detector, going through the thin detector to the thick detector. This is a trigger to see the spectrum of the thick detector. That's what it is. It's a triggered pulse height spectrum. So this turned out to be 7 times chance. Sensational. It's really great. Oh, so you can see my effect just with one detector. And it's easy to do. Anyone can buy these radioisotope buttons. They're license exempt. They're not cheap. It's like $150 to buy this. So what? And you have to do it the way I say. You have to use a large detector. And there are textbooks that will analyze this sum peak, this pile up peak, and they'll say, take the amount here and then use a modified chance equation. It's the rate in that peak squared times the time window. The time window is, there's some theory where you have to understand, well, how long would the pulse be, how long a time lived within the detector is that time. And so there's some understandable theory about that. And I write about it in other places. So you get that time and people agree what it is. It's 300 nanoseconds here. within the scintillator. You calculate chance, and then you read how many are here, and you get some rate. And you look at the same ratio I did before, 6 times chance. The experimental rate divided by the chance rate. Quantum mechanics says 1. It should only be 1. And textbooks will do this experiment. With that other isotope, cesium-137, way up at 122 keV, where the photoelectric effect is below the Compton effect, we'll see that in textbooks, and they'll say, oh, it's like chance. Huh. But if you know how to do it, you get above chance like this, really great, and you see quantum mechanics fail. Easy test to do. So I didn't stop there. There are all these tests I did to see, well, what makes this tick? I invented a spectroscopy to see functions of angle with the unquantum effect by twisting around crystals and stuff. It lets you see the property of the electron. You get to see the bond structures with under magnetic fields, whether it's dielectric or, dimagnetic or ferromagnetic. It makes a difference. I got to see all that. Cooling the beam splitter makes the unquantum effect twice as much. All kinds of effects. I found that the property, the material state, whether it's crystalline at the source or metallic at the source, changed the unquantum effect. Nobody ever saw this. These are all discoveries that I'm showing here. These need to be repeated. The experiments that I showed you earlier, I've repeated many times. These were not as repeated as much, so I expect people to be agonizing over this forever. This is how the experiment looks with that giant shield from the side. These are 2 of these liquid nitrogen cooled high purity germanium detectors. Really great. I was able to pick these up on eBay, kind of lower cost. Just about everything I did was buying used on eBay. Oh God, I made that same mistake again. All right. What about rest mass? What about particle diffraction? Like, we've known from 1930 that atoms act like waves and electrons act like waves. There's wave properties and particle properties, and it's been duality ever since. This is an interesting experiment by other people. It was great. They did the experiment right. So I'm showing that with helium, it can smear across as a wave and focus, but it can also go straight through as a particle. So you get to see the 2 states, the particle state and the wave state in the data. And the authors admit that it has like a particle and wave state in their data. However, these particle diffraction kinds of experiments can still be explained with the probability interpretation of quantum mechanics. But it's still interesting to see that the matter wave exists and there's a particle state. There's a 2-state. This experiment straight away says that what's going on is like solitons, where it could either hold itself together or not to go in either of these 2 states. All right, except that it still has that problem of the probability wave. So I do the beam split experiment with the alpha, what they call the alpha particle, which is helium nucleus. I'll call it the helium nuclear wave function. It's helium alpha. It's very similar to what Rutherford did with gold foil and everything, except I use good detectors and look at coincidence. So the alpha can go through the gold foil to one detector, or it could bounce to the other detector. Well, does the atom split? That's the question. Now, if it did split, other people did these experiments with collisions to see, well, what does it take to split the alpha? It takes 14 MeV to do that. And what's this? I only have 5.5 MeV of kinetic energy from the decay of americium-241 to make this alpha. So we don't have enough kinetic energy to split it by conventional physics to say we're making 2 deuterons. And so here we have the data. It took a lot of, I had to program the LaCroix through the GPIB, through QuickBasic to get all this. And so I pasted on, this is the pulse height distribution of the reflected detector, the pulse height distribution of the transmitted detector. I just pasted this in the right place. It's in a 2-dimensional graph to see, well, what are the pulse heights of the 2 detectors? And here we could see half-height pulses are mostly what happened, but we defy the binding energy. So there's something really special going on here, that I'm splitting the atom like a wave, even though it's half-height pulses. And this came out to 105 times chance. Oh, but what's this? These are big pulses. These are the full height pulses. So you do the chance equation on this the same way as before. And we get 6 times chance. 2 for 1, splitting the atom. No one's ever done anything like this for either gamma rays or alpha rays. No one even tried. And so now we know quantum mechanics is done for both matter and energy. And so, well, what's going on here? I mean, first, let's look at all the different ways. I'm not going to look at all of them. I'm just listing them, that I did all these different ways of doing different foils with the alpha ray tests. And I scattered it off of diamonds. I got some effects with that. Very interesting. Different isotopes, different detectors, different geometries, blah, 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 blah. What about theory? Well, I used this beat model of the electron, and it turns out Schrödinger talked about beats in his first famous theory. And I actually had it earlier, but I looked back to see who was looking at these ideas about beats and thresholds and everything. I did a large historical analysis. So anyway, I used the beat as something very fundamental, the envelope of psi, Schrödinger's psi. The envelope of psi is the identity of charge, is what I get out of this. So I use that model, and what I've done is looked at the de Broglie equation and used this beat equation to notice that there's 2 beats for the way light wave interacts with it. There's a factor of 2 correction that's easy to put into a transformation from the de Broglie equation to the photoelectric effect equation using velocity equals frequency times wavelength. But you have to know this little tricky thing. And then you get the photoelectric equation. It's a derivation. I derived the photoelectric equation. Now, if you look back at what Einstein did, he took E equals h nu and said, oh, that's cool. Let's take a particle that goes at 1/2 mv squared kinetic energy. Let's just cram it together. That's it. That was his derivation of the photoelectric effect. I'm doing a derivation with algebraic precursors and connecting it to the de Broglie equation. So I derived the photoelectric equation. So I have some idea what the photoelectric effect is. And then I went and applied it to the Compton effect and derived that with waves. And I looked at how to see the black body. I did a derivation of that equation my way. And then I identified, well, what's the difference between matter and antimatter? These are all important things if you want to apply physics to see, well, what's going on with all this matter and energy and light and stuff. These are real, this is the ground floor as to how to think about this stuff without wave-particle duality, which is, well, we're going to lay that to rest, I hope. Anyway, there's still a problem here from this slide. What are these little M's and E's doing here? They still look like they're quantized, like the mass is a number and the E is a charge. So here's how to fix that. This realization of how to look at the equations of the effects that are famous for wave-particle duality, this is every bit as important as the experiment. This realization, it lets you see how the matter wave can work to show itself without the duality. So just looking at the de Broglie equation, there's the H to M in a ratio. Well, what does the experiment say, like an electron diffraction experiment? What is the message of the experiment without stealing H from another experiment or M from another one? The same with all these other tests. The message of the experiment is that there's a ratio. That's what's important. The same with all these others. I'll just write Q's. All I'm doing from looking at from the quantum mechanic view to the threshold model view, all I'm doing is rewriting the ratios like E to H here as a Q to say that's the message of the experiment. So from that, you get to say what goes across space in all of these experiments that show wave properties, it can smear out, and you take a little piece of that space and say, oh, there could be less M and less charge and less action in that piece of space, but the ratio is conserved. So when you do these beam experiments like electron diffraction and stuff, the identity of what they call the particle gets to be transmitted by the conserved ratios that go across space. And that property of the wave gets to load up at the absorber and then hit the threshold and give the click that gives the illusion of a particle hitting there. That's the resolution of wave-particle duality. This picture is. So you might say, oh, well, the Millikan oil drop experiment shows that charge is quantized. Well, when you do that experiment, it's not in free space. It's a drop of a godzillion charges. And there's going to be an ensemble effect that globulates it all together. It'll make it show just the quantized aspect in an ensemble in that experiment. But when you go to a free space experiment, you won't see that. You won't have that issue. So what I'm pointing out is it depends on how you do the experiment as to what model you use for charge. They took the model of charge in the oil drop experiment and said, oh, it's quantized. And then they put it in the free space situation and said, it must be quantized also. But I'm saying, hold on, not necessary to do that because the experiments show that it's only ratios, and you get to do this ratio principle and understand, identify the assumptions made in the past experiments. So this business about looking at past experiments and saying, oh, Eric, what about that? I've handled quite a bit of that. It's in my other lecture. Oh, I thought I had my other lecture. Oh, yeah, the other lecture I showed at the very beginning. So, in conclusion, just to reiterate some things, there's no entanglement. Entanglement was an illusion. There's no ghost wave. It comes out with all these weird things like we're all in a computer simulation, completely outrageous stuff. Light is always a wave. There are no photons. The matter wave is a real thing. It's not a probability wave. Planck's 0-point energy, we get to identify what it is and figure, well, are we going to be able to suck energy out of it or not? Probably not. But I do think we can interact with it. That's the important message here. To understand space, that there's something there that's a pre-quantized, sub-quantized version of space that I see straight away in the experiments. So we can identify dark matter, and there's a preloaded state of charge that's still available to interact with other people's ideas as to try to see these propulsion effects. So I think I have only a few minutes, and I'm ready for any kind of question.
Awesome, Eric. Thank you so much. So let me do this. I'm going to bring everybody in. We do only have a couple of minutes here. I'll be quick with the mouse, and let me see. I'm going to remove the presentation. Everybody, please put your hands together. Give Mr. Eric Reiter an enormous applause. Eric, thank you. That was incredibly detailed and rigorous research. I had no idea that you had done that level of detail on it. So thank you, sir. Thank you very much.
Hey, Eric, I was just going to say, I'd like to reconnect with you
Good.
And talk about your experiment.
Good. Yeah, I remember you well.
All right, great.
Yeah, Eric, I think we talked also in back in April. Yeah, we should talk again.
Good, good.
So I'll tell you what I will do. I'm just going to put this in the private chat. Eric, I have been corresponding with you on LinkedIn. If you want to give out your email, we can do that in private chat. But I do not paste those into public, right? Because they get. Let me see. But so you know what I am going to do is I'm going to put your website in public chat though. So anybody who wants to learn more about Eric.
I'm just putting it in now.
Okay.
But
there we go. There we go. And you've got your email in private chat, and anybody else can correspond through your website. And that way it won't get scraped from like our pages or anything, because that does happen, and you don't want those emails out there getting scraped. So, okay. Well, we've got about 2 minutes. John, go for it, sir.
Eric, very interesting. And I love the fact you're doing experiments, you're measuring stuff. Okay. Do you have a take on, okay, what is the resolution of the particle wave duality that everybody uses conceptually?
That's what the whole lecture was about.
If I missed that, I apologize. But can you give us a 3-sentence explanation of that?
Right. He said everything is thresholded, not quantized. Thresholded means that there are maximum.
Okay. Follow-on question: what makes the threshold? Where's this threshold circuit, A to D converter, basically? Is that in the vacuum too?
One step at a time.
I'm being a smart aleck. I realize.
Yeah. One step at a time. Just try to see what is there first, and then we don't have to wonder, well, what color are God's eyes?
I know.
Well,
I know.
John, I do want to. I want to direct everybody to thresholdmodel.com, and again, I put a link in there because Eric he's done so much work, right? That I don't know if there is a super short version of this. I think that you have to really go through. This is one of those presentations that people will have to watch and rewatch and probably go through the website. But, I really like the fact that he is looking at all of this new data from a new angle.
Yes, he is.
Curtis, go for it real quick, sir.
Yeah, I want to say I found Eric's work back in I think it was in April, and I contacted you, Eric. I asked you, hey, I've been giving talks in APEC. I'm glad you came and gave a talk. I have been working on a theory that basically quantum mechanics comes out as a low energy approximation, right? Correspondence principle type thing. But it's important in physics to understand, okay, what is fundamental, what is something that is emergent, right? So the quantum mechanics model may be something that is emergent and works in certain regimes, but not necessarily everywhere. And the thing is, in high energy, the theory I've been working on, Sachs's theory, he always would say is quantum mechanics is low energy approximation. So this is something that definitely needs to be replicated. I would encourage, any physics person out there that can do a paper. I unfortunately don't, I'm busy with Jim's experiment and Jim's work, but I would like to see, more replications and some serious follow-up effort done in your work, Eric, because
there's a very simple way to do the experiment I showed with just a gamma ray spectrometer. And all right, Shiva had a question.
Yeah, let's go to Shiva, and then I think that's it for questions.
So I believe basically what you're saying is you favor a soliton model of the idea of particles. And so, like for instance, when the paper that Schrodinger cited, when the paper that we get Schrodinger's equation from came from de Broglie, and de Broglie was talking about a physical, like oscillator model, and he was comparing two frames relativistically and seeing that there was the waves. And so you're kind of going from that de Broglie paper and saying that is part of what causes the energy level to rise to enough that it can cause a threshold effect. But are you saying like if you remember back how we actually met was in that 2016 conference that and I have had the same idea of talking about thresholds. So are you saying that there is an interaction with material so there's something about material itself that allows these various possibilities of additional energy to cross over a threshold where it becomes an interaction? Is that what you're saying?
Yeah, usually quantum mechanics works. Most of the experiments, you won't see the distinction between a quantized model and a threshold model. You have to know how to look to see through the illusion. And then you understand how it could be that you have diffraction, particle diffraction. That's a misnomer. It's a nutty thing to even say such a thing. So we're getting around this wave particle problem. That's my main point. Transcend wave particle.
Was I correctly categorizing what you're saying, though? I just want to make sure I was, not putting words in your mouth.
What?
Did I correctly categorize what you were trying to convey? In other words, that you have a soliton model. In other words, there are various waves in space or medium, whatever. And what I was talking about there, was that correct? That there is basically these addition of waves within what we think of as particles, even though they're more of a continuous.
It's a little different. It's a two-state. It's a two-state solution. It's not that there are waves and particles at the same time.
Right,
it's that it can hold itself together as a particle. There is such a thing as particle.
Right. Mm-hmm.
But it could lose that ability to hold together and smear out like a wave. So I'm identifying, right.
That makes sense for an interesting soliton model. Great. I'd really love to talk about this more.
Good.
Awesome.
All right.
Well, guys, thank you so much. And let me apologize for being a little bit tight on time. I want to go to Michael McDonnough next, but first, let's put our hands together one more time for Mr. Eric Reiter. Eric, that's amazing. Thank you. Absolutely amazing. You've got your email in there for folks to correspond directly with you from our
Good.
panel.
I want that. I want all kinds of feedback.
Our website is in chat. It's thresholdmodel.com. And thank you again so much, sir. Okay, so I am going to take everybody out now, and I'm going to go to Mr. Michael McDonnough. Michael, welcome back. It has been a while. So folks may not know this. I've known you for like 25 years now, something like that.
Yeah.
So
we were both youngsters at one point.
And actually, your mic is a little faint. Do you think you might be able to move that closer to your mouth?
How's that?
Yeah, a little bit better. Yeah, as long as you speak up, I think it'll be okay.
You got it now?
Yeah. And so you're going to be talking about it. And actually, I think that this isn't a direct propulsion technology, but I think it has a ton of applications, right? This is one of those crossovers where it's like this could apply to so many different things that thank you for joining us and presenting on this. So basically, we're talking about hemp-based graphene. Let me put this up. I think this is the one you wanted to start with, right?
Or the asymmetric capacitor one, whichever.
Okay.
But this one's fine.
Okay. Well, it's up to you, sir.
The asymmetrical supercapacitor I did because I've been following. I don't always participate, but when you guys had Exodus propulsion technologies on here, that really got my attention because I realized that one of the features of our material is that it has the highest capacitance for weight and mass of any material that there is that you can work with. So if we have the best capacitor material and it's super strong, can be either put in a flexible matrix or it could be in a stiff matrix, whichever. But so long as it's fastened to the ship, it should be able to be a part of the hull of the ship. And the capacitor, is essentially a shaped charge, and it can follow the shape of the craft, or it can be independent of it, and it can be a component. And so that got me excited. I'm like, well, I need to get a hold of these guys and get some of our material in the hands of Exodus propulsion technology so that they can test it and see if they can basically make very lightweight, very large scale, low mass asymmetric capacitors that will actually fly. You can actually make entire ships out of this material. And every other component of the ship is also something that you can make out of our material because it will matrix with ceramics or it'll matrix with polymers. Are you following me?
Oh yeah. I took myself out because you were going to run through things. Let me apologize for that.
All right. The slides there, it's just to show that this is what got my attention was the asymmetric supercapacitor idea. And if our material can provide that for them, then I'd like to get it in their hands, and I'd like to make some experimental devices myself. I've got all the equipment in my lab, to do that as well. But
okay, well let me get you in touch with Drew then. I'll get you in touch with Drew. In fact, I'll send both of you guys an email in just a moment. Now, Michael, if it's okay, is there a way to turn your mic up a little more? It's still a little bit faint.
Hang on a second.
And let me apologize for bothering you. So I'm going to let me take the asymmetrical
better?
A little bit better. Yeah.
All right.
Yeah. Just as long as, just try and project and we'll get you. Sir.
Sure.
Okay. And I'm going to take myself back out and my apologies for the interruptions.
What we're showing here is a reactor that manufactures the material. This is a little larger one than we're using now. I'm using a pilot scale one, which is probably 2/3 of that diameter, but same principle. We create it through a type of pyrolysis, obviously, because you're taking the hemp fiber and turning it into nothing but carbon. So removing everything but carbon, and then we do some further synthesis of it to create what is called mesoporous carbon. Mesoporous carbon has tiny little pores throughout the carbon molecule, the carbon material. And in our instance, it is micron down to nanoscale fibrils, like a carbon fiber, but a fibril, a very small fiber that's left over from the breakdown of the hemp material. It's essentially the bones of the material itself, the carbon bones. And we have ways of, through heat and pressure and some changes in the chemistry, we can make that material very high in carbon allotropes, richen in carbon allotropes through further processing. So we start off with a mesoporous carbon, which has tremendous strength and tremendous surface area for carrying charge for electrostatic capacitor. And also, we can build up the nanotube molecules as well for increasing the strength and increasing the density of the charge carrying capacity. But that's essentially that in a nutshell. What we can do is we can take our material, and because of the nature of it, it's paramagnetic. And being paramagnetic, when it's under electrostatic charge, it is then also able to be magnetically aligned. Because under electrostatic charge, carbon nanotubes are able to carry a tremendous magnetic field from the electrical charge that it's carrying. So it's like a stacked up electric field turns into has a magnetic effect. So we can cluster them, as you see in this image, along with either the ceramic or the polymer. In this case, I'm showing crystalline from ceramic material that is intermatrixed in with the carbon nanotube fibro bundles that we create through magnetic cohesion. And so that allows us to make super strong composites, which will make airframes that can handle the rigors of space travel and or regular things here on Earth, like for ships at sea or anything else that has to have a very high strength and very low weight. So as a material for constructing spaceships out of, you're not going to find a better material than the stuff that we make. And it's made from hemp, which means it's completely renewable. It will always be around, and we don't have to worry about importing it from China or anywhere else. It's, we can grow it. We do grow it here in the United States. And we're setting up a system now where we have complete over a supply chain so that everything is U.S. based. We can, get more material as needed, and we can keep the price low enough that it'll compete in the market with mined graphite, but with a lot more capabilities. One of those applications is as hyperconductive electric wire bundles made almost entirely out of carbon with the magnetic alignment into the nanotube wire. And the nanotube wire will have roughly 10 times the charge carrying capacity, electrical carrying, current carrying capacity as copper does. So, without the problems that are inherent with copper and aluminum, which is sagging and melting under heat, this does not exhibit those. So you'd be able to have power lines running through a spacecraft that are not susceptible to heat, won't burn, and won't melt, even under extreme conditions. So long as they're removed from oxygen, carbon does not burn, even at very, very high temperatures. So this is one of the solutions we're looking at producing in the future, not just for spacecraft, but obviously for reconstructing the grid from the ground up, where our material replaces all copper wiring and all aluminum wiring throughout the entire grid system globally, and made entirely from hemp carbon. So it'll be sustainable, carbon negative, no mining is required. So it's a tremendous resource that we're bringing to market. That it's been around for years and people have been talking about it, but nobody was doing it. So my company, Halotrope, has stepped up, and we developed a commercialization of the process for making it. And in the interim, we got very good at building up components of it that are allotropes that are more useful, like the carbon nanotubes. The mesoporous carbon is incredibly useful, but it has just so many uses. And then now the carbon nanotubes, especially if we can magnetically align them, become electrical wiring that can either be used as for carrying electricity with very little resistance, and what the resistance it does meet, the heat is dissipated very quickly because it's an excellent thermal conductor. Go to the next slide. And this is just showing a Tic Tac UFO, which I believe I've seen them, and they look to me like they're operating on electricity. I mean, they change direction like you're flipping a switch. So, you know, assuming these asymmetric capacitor propulsion system, similar to what Exodus is using and is developing, is probably already in use by these UAPs that we call the Tic Tac UFO. So, you know, I'm thinking we could do this now with our material. I came up with a couple of concept models, and in these I'm using a kind of a boomerang shape so that the asymmetric capacitors can, you know, the charge can be moved from one area of the craft to the other to change direction and, you know, increase the forward momentum, or, you know, switch immediately, instantly, side to side, similar to what you see the Tic Tac UFO do. That's a couple of the models I'm working on anyway. I can't wait to get to talk to those guys at Exodus and see if we can get some in their hands and verify that what I'm thinking is correct on that. Another thing we're looking at is in the future, in space, you don't want to have, you can't get out and fix anything. You know, if you have a problem, yeah, if you want to make something in space, the amount of people that have to be risking the vacuum of space in order to build things is ridiculous. I mean, it's everybody knows it's going to go to robots, but nanobots, fabricator nanobots, is something that we're really interested in developing. These are made from the same materials as the ship is made out of: the carbon nanotubes, the mesoporous carbon, and ceramic. And then when these nanobots go to where there's, say, a micrometeor impact, and they fix it, they can fix it with the body of their fellow nanobots, can be disassembled and, you know, put into place to, you know, repair any kind of damage that happens to the ship. And what I see is these things, by the countless numbers, working together to essentially weave carbon nanotubes and carbon fibrils and the ceramic materials and create whatever structure we want in space, or repair any structure we want in space, and be able to, like, you can go to the outer rims and, you know, out in the cold of space at high speed and extreme cold temperatures, your nanobots can work 24/7 and, you know, repair any kind of damage, and, you know, the people on the craft can be safe and, you know, deep inside the interior where they have, you know, radiation protection. And so that's one of the main things that I'm looking at doing in the future. You know, we have the material that's the best thing for the propulsion, it's the best thing for the hull material, and it's the best thing for any kind of armor that is required for, like, micrometeor impacts. You know, that's pretty exciting stuff. And there's just so many applications. That was the reason we set up Halotrope, is it's the company we're using to devise all the ways that we can apply this remarkable material that we can grow in abundance and make as much of it as we want. So I'm very excited about this material and getting it into aerospace applications. Right now, we're working with a battery company that is in startup mode, and one of the first things I saw was they were interested in doing carbon batteries out of a hemp carbon, which we produce. So I'm like, well, these guys are going to get into that business, so we need to be talking to them. So they've tested our material out, and they found that it is suitable for what they want. And so that's, if you could, I'm finished with that slide set. There we go. Any questions? Anyone have questions? I'm only about 20 minutes in. Am I still in there?
I'm sorry, Michael. Sorry about that. Do you want me to put the other presentation back up, or are you all set?
Let me do the control the what you call it, screen share. Let me get that.
Ah, okay. So if you click the present button, and then you can do share screen. Do you want to?
Yeah. Go with this one.
And actually, I did just forward an email over to Drew, and he would probably be heavy on the material side of that, and I forwarded it to some of the other guys too.
All right, you want to bring this up? This is a little quick news clip about the company that we're working with.
Ah, okay. So yeah, I think. Oh, here it is. Perfect. Okay.
Got it?
Yeah.
Start that.
Battery company plans to open up shop in Portage. This says Energizer is currently laying off all its employees in the same town. WMTV 15 News' Marcus Arsvold broke this story even before Energizer made that official announcement earlier this year. And Marcus, this new company would make hemp batteries, and they want to hire those employees being laid off.
Right, so this new startup company would make those hemp batteries in hemp carbon-powered batteries instead of lithium-ion batteries, which are still being made at the Energizer building behind me. But this company is slowly phasing their employees out as it heads overseas and to the East Coast. Wisconsin Battery Company, or WinBat for short, is planning to build a new $25 million plant in Portage. It's not at the Energizer facility here. WinBat's CEO Jeff Green says they pulled out of negotiations to buy the old building from Energizer. Portage City Council approved Green's pitch to build a new manufacturing plant at Portage Industrial Park. And even though it's still early in the process, he's already sharing what kind of hemp batteries they would make.
We're starting with small, hearing aid coin or alkaline type batteries. Next step for us is going to be the OEM type batteries. Ring or Milwaukee Tool are manufacturers that use their own batteries. Those are examples. And then finally getting into the EV market.
Now, I have spoken with people who would be losing their jobs. I reached out to them today and they haven't gotten back to me yet, but I will be talking with Green coming up at 6 about why and how he wants to hire all of those people. For now, live in Portage, WMTV 15 News, Marcus Arsvold.
I wish I would have known about the farmer's dog a lot sooner.
Okay. And do you want me to take that one down now?
Yeah, sure.
Okay. Awesome. So, Michael, are you all set, or did you have more?
That's what I got.
Perfect. Okay, well, let me do this then. I'm going to bring everybody back in, and let me see everybody who's kind of with us. Oops. Yeah, there we go. And yes, big applause for Mr. Michael McDonnough. Michael, thank you. Thank you so much. And so these are big ideas. There's the mesoporous carbon that your company is developing. It's all hemp-based, renewable. There are a lot of big advantages to the way that you're doing it as well as what you're doing. So the mesoporous as well as BioGraphene, both of these are really useful for asymmetrical capacitance, and they have tons of structural applications as well. So again, thank you so much for presenting. Do you guys have questions?
I have a question.
Yeah, go for it.
So it's my awareness that one particular super strong, super useful form of graphene is carbon nanotubes. Are you doing any work with carbon nanotubes?
Yes, we can synthesize carbon nanotubes with very high purity, and we've developed a method to separate them from the mesoporous carbon so that we can sell the mesoporous carbon for batteries and supercapacitors, and then we can have the nanotubes will be used mostly for very high level charge carriers, like tiny devices that need a high charge, like military drones will use that material for their batteries, but it's a lot more expensive. But the enrichment process and the synthesis process we have developed, and we can produce from the mesoporous carbon very enriched amounts of carbon nanotubes, and we can vary the size and vary the thickness of the carbon nanotubes to a very high degree. We can create essentially tuned carbon nanotubes.
That makes me very happy. That, if you wouldn't mind a second question, I was wondering how you, in your craft design, I noticed you have a sort of graphene on the skin, and you're using that to apply charges directly to the skin as a way of, well, partially using it for turning, and partially, it seems, for propulsion. I was wondering how you're applying those charges to the skin. Is that with plasma emitters, or just directly to the skin, and that's kind of creating plasma like a Tesla coil?
Yeah, it's a regular conductor going to it, or it can be a carbon, one of our carbon nanotube conductors that's laid down in ceramic for strength. But it is like a laminate of very super strong materials that can be applied to the ship and move the ship, because it sticks to it, and it doesn't have to be very thick.
Okay, and I'm actually just putting in the URL right now for Halotrope. So for anybody who wants to contact Michael, they can use the website, right? That's probably the absolute best way.
Yeah.
And then what I'll do is I'll drop your email into private chat as well. But again, I'm always hesitant to kind of give those out online because people scram them.
But the interesting part is we just got back with we have a LOI with that company, WinBat, and our LOI is to produce enough material for them to make 7.2 million hearing aid batteries a month. And so our carbon will go into those, and that for that purpose, they had to test the heck out of our material, and their testing verified that we have the highest capacitance and the highest porosity, mesoporosity that they've tested in a carbon. So, that means like 1 cubic centimeter of our material has like a half acre of surface area on which it can carry an electric charge, or it can, have capacitance for a static electric charge. So, it's like tremendous amount of surface area that gives you huge amounts of electrons in a very, very tight space.
So, from what I understand, the only thing that's really been holding it back is the scaling up of production. Are you saying that you've kind of overcome the scaling problems? Because that seems to be the only thing that's really people are reporting as the only problem with it.
That's what we've done. I've invested the last 2 years of my life. When it kept coming out that they were talking about hemp batteries, talking about it, and nobody was doing it. I'm like, what is the holdup? And then I realized that the hemp bast fiber that they're making it out of is difficult to work with, especially once you turn it into carbon. It's the toughest material you've ever seen. You can't mill it. So we had to develop a method to integrate milling into the synthesis process so that we can generate all the different the very, very small sizes that you want for, like, pumping it through a 3D printer. You can put it in a fluid and it'll actually go through the nozzles of a 3D printer. So now you can 3D print with our material.
That's incredible.
Yeah. Let me go to John. John had his hand up. Sir? Oh, I think John froze, actually. We'll give him a sec.
Either way, this is really exciting.
He's got his coat on. He'll warm up.
Wait, there he is. John, you had your hand up, sir? I think he's having internet issues. Okay. Well,
he's still moving around.
Yeah, I think he's having some internet issues. Jared, go for it, sir.
Yeah, Michael, outstanding presentation. I'm curious about your supercapacitors. If you can give any kind of numbers for those, like energy density or total capacitance, operating voltage, anything like that.
We're not discussing that kind of stuff right at the moment because until we get independent verification, I'm just talking. We don't have independent verification. But like I said, the battery company that we're working with, WinBat, they tested the heck out of it. And it has very low internal resistance.
Okay, wait, there's John. John, go for it, sir.
Why are you using hemp?
Because hemp has the hexagonal structure at every layer of the fiber, from the macro scale down to the nanoscale. It's basically hexagonal structure facing upward toward the sun and stacked up high. And it grows quickly. It's super strong. It makes incredibly tough material, which has all the features we need. It begs to be turned into graphene. Graphene sheets are naturally formed in the high pressure, high temperature environment that we put them in. And then once those graphene sheets curl up, they curl up into carbon nanotubes at the right temperatures and pressure. So now we can generate endless amounts of carbon nanotubes from inexpensive bast fiber from the hemp plant. And the hemp is
We got plenty of hemp, that's for sure.
Well, yeah, you're in Oregon. He's in Oregon, so yeah.
I'm in Oregon. Hemp's a big industry here.
It's a big industry everywhere. It's getting bigger because you can produce more hemp fiber in a year than you can produce any other plant. I mean, for the amount of strength that it has, sisal is close, but sisal is weak as a kitten, compared to cannabis fiber.
Can you smoke it too?
It's not really for smoking. As a matter of fact, once we're done with it, it's permanent. That CO2 is permanently out of the atmosphere, and it'll be gone forever. When we pull CO2 out of the environment, when we're pulling CO2 out of the environment, you can run it over a truck scale. You know what I'm saying? It's not like you don't compute it based on some algorithm. The amount of carbon we're taking out of the atmosphere, you know by the trucks when they leave, they go across the scale. That's how much carbon we got out.
Yeah.
So,
well, I'm not trying to be a smart aleck, but hemp has so many cultural connotations now. I just wondered if there's any other material.
Here's a really old connotation. Here's a really old connotation.
Those are old and backwards.
Connotation. The oldest connotation is that it's probably the closest thing to the tree of life on the planet Earth.
Well,
It
yeah,
can do anything. It makes food, it makes medicine, it makes clothing, it makes housing.
The ropes and riggings on the ships that brought the Pilgrims over were made of hemp. The Declaration of Independence was written on hemp. Yeah, America was founded on hemp. The only reason why hemp was eventually kind of thrown out of the way was more for political reasons and to make it where other countries wouldn't have access to a very important resource. And so that was actually part of the things that went against hemp and marijuana simultaneously. They were actually interrelated.
That's true.
Hemp made a big comeback starting in the 1990s.
Yeah.
And I think that a lot of that is just recognition of the tremendous industrial value that it offers. So
well, now we know that it can be used for not just from making shoes to put on a child's feet and feed and food to put in their belly. It'll make spaceships that can go to the stars. How about that?
Well, it's interesting. There's so many applications there.
Shiva strikes again.
I spent time in Wisconsin where the favorite saying there is, I'm just saying that, I'm sorry,
Well, the DOE
ever
actually.
since
I do
college,
believe the
everybody
stigma
told me,
of hemp is like receding, that there's a lot of practical applications of like material use and stuff like that these days in industry, and that, we're just finding more and more
Yeah,
out
the
about it.
stigma
well,
has been disappearing for a couple of decades now. There was a differentiation that really started in the 1990s, and back in the 90s, I remember you started seeing more about the uses of hemp, and they started to differentiate that because the THC content is negligible, right? So it doesn't violate any
okay, I
laws to
guess,
grow it. So
I'm behind the times, but
yeah.
when I was going to
Yeah,
college, everybody was talking about hemp, and they used hemp and
Oh, you used to get
marijuana.
arrested if you were caught with hemp because they'd claim it's weed and throw you in jail,
I know
right? Like,
the differentiation. There was no differentiation between hemp and weed. Hemp was just considered a polite term,
yeah.
and so
Hemp.
I mean,
Well,
I'm speaking of my generation. When I hear hemp, I just think,
yeah.
you
It's
know,
things have changed,
I
and in
told my
fact, John, in fact, industrial hemp, and I remember this from college. We studied this in college.
A lot of
Industrial
that
hemp.
is William Randolph Hearst's fault.
A lot of
why
industrial
did
hemp
Randolph
companies
Hearst
started.
not like hemp?
A lot of
Because
industrial hemp companies actually started breeding strains that were low in THC, and there were different reasons for that, right? But again, it started
Okay,
making a comeback.
the
So
reason why Hearst
I
did
get
that was because he
I,
owned paper mills, and they relied on wood, and so it was a direct competitor. And he owned newspapers, and so he's the one who put out tons of false stories, like people axe murdering their parents and things like that. There was a whole it's follow the dollars. That's where it came from.
well, I mean, I myself have smoked marijuana, and I did inhale. And I discovered as a physics major in college that I suffered from the rare side effect of marijuana, that it made me feel stupid and lazy. And I couldn't keep track of physics lectures. If I arrived at my lectures hungover from the weekend, I actually
John, you got
would
it
take
all
most of
wrong.
it.
You smoked an indica that put you down. You need the sativa ones that engage the other side of the brain and that are the art and inspiration.
with the
Yeah,
appropriate
well,
medical permits, of course.
my
Of
my
course, right?
my roommate in college, this is my freshman year of college. We were in a dorm full of 18-year-olds, all away from home for the first time, and we partied like crazy. And I actually gave up marijuana and just drank. I drank too much, of course, because I couldn't keep up in class, taking physics and calculus and everything like this. Because you stay high for several days. Now, my roommate did the opposite thing. He gave up alcohol and would only use Marahushi
Yeah.
weed.
Well, John, if
And
it's okay, let's.
and he flunked out. Unfortunately, he quit finally even going to class. And
Yeah.
so I'm just saying that I think that a lot of people don't understand the differentiation between hemp and cannabis. I'm sorry, and
Well,
like I so
yeah.
I just think that
Yeah. So, John, let's take things back. Let's kind of get back on track with my, because so we're talking about industrial applications, right? And so I mean, I know there are some cultural ramifications there, but it's one of those things where, I mean, I think we probably need to focus on the applications of the BioGraphene and the mesomorphous carbon, right?
I
And
understand.
after
Yes,
it's
I
been
understand.
processed,
Mesoporous carbon.
mesoporous carbon. So, I think Jared alluded to using it for supercapacitors, right? Definitely for
Supercapacitors.
Befield Brown.
There are several
Yes.
several very good papers. If somebody would like, if they would like them, you can correspond with me through email, and I'll get you those papers. That's our material has been shown to have the lowest internal resistance and the highest electrical capacity of any material for supercapacitors that's out there. Nothing else compares. So when you have the top material, we can charge a little more for it. That gives us the ability to make money at the early stages of our development. Right now, we're working on batteries because it's the low-hanging fruit. Obviously, the graphene and graphite that's coming from China, that's going to be an issue, especially if politics changes and China is put on tariffs. Then they're going to respond and not let us have things that we want from them. So it's going to be an issue where if you can make your own material and pull carbon dioxide out of the atmosphere in mass and make it the strongest, physically strongest material there is, up to diamond. We can make diamond. My reactor could make diamond out of hemp. We don't prefer that. Because the applications are just not as vast as the carbon nanotubes. Carbon nanotubes has, a lot more applications and for a lot less energy input than making diamonds. But same process, the carbon nanotubes is a type of crystallization. So
one quick question, very quick question, and then I'll shut up. What is the energy content per kilogram of supercapacitors now compared to like a lithium battery?
They have maybe 10% the capacity, but
okay, but that's a lot. It's a lot. Okay.
Yeah.
I know supercapacitors are really a really great thing. So anyway, thank you very much then.
Yeah, let me go to Jared.
Jared.
Yeah, Michael, so it sounds like your stuff's really exciting and it's moving really fast. I was wondering if you could provide any kind of timeline estimate for what your next steps, next phases are, and what kind of engineering challenges you're currently facing.
Right now, our challenge is money, like everybody that's in startup. And one of the things that John has brought forward in his discussion is one of the things that we have to deal with as well with investors. Because it's hemp, there's a smaller number of people that are willing to invest in it than would be if it was, wood from a forest up north. But the stuff that you get from the forest, it's just not the same. The material, the bast fiber from the hemp is much more able to be broken down in the proper form to make the carbon nanotubes because it naturally wants to turn into a carbon sheet, into a graphene sheet. When you blow apart the fiber, it unwraps layer by layer, and when it does that, kind of like an onion, those then thin out. Everything is decomposed, is driven off, other than the underlying carbon structure. So you get these beautiful sheets of graphene that are just falling apart in your reactor, and now you just curl them up into carbon nanotubes, and you've got yourself some of the strongest material on the planet.
And let me go to Shiva next, and then I had a question from one of the folks in our room as well. But Shiva, go for it, sir.
So are you working with Dr. Midland? It seems like, this is like some incredible science. I couldn't believe that it actually had been replicated and by other researchers and still hasn't been developed. It's like how has this not been developed? How are people not just throwing money at you? I can't believe it's just their superstitious fear of weed, that isn't even, it's not even related really, that is keeping them from making just a tremendous amount of money by finding your product. It's weird. So it's like, have you are you working with Midland, or are you, like, in other words, how are you showing and proving that you do have a superior production, process that can be ramped up? Because I mean, like I said, money should just be raining on you.
Well, we just signed the letter of intent with WinBat, Wisconsin Battery Company. They were the first ones that showed an interest in testing our material, because that's what they were, presenting to the world, is that they were going to do hemp carbon for their batteries. And we had just developed the technology to, we had put together a pilot plant of our reactor, and that pilot level plant fits inside of a 20-foot shipping container. And so it's infinitely scalable. We can go from there to a 40-foot container and almost triple our output, and with the same type of technology. And we clean up the, when you do the pyrolysis, we take the smoke that comes from that and the gases, and we convert those back into carbon. So we use 100% of it, and so we get a lot better rate of production than you would if you did it with technology that didn't include recycling all the components into the target molecule. So if you just say, for instance, did pyrolysis straight, and then you activated it afterward, like you're doing activated carbon, well, you lost a whole lot of carbon in the process, as basically as waste gas, as synthesis gas. Instead of making methane and making hydrogen, and other small hydrocarbon chains, you can recycle most of that back into our product by using electrostatic separation and magnetic manipulation in order to generate more of our graphene and more of the carbon nanotubes.
So did you say whether or not you're working with Midland? I didn't hear that part.
No, we're not working.
Okay, so just independent. That's cool. Okay.
I read everything that everybody does. I've read thousands of papers and dozens of patents, and I actually went through and one of the early patents that was done on this technology, I found out that they used too many of the same components as were used in the development or in the technology for making carbon fiber out of polymer. So their patent is worthless to them. I'm sure they spent lots of money on it, but because they're using the same basic technology as you would if you were making carbon fiber out of pan or acrylic, then you can't really patent something like that. They're basically trying to patent use of technology developed for plastics for a natural fiber. That's really the only difference between what they did and what had been done before. But those patents were awarded long before anybody even heard of graphene. So they were probably producing graphene along with carbon fiber for many, many years, but nobody knew what graphene was. So they didn't even there wasn't even the word graphene, back then. So it's like, until 2004, there was no graphene, but there was the processes that were used to develop carbon fiber, which incidentally also produces graphene.
So are the major battery manufacturers not listening? I still don't understand why you aren't getting funding, because it seems like you
they're
should.
tied to their supply chain. We developed our own supply chain, and we're a component now of the supply chain. The hemp fiber manufacturers, the farmers, the people who process it, and everybody else involved. We now work together to develop ourselves and our industry to the level until we existed, there was no carbon manufacturer. So we're the first to the market, and this will be the first, Wisconsin Battery Company is going to be the first ones to have a commercial hemp battery using our material. So until we existed, which is relatively new, and we did everything on a shoestring. We have about $150,000 that was external funding. Everything else came out of our own pocket. So, not having Fortune 500 money or, big institutions like University of Alberta in Canada, which has one of the primary patents. We just weren't in the area, in the market to compete with them as far as getting people's attention. But now with this letter of intent with Wisconsin Battery Company to basically make $6.5 million worth of this stuff next year, now we're getting funding. We got people that are showing us proof of funds, and we should be cruising right along with we have an offering out for like $5 million. But
I'll be looking for your IPO.
Well, it's right now, and one of the people that are looking at us right now funding us, they're interested in a holding company which will go IPO. The holding company will basically be their vehicle to get their money back out, I'm sure.
Yeah. Well, so let me see. Who else had questions? We've got about 10 minutes left. Let me go to Brendan, and I think we're going to go probably to lab time after this. So I was going to do Gerald, but Gerald is not with us today, and that's totally cool. So so we'll do lab time after this. Okay, well, go for it, Brendan.
I was going to say, careful, Tesla Motors doesn't just sequester your ideas, because Elon's pretty sneaky that way. He's snagged at least one of mine. But I just wanted to give you kudos. Like, this is the magic bullet. It seems almost too good to be true in terms of, like, you're not just carbon neutral, you're carbon negative. And that you're taking carbon and turning it into industrial products. And, we talk about additive manufacturing versus the old heat, beat, and treat. So this is a whole paradigm shift in manufacturing away from, digging rocks out of the ground and pounding and pulverizing them and turning that into stuff. We might be able to start to heal our mother. So I appreciate you. Thank you.
Well, if we can increase abundance for ourselves and for the rest of the planet, that's a win-win. And hemp is the abundance plant. I mean, it is the abundance plant. That's what it should be called, because it literally just makes everything that you could need: food, medicine, clothing, everything.
Wasn't it George Washington that said make the most of the hemp plant?
Yeah, I think so.
Now, can you, just out of curiosity, Michael, for structural stuff, could you use hemp fiber for fiberglass, or would that not meet the requirement?
Well, like you would a chopped carbon.
Ford made like a whole car, Tim. Like, that's in the literature.
Yeah, you can make tank armor out of it. Matter of fact, we're working on some armor right now that uses silicon carbide and magnesium phosphate ceramic, and it'll be half the thickness, 1/4 of the weight, and be able to stop anti-tank rounds.
In the movie Cheech and Chong, they have a car made out of hemp.
Yeah.
Up in smoke.
Reefer madness, right?
I think
based on reality, loosely based on reality.
Guys,
I'm sorry.
Guys, I'm trying to redirect us off, John.
Yeah,
I'm trying to redirect us off.
I understand.
John likes to have fun with
sorry.
I think we've learned that you need to focus on bio.
You just have that hill to climb. That's
what?
all.
On bio
battery.
Oh.
Yeah, focus on that it's carbon nanotubes and bio battery, and perhaps just kind of leave out where you get the material from.
Yeah, I think that's fair. I mean, it's coming from a plant, like any other. So
coming from a plant, that's good. I like it.
Exactly.
I like it.
Like so many other things.
Hey, we got Mark.
There's also such a thing as phytomining, which is being developed as a way of getting rare earth materials and minerals by growing plants. Like, you can take a mining site and plant certain species out there that are natural bioaccumulators, and then you can use those for your rare elements. It's pretty. It's a whole new world opening up.
What is good for that is coffee. Coffee absorbs gold. The gold regions in South and Central America, where they grow the best coffee, it's full of basically flat spin gold, what they call monatomic gold.
Interesting.
That's why. That's one of the reasons coffee makes you feel like it's a gift from God, because it's got that.
Got gold and then there
I got
be
some monoatomic gold right here, and I got it as white. And then also when I left it out in the sun, it turns purple. And that there's even some original pure 24 karat gold at the bottom that you can kind of see that it was made out of.
Well, you can get that from a good Guatemalan coffee now.
Yeah. Well, do you guys have any more questions for Michael, or should we go to lab time, do you think?
Can I just have a quick question, please?
Oh yeah, Tigre, go for it.
Sorry, what about the energy consumption for the process? I mean, does the pyro requires a lot of energy to put in?
Not really. Because we use a super insulated reactor, so our heat stays where we want it. But also, we recycle some of that gas, and because we use gas for heat, we start it, for instance, with natural gas or propane, and then we can switch over to the synthesis gas that's coming off the reactor. So it's very efficient.
Awesome. Okay. Well, guys, let's put our hands together one more time for Mr. Michael McDonnough. Michael, thank you so much. Thank you so much. This is a tremendous, tremendous idea. What you're starting on is amazing. And again, I've given your information to the guys. We've got your website, the Halotrope website, that is in chat. And so if anybody wants to learn more or get in touch with you, if they're like interested in using this for like asymmetrical capacitors or, structural components, things along those lines, those are all really great ways that they could put this to use. So
I'll be in the chat for a little while. So if anybody has any questions, I'll be in the open chat as well.
Awesome. Okay. Well, so I'm going to take everybody out. I'm going to go, actually, if it's okay, I will go to Mark first because Mark just popped in. So let's go to lab time. Mr. Mark Sokol. So Mark has been doing a ton of stuff, including arts parts analysis. You did the SEM analysis. You're doing metallurgical microscope work. You're doing all of that as well as dynamic nuclear polarization Elsevier stuff. So take it away, sir.
Okay, yeah. So the big updates from our last APEC, I've added a couple things to this S-band system. One thing that we've achieved recently was I think it was 5⁻⁻⁶ torr vacuum in the system. The main chamber that housed the sample had cracked, so I had to get replacements. That took a while. They're only made in Europe. We finally got them and been pumping down the system. And I actually was just opening it up in order to put a sample in there. Another thing we've had trouble with is our the actual sensor device that measures the weight. If you see when I push on this, you're able to see the oscilloscope moving up and down. So that uses some sort of piezo or a force sensor, and it's very sensitive to RF noise. This being both a microwave system with a strong electromagnet, there's a lot of sources of noise in the system. So we designed a RF absorbing foam, which is over here actually, and these slide into the chamber to absorb the RF noise as it is created. Another thing we noticed was that the turbo molecular pump down over there, that bad boy was creating a lot of noise and it was showing up on our oscilloscope. So we got an isolation transformer, that's that thing in black, and that got rid of a lot of the noise. So we're getting closer to running this bad boy at full power and should have a more substantial update in the coming weeks as we get the thing up and running. We still have a vacancy here at the lab. If anyone thinks they're qualified to work in a place like this, send in your resume. So you can work on stuff like this and other cool shit that we're doing over here. We don't need a PhD in physics. We're actually looking for people who are good at rapid prototyping, know how to do stuff in the manufacturing end of the lab, because all the theory and stuff, there's enough theorists out there, and what we need to do is actually build the experiments and test the experiments and get better signal to noise ratio. So somebody who knows how to work with sensors, vacuum, building stuff, MacGyvering, one-off builds, that's the kind of people we're looking for. So if you're interested, shoot over your resume. Another thing we got is a metallurgical microscope. We've been analyzing parts with it. Haven't had enough time actually with Arts Parts yet with this microscope yet. In order to attach the sample to microscope, I was actually using this painter's tape because the sample needs to be held underneath. So it's a pretty cool microscope. It has about 7 different types of filters. We saw some interesting pentagon or sort of star-shaped or I think it was octagon-shaped patterns in the metal, which was kind of interesting. So yeah, we'll be doing more analysis in the future. And Tim, I still need to get you over those pictures. Here are some of the samples that we'll be running through the S-band ultrafine experiment. So bismuth, magnesium, niobium. These are powdered metals that are held within an epoxy. They're held at the end of a stick, which is made out of quartz, and that goes into the chamber, into the exact spot where the dynamic nuclear polarization has taken place. And because of the leverage, we're able to get very accurate measurements on our computer. This one is the same sample that our original X-band experiment we got pretty good results on. That's aluminum, 98.5% aluminum powder, iron 1.5%, and the rest of it is encapsulated in epoxy, of course. And we got another sample. This is an osmium pellet, just pure osmium, 1 gram or 1.25 grams. And this we're actually going to probably surround with different materials, like different layers of thin metals, to see if the dynamic nuclear polarization can affect that heavy mass. Osmium being the heaviest material on Earth, or actually in the universe that's known to us. Well, a neutron star is heavier than that, but this is the heaviest element on the periodic table on Earth. That is non-nuclear, and it's slightly blue if you noticed, which is interesting. So that's going to be one of our samples as well, and that's pretty much it, Tim. That's what we're doing. Oh no, I forgot. There's some more stuff. 1 second. So Mercury vortex engine. We've been this I can credit all to Tom Butler. He actually managed to cut these blocks of PVC in half. These are going to be machined out in our CNC machine over here into probably be putting like little ringed grooves with a center spot in it. And we'll be putting 2 of the pieces together, gluing them together, and that will be our ring for the Mercury vortex engine. And we calculated we have just about enough mercury for it. So if we end up needing any more for the next version, we'll probably have to get a little bit more, but about 15 pounds of mercury, so it'll be about 7 for each one. 2 rings so that they can counter rotate, so we won't have any torquing effects. And yeah, that's what's happening with the Mercury vortex engine. And we should have an update for you guys in 2 weeks. I mean, I've been out of the lab for a bit on vacation. Just trying to get the kids to enjoy the summer a little bit before the new school year. That's it.
Awesome. Mark, thank you, man. Yeah, and actually you're the only person who is here for lab updates, but you know, I mean we've got back to school chaos at my own house. Wait, there's Curtis. Okay, let me go to Curtis next. You had your camera off, so I wasn't sure. Curtis, take it away, sir.
Sure. Let me do one thing here, and then I'll get started here. Go to the. I'm gonna open up the drive folder so I can, when I get to that part of the presentation, I can show you the actual runs that we have recently done. So let me cue that up. Okay, that's queued, and let me get this presentation. I should probably put do not disturb. Okay. Hold on a second. I'm trying to share my screen. Let's see. Present. Share screen. Okay. Okay. Can you guys see my screen? Hopefully.
Actually, I think there we go. Curtis, I will add that in.
Okay. So lab update for today. So we've been working. I mean, there's plans and there's what you have time to do. So what we're been basically working on recently is, of course, sourcing the materials to make stacks, testing other bearings, overcoming the 2-to-1 rules, basically the design of the actual device, and eliminating or reducing stick slip responses. And we've done a lot of upgrades to the data collection in terms of the tracker side, so upgrading the computer. So that's what we've been doing. So the reaction mass supports, we have actually upgraded this device so that now there are supports at the aluminum cap, and I think my update picture didn't show up, so I can follow up later and show you that. But basically, it's just like this. And what happens with this cap is we actually have a big ears cap, so it's a different, instead of this sleeve / flange bearing, we have a big ears bearing with the ones with that actually have the ball and have the ability to move in a have a freedom of movement, so they're more resistant to vibrations. So that's what's actually in the lab with Jim today. I put it on the device last night, and he's in there doing runs. So that is, we're gonna hopefully later on I can come back and maybe show some runs, or at least show you the picture of that device, because that didn't sit in there. So this is the biggest device that we have been working with since basically around the beginning of August, just before that. This has, as you can see, this I showed this last time in the open mic, where this bearing has basically a ball portion and an outer portion, so that can actually move at an angle, and it allows us to reduce the vibrational impacts of this. Now the thing is with this is that, again, the distance between the bearings and where the forces are kind of, they're not far enough apart. So that's what we're testing today, if that helps. So this was revisiting the open mic. This was the run from August 1st. This was kind of like the wow signal we got, where we're doing a sweep from 44 down to 24, or was it 45 to 25 kilohertz. And so before, when we would do these kind of sweeps, we would see some motion all throughout. There would be a lot of noise. In this case, it just basically sat there, and the vibrations were dampened quite a bit until we got close to resonance. And then you see this big kind of spike signal. So repeating what I said last time, basically the red is the balance. The green here is the actual device, and the blue is the calculated center of mass. And you can see that when there's stick slip events, right, the device and the torsion balance go in opposite directions, the center of mass doesn't really change much, right? There's a little bit of noise, but as you get to the resonance and where we think the effect is, you see the center of mass, go up quite a bit. And this is something we reported last time as a time average for over 1 second. It's looking like a 700 millinewton force, although you can, maybe if you compress the time, you might get higher forces, but that is something that we're not able to like reproduce those higher forces regularly, right? Those are transient. So I'm trying to be a little bit conservative in what I'm reporting here, but that is quite a bit of force. So that's exciting. Now the question is, after that, what happened, right? So we had one signal, the end of the run that day. That was like really big. And the next day, what happened is the thing fell apart. So the bearings were put in. There was no Loctiter in there or anything like that, and they were keeping them in. And what ended up happening is one of the bearings popped out. So then we had this device with one less bearing, and we weren't able to replicate it. Now we did try to put it back in that build. As we do these things, these are custom built devices, and they don't always run the way we expect. So I will, since you've seen a video of that August, or seen a picture of that August 1st run, I will show you the video of that, and so you can get a sense of what we're dealing with and looking at here. So this is about 40 seconds, and what I'll do is I'll skip ahead a little bit so that we can get to the part where it starts moving. So I skipped about 10 seconds in. And what you want to look at, this is the device, and it's riding on these rods, and this is the torsion balance, and you can see that big push that happens right there. And it's not a thing where like the device is going back, it's obvious stick slip. It's like, no, they were both going kind of the same direction. So the question is, were we able to replicate this, right? So that's the thing we're talking about right now. So yesterday, August 30th, we basically reconditioned the machine, the device. We had put it in before, but it was for some reason things weren't working. So Jim went and did some work on the torsion balance and did some, cleaning up of the device itself. We didn't make any changes. It's still four bearings. So basically, as this run progressed, the 7th run, you'll see it here. We get something very similar. Although what's different here is you notice that there's motion in the beginning, which wasn't there before. So somehow it's not as damped, but you can see that big push happens right at resonance again. And this it looks like it goes off scale. Now, one thing to keep in mind, that August 1st, the scale was 5 volts. Here it's 2.5 volts. So it's off scale here, but likely the peak is similar. And then here's run number 8. And one thing to keep in mind is when we do these runs over time, the device heats up and performance starts to degrade. So it's kind of like a sweet spot between like the self-lubricating bearings having motion. There it goes. So you can see that was a very similar, a little bit not as great of an effect, but you can see that showed up there. And prior to these, Jim had done basically, you see the sweep going from 45 to 25 kilohertz. Jim had done a narrow sweep within where that resonance is. And this was run number 6, so right before run number 7. And you can see here it's sweeping over 4 seconds, 37 to 34 kilohertz. And you can see that once the thing, kind of loosens up in there, it starts actually, during resonance, it frees up and it actually starts pushing repeatedly. And you can see there's one big signal there. So we're getting closer and closer to being able to like reliably replicate this. We're having, better mechanical systems in place. And I will show you one more, the one right before this, just so you guys can see. I don't remember if this one. Yeah, you can see that pretty big signal. So here, he's trying 47 to 34 kilohertz. So that was a wider range in 3 seconds. So that's a faster sweep rate. So as we change those variables, the device will respond differently. And, it's a thing about figuring out, where the resonance is and, sweeping through that resonance at what rate do you want to sweep to pull out the effect. So there you go. We're getting the motions we're looking for. So that is those are the videos. And I guess Eric came in today, and so I had before during the open mics, I have been giving this small comments on physics. I think I should kind of emphasize that what Eric has done. I mean, that's primary, right? The experiment and the interpretation of the experiment and what it leads to. So I really hope somebody can replicate that. If no one does, maybe one day I'll be able to. I think it's very important to have a clear understanding of what's fundamental and what we should be using for thinking, right? So quantum mechanics, we know, is able to predict to a certain extent, right? It's not a descriptive theory, but a predictive theory in certain regimes, and it works in those regimes. But we're finding it doesn't work everywhere. So when we talk about what's fundamental, and we're talking, and we're talking about higher energies and what is matter and those kind of things, I think we got to take a step back and be careful. So in terms of what I have in terms of what I'm working on in the theory, what I have accepted as fundamental is more or less these 6 things. There's other things, but that what Eric has touched upon is that the wave nature of matter. And what I'd like to say is that there are other people that have that have the same view. So that is something that you can look up. Carver Mead Stocks, I brought him up before, and it's very it's very interesting that that there's a convergence there on viewing that. So I'll end that for now. I have more to say on that, but we can leave that for another time. So let me go and I can take
Curtis, thank you so much. That's totally awesome. I mean, again, in terms of lab stuff, all of you guys are just like, all of this is surging forward. It is so amazing to see all of this work being done, and like the collaboration too, right? And so that's really exciting as well. So, and then I think the other thing I should mention is you guys are working on a vacuum pump, I think, with Drew from sunny Florida. He has a spare roughing pump that hopefully you guys will be able to send that across the U.S. So
yeah. Hopefully that'll help us get lower in the vacuum. And I'm looking at making a reconfiguration where the turbo pump is pointed straight at the chamber to aid in the lower, the ultimate vacuum we can reach.
Yeah. Well, I mean, this is a really tiny community, right? So it is wonderful to see people working together and achieving common goals. And we have that in a number of different ways. We have people who are building things, working together, right? Sharing parts and components and things along those lines. We also have theorists working with hands-on folks. And so you have this good spectrum of like technical, engineering know-how, and then theoretical ability, right? So it's so exciting. It is so
and I
exciting.
have been talking with David Chester over email, I guess, this last couple weeks, and he's been engaged, which is really great. She was engaged now with me, and so we're talking about these fundamental things, and these experiments are very important. Like I'm curious what David would say about Eric's work, for example. So this when you're doing physics, it's not like math. You can't just ignore.
Well, and I should point out, and I pointed this out in a couple other email chains as well. David is juggling like 6 different email chains right now, right? So he's busy. Like he and so they CC me on like all of these, and so like a bunch of the older physicists, they have some really heavy stuff that they're going back and forth on, and so David is like, I'm sure he's completely overwhelmed, but he's doing great. So. Well, so why don't we do this? I think that's it for lab time. So I'll just bring everybody back in. We can do open discussion. I don't think I need to moderate. I'll just bring everybody back in. Just try not to step on each other's toes, so to speak. And the only person I'll leave out is Jeremy, because I don't think Jeremy is there. So, but that's cool. So I say open discussion, guys. Let's go for it.
Okay, I just wanted to tell Curtis that it's very impressive, the work you're doing. Imminent. Yes, it is imminent. It's in the, we can see the dawn light, the light of the dawn in the sky. Curtis, I just wanted to say how pleased I am that you guys are getting those results. And please give Jim Woodward my very best regards. More power to him.
Definitely, John, and Jim. I know Jim likes to go things step by step, so that's how we're doing things. And you know, I'm trying to bring in the best engineering stuff that I know how to do, and it takes some convincing. But you know, just changing the bearings from those ball bearings on steel rods to composite bearings has made it so that we can actually repeatably demonstrate the thing, as long as something doesn't go wrong.
Very impressive. Very impressive. You know, I was there working with them. We were just getting very tiny motions, and you guys are really getting the big push now. The big push.
Yes, yes. And by the way, he calls that one with big the bearings with big ears. And I told him if it actually works, if we can prove it works, and that's the one that works, we got to rename it Dumbo, because then it can it's able to fly. So yeah, we'll see.
Yeah, I was about to go and check out. I missed the beginning of your presentation there, John, and I was wanting to catch up on that. I still haven't had a chance to. I'm looking forward to it. But I was curious, how do you know Jack? Because there's, you know, I'm picking up something about the way which you work. That
because I'm a smart guy. I know Jack. You know, and as far as Jack Sarfati and I, we've known each other.
Sarfati is right.
Well, yeah, I have yet to make the schmuck list. I have to say.
I always call him Sarfati. You know, it's late in the day. I'm tired, and no, Jack's a really smart guy. He's a quantum theorist. I'm more of a, you know, I approach quantum mechanics from kind of semi-classical method, which was good enough for Feynman. But you know, the really deep quantum mechanics, you know, Schrodinger's cat chasing mice. I don't know. You know, that's a little bit out of my field.
There's a level of knowing Jack that once you've gotten to a level of him knowing about you at all, you know this by the fact that he has cursed you out and called you something.
Oh, it's happened to me many times.
Okay, then you really know him well.
I got called a nothing burger.
That's why I call him. That's how you called me nothing burger. That's why I call him Wolfman. It's from old Wolfman.
It's just it's a love tap. It's a love tap.
It's a love tap.
It's his neurodivergent
exactly.
coping
It's his
mechanism.
way of love. You just don't want to make the schmuck list, right? It's like
Oh well, I was on his.
We're all schmucks by virtue of the fact that we're human beings that are not named Sarfati. That's just
exactly.
Well,
yeah.
let's not pick on. Let's not pick on him too much.
Let's not pick on Jack.
We love Jack.
Jack
is
a hero. Jack is a hero.
He can talk like that because he can back it up. He gets a pass.
Yeah, let's not pick on him too much.
He can back it up.
I think the other part too is his metamaterial stuff. There are so many things that are converging back on his metamaterials work.
I mean, in my opinion, yes. I think he's probably the closest to, and when it comes to everything from neuroscience and physics and merging them. I have never seen anyone who has their finger on the pulse as much as Jack, and I'm.
He's
it
got
makes
all
me
his
sus of
fingers
him,
on
actually.
it.
We need Sarfati back.
Really, but the man knows so much. He knows too much.
Actually, I had to go ahead, Jim. Sorry.
Yeah, I mean, I think part of that is Jack's email list. He corresponds, and he has for decades, with the people who are at the top of these fields, right? And so, you know, it's fun. It's fun to tease him every now and then, but he really is. I mean, I don't know what you would call it. He's probably one of the closest people, if not the closest, to being on the top of the hill. You know?
Oh yeah,
Really,
he's definitely.
He's a smart guy. Everyone should be listening to him. They don't have to always agree with him, but they should listen to him because his ideas are sound. I think his judgment is sound. He's been around the block. He's been around the block a lot longer than I have.
I mean, you know, he is the prototype for Doc Emmett Brown in Back to the Future, right? I mean, they knew of Jack Sarfati at that time, and he is literally the prototype for him.
Really?
Yes.
That's amazing.
Yeah.
Like
fabulous. Fabulous.
Thought it was Thomas Townsend Brown.
No, I mean, I heard it from
combination between the two of them.
Yeah,
he's probably a composite.
Yeah, well, of course.
Well, the last name Brown.
Marcus, Mark, I noticed you had the dog up there. Does that mean you filled the position, the vacated position already?
She's out of security.
Well
said.
Mark, I was going to be saying, please be careful with the mercury. I mean,
yeah.
it drove Michelson Michelson went insane after his floating his Michelson Morley experiment on just the mercury vapor got to him.
I hadn't heard of that.
And another,
Mercury
yeah, oh yeah, his wife had him locked up in an institution, and he managed to get a note to his lawyer to get out. But he went off the deep end for a little bit after the experiments. And another person who probably got mercury intoxication was Jane Fonda filming Barbarella. If you ever watched the opening scenes, the mercury-filled helmet, she had to wear that thing all day. And after that, she went on a tear. Of course, she was married to Vadim, in France. That's
Well,
enough to
the
make you
Mad
go crazy,
Hatter
too.
moniker has
Yeah.
to do with mercury being used in hat production and driving hatters crazy. But I had a thing, connection that was made during the presentations between Alex Tigre's talk about the luminiferous ether. Somebody brought up Jack Sarfati. John Brandenburg brought up Jack Sarfati, and there seems to be a connection there of sorts between the rate of the propagation of light, aka speed of light, and space-time. And I was wondering, I didn't get a chance to ask earlier, whether the ether is another framework for understanding what we know of as space-time, or if it's caused, like if it's affecting space-time, or if they're basically just the same thing. And that pertains to Jack's modification of the refractive index. Sorry, losing my train of thought. But
Brandon, if I
speed of light
can, before you go
to
off on a
modify
new
gravity.
tangent. Okay, you guys can't hear me. Can you?
Yeah, we can hear you.
Can anyone hear me? Oh, I was just going to say about mercury. We got a mercury vapor detector, and I keep it in a bag of powdered sulfur, which is supposedly supposed to create a strong amalgam of it.
There was something you were bringing up about about Sarfati. Like, I mean, I know he won't touch ether. But what was it you were asking, Brendan, again?
There seems to be a connection between this modification of the speed of light and gravity that Jack brings up, but it seems like the luminiferous ether could start to help explain that connection if it was brought into the picture.
So I haven't heard him say anything about a refractive index, but basically the curvature of light around the sun in ether theory is a lot like the refractive index. In other words, the change is because there's a gradient of alteration of the speed of light around gravitational objects, and so it is very much like refractive index of the ether itself that's causing the curvature of light around massive objects. But I had not heard that Jack was in any way using that terminology. Could you tell me a little bit about that?
Well, the way that he was describing his use of metamaterials and metamaterials to change the distribute the I remember him bringing up the phrase refractive index at one point. I might be mistaken. But
yeah, a negative index can cause it to curve backwards is probably what he's talking about with the metamaterials. And so that's how you're by using a negative index in them, metamaterials, you end up changing the way that the light curves. In other words, you would usually curve one direction, but then you make it curve the other.
So the thing about the speed of light, right? If you look at, theories like Sachs's theory, where there's a mechanism, there's a background pair, an ether, whatever you want to call it. The speed of light actually comes out of the wave speed of the electromagnetic radiation in that media. So if you're changing the density of the media, then you're going to likely change the wave speed. So
the rigidity.
Yeah. There's multiple
Well,
effects.
specifically, those two are the most direct, and that's actually where I feel like ether theory. The reason why it ran into a problem is because of Fresnel saying it was the change of density of ether in an object that caused it to have the refractive index. But instead, you can just all you need to do is change it to, instead of increased density, it is reduced rigidity. And then the formula comes out exactly the same, but the ontological statement about what's actually happening to the ether in the presence of matter changes, but still causes the same alterations to the speed of light in the exact same way. So.
Right. I recall now. I was thinking of his alteration of mu and epsilon in order to change that value of c to the fourth, and that's what I was thinking of.
So going back to the physics, one question I have for you, Shiva, and maybe anyone else dealing with ether experiments and those kind of things is, we know for sure that you can take gamma rays, and they come together at certain energies, and you get an electron, right? And we know that if you have an electron and a positron, right? We know that if you get an electron positron, they come together, you get gamma rays out. Now, if you have those gamma rays, where is that matter coming from? Is that matter, that experiment, in terms of like an ether, like, okay, you can't detect it, but you get high enough energy, all of a sudden, everywhere you go, there's electrons. If you get high enough energy, you get other particles. What is the mechanism for that, right? First, it's like, okay, here's the basic understanding of the EM energies, but then there's inertia there as well, which is it EM, is it not EM? Those are fundamental questions. But in Saxe's theory, that comes out, that electron and positron come out because in the theory, there's a dense sea of them, or a matrix or whatever, where the energy, they're basically getting out of the ground state that they're in, and now free.
Okay, so just going back to my version of ether theory is just the extension of the dominant ether theories, from where they were. And so, that means you're going to have a model that's based on Kelvin's, ring vortex atoms, and that extends up to a few different other things like, Kosarak continua, which are a model of a superfluid. So it's a superfluid vacuum. So the way in which matter formation occurs in this model is that basically there is something called wave vortex duality. And that is whenever you have in a substance, a wave, especially if you set up like a set of standing waves, and say you have a set of standing waves in a square, thing of water. If you create a checkerboard of standing waves, underneath them you will have these counter-rotating vortices that are there as well. So this is something well known in fluid dynamics, is that waves and vortices are dual, in that waves pump vortices shed waves, and they're basically one phenomenon because of the way the mechanics, in other words, the fluid has to mechanically gear against things, and so there's a lot of this sort of gear work sort of look at it. So whenever you have the combinations of waves and an increase in amplitude, what can happen is you can increase the speed of the vortex that is accompanying a given wave, or if they are crossing in some way. So because of the increase in the amplitude of it, you can cause a substance to cavitate. So in other words, that is a threshold effect when you have overcome the elastic threshold where it can no longer support the typical elasticity, but instead it rips apart. And so that is a threshold effect where you can actually have something go from being a fluid, which is and waves, which is continuous, to something that is more localized and therefore particulate. And so the creation of mass would be this mechanism by which the amplitude of the wave is converted into a speed of rotation, which are basically kind of both in the same place at the same time, and that can lead to this cavitation effect and all of the effects around it. So that would be the way in which you would have this material. But the difference between something that is persistent matter versus something that is not, that is either only particulate while in motion, would be the fact that you have to have a mechanism that can basically turn waves around, because waves are constrained to move in their fluid. So if the fluid is rotating fast enough, a wave that is traveling in a fluid that is rotating fast enough can be turned all the way around back in towards itself, towards the center.
Yeah.
And so you can create an infinite flywheel of energy if the rotation rate is high enough. And so what you find is that the vortices can create cavitation when you are starting to reach the speed of sound in that. In other words, the mechanical wave speed. When you're when the rotation is reaching the mechanical wave speed, it starts to do this cavitation type effect. So that's where the creation of matter would come from. In other words, that's how matter and the difference between the different types of matter, energetic particles versus something that is more massive. The reason and the reason why it is massive in the case of something that is a persistent particle is because the rotation that you have in this complex knot. So in other words, it'd be a vortex, it'd be a toroidal vortex, and inside it you've got these things I've shown on some of the other presentations. I think you remember the cymatic figures. They're also known as Faraday waves, and it creates these specific locales where there are vortices within the larger toroidal vortex.
Yep.
So those things are part of a mechanism where you've got it's staying in one place. But that kind of rotation, when it is touching an external set of fluid, because it's doing this internal rotation, when you have to have some way in which the two surfaces, in other words, which you've created this surface that with it's kind of like a laminar flow layer. What's happening is there has to be sort of a idler wheel effect, is what Maxwell called it. There has to be something that allows them to move against each other, and still if you have something that is kind of in a gearing sort of situation, then there's going to be the rotation that is internal is going to express itself outside of that skin. In other words, the skin is going to be moving against the outside surface, and then that outside surface, because it's geared against it, it also has to rotate in some way. And then you have out from this surface, you have the vortex filaments, and that's where you have this whole set of vortex filaments around matter, and that's which are
I'd be very curious what your thoughts are on that whole quasicle theory from John Williamson. That there's a lot of material there, and I was quite shocked when I found it that he had worked backwards to a similar, basically a Clifford-Dirac algebra from kind of like the point of view of a particle physicist coming in, and then ending up with that, and that. Almost the same thing that Sachs came in, with his, development of basically the same program Einstein had with getting rid of the parity and time symmetry. So it's like it was shocking to me. Like, oh, here's the other puzzle piece. They just kind of fit in, and what you're describing is sounds a lot like what he was doing in terms of like the fundamental. And the other thing I want to say about that, it's important. Like the reason I reached out when I found Eric's work, Eric Reiter, is that knowing these quantum ideas, the quantum mechanics ideas of probability being fundamental or not. This is important stuff because we're talking about something like and the quasi-cyclical guys call it subquantum, but it's kind of outside the scope because really it's higher energy, it's smaller, and we don't have direct experiments for some of these regimes. Some regimes we do, and we find that there's nonlinearities and things that are not expected. So answering that question, is quantum mechanics fundamental, and do we have to keep it in there? Because that actually idea, if it's not fundamental, is blind. Basically, is blinding us to what is real, right? So if we kind of set that aside and we can start talking freely about, and we do, about these what is down deep.
But you're saying is quantum mechanics fundamental, but you're presuming a specific interpretation, because there is the de Broglie-Bohm interpretation of quantum mechanics actually can fit perfectly with a fluid dynamic version of space. In other words, like it is especially when you look at the work of the Coudet and his name, John Bush at MIT, and all of these silicon Walker experiments,
Yeah.
how the droplets explore a Faraday wave mode of a cavity and all of that. All of those things directly show how the apparent randomness that you see in quantum mechanics can have an underlying layer that is completely mechanical.
Yeah.
And so this the fundamentality of the stochastic idea of quantum mechanics, I think that is what can be challenged, and I don't think that that it's I think it's important to differentiate the two.
Yeah. So keep in mind that with quantum mechanics, if you're talking about a more fundamental layer that's descriptive, that's not right. The standard, the Copenhagen or whatever. Like you go in there, there's all these other interpretations, but the mainstream is really what it is. And keep in mind that's what people are using when they're trying to develop the ideas and understand how things work. So it's kind of tainted. Like
they don't think there's any additional
there's something more fundamental
information.
Yeah,
but there is.
Right. If there's something more fundamental, then that becomes a subset. Kind of like what happened with GR and Newton's work, right? Where you use Newton like pretty much most of the time, but when you have like higher energies, higher masses, certain things, you have to use GR, right? We have GPS that has to use general relativity, to get the time corrections and all that stuff. So there's differences in if you're only thinking of gravity in the Newton way, you couldn't have GPS. So that's the thing we got to realize is like, what is fundamental? And it's a question. I don't know the answer. But to me, I'm looking around and there's evidence and people that have done a lot of work in, with electrons saying, hey, matter is a wave. What are you talking about? Right. So.
Yeah. Well, guys, it's 4:41. Should we close things down at 5 tonight, Pacific? That's about 20 minutes left. Okay. Yeah, it's a little bit shorter than usual, but this has been one heck of a conference session. I'm really excited. Thank all of you for presenting and being with us and helping bring all this together. I mean, we started out strong with John and just it's just been like all the way through today.
Conference.
Yeah, this has been a really amazing conference.
I think we need to give Tim a hand for all his work, don't we? I think we should. That's right.
Thank you. You guys are too gracious. I'm just trying to keep things together. What I would say though is we've had more and more folks reaching out who want to present, and so we have a bunch of good stuff that's coming up. In fact, I just had that up a moment ago. Let me go back in here real quick. So
guys, I got to go, unfortunately. I'm have to leave a little bit early. So thank you so much, Joe.
John, thank you. Thank you.
Thanks, John.
Yes, thank you.
And we will get some replications. We'll get some replications for your experiment, sir.
Hey, if you don't believe me, make me a liar. Repeat these experiments.
Only you'll end up proving them right, so the joke will be on you.
Yeah.
Right? I know it will be.
Thank you again, sir.
There is no wrong or right, only useful and unuseful.
Yeah. So, I mean, Dennis Lee had more stuff that he wanted to discuss. A fellow named Jack Al-Kawadi, I believe, from the Middle East, had something called the Star Drive Mass Relay System to talk about. Jason Cassabry, and I'm really excited about Jason's work. He is an associate of Greg Hodgen, and he has this concept for dielectrophoresis as a means for artificial gravity. So it's kind of an innovative gap, I guess, in science that he's helping to fill. Then Mark Fiorentino. Mark is working through some. He has some scheduling conflicts right now, but we may be able to present that for him. Louis Rancourt had light gravity theory. That's something that Wayne Ojala found for us. And then Nathan Innan had classical. He had an update on classical coupling of EM and gravity. And then, of course, Jared has coming soon a giant update on arts parts. So that is coming. And let me see. Oop, they took everybody out except me. Okay. And then Lance Williams actually has inductor rectilinear frame dragging and the local coupling to the gravitational field of the universe. So we've got some good conference presentations coming up.
Sounds really good.
Exciting stuff. I hope to be able to add something to Jared's update on Arts Parts. We're going to take some more pictures and I'll shoot them over to you guys.
Yeah. Well, and then Mark also has, and Jared asked me not to put these up until he has time to kind of organize things. But Mark, you got a ton of scanning electron microscope photos of it. I mean, and thank you for that, man. I mean, you guys are just moving mountains right now. It's amazing. It is absolutely amazing.
And then we're getting a terahertz source too. But that's a secret though.
Oh, okay. Don't tell him.
Yeah, just as a little like teaser for that whole Arts Parts thing. So we already have enough information right now to cast a little bit of doubt on the info that was put out by Oak Ridge. But casting a little bit of doubt isn't good enough. I want to cast a lot of doubt. So we're making sure that we got our I's dotted, our T's crossed, that we have as much spectroscopy information as possible. Also, we're not really here to like, poop on them. Really, we're more here to just identify stuff that other people haven't identified before or have identified but haven't shared. And we're doing that by doing our own testing of it, right? You don't want to rely on other people's results. You want to have your own data to work with. So hopefully in the upcoming few weeks, we're going to be able to get a few more tests done. And then we want to put all that information together into a single, like, here's the next big thing on Arts Parts, rather than just piecemeal a little bit at a time.
Yeah. Well, and I already have a photo gallery that's up for that, and I can either create an additional one or I can just add to that, right? Either which way. And then, we can do all sorts of live streams, we can also do Zoom. There's all sorts of things that we can do as focus areas to try and update people on that. I mean, from what I've seen, I mean, again, without going into details, because he asked us not to, we were given a chain of custody verified source of the Arts Parts material. It matches all of the rest of the stuff that's been tested, right? So we know it's real. I think the question is nobody's sure if it's legit or not, right? Going back to the 1990s.
Although I will put that out there that for anybody who has read Lou's book Imminent, he does have a little tidbit in there where he's talking about the warp fields of the things. And instead of saying the power requirements, like he says he's saying, you would need the power of about, he says terahertz instead of terawatts. And the terahertz that he says just so happens to be right where I've got like 3 different sources that are all saying, yeah, that's the frequency you need with that.
Wait,
so,
can we give our frequencies out? So wait.
I don't see why not. So in the book, he says 3.2 and 5.6 terahertz. We'd already seen from other put off stuff that they thought it would be somewhere between 1 and 4 terahertz. I've received a couple of different communique that suggests that the ballpark is somewhere around 4.4 to 4.6 terahertz, which is right smack dab in the middle of Elizondo's 3.2 and 5.6. So what I've observed about this is that it looks like the frequency that they may have successfully gotten the sample to levitate with would have been related to the thickness of the bismuth layer. So the thickness of the magnesium zinc layer, which is weird. Everybody thought it'd be the bismuth, but it's the magnesium zinc. So the magnesium zinc is somewhere between 1 to 200 microns, and the wavelength for where it looks like this works well is around 60 to 70 microns, which just so happens to fall right smack dab at about half wavelength for the thickness of the magnesium zinc, which is interesting. There is a possible relation there. So we are working towards getting a good terahertz source that we can work with. Also, the spectroscopy stuff that we're trying to get is going to be hopefully lead some more insights, not just to the inner workings of the stuff, but we're really hoping that we're going to be able to identify some special stuff with the bonds between the different layers, because that's kind of a smoking gun. Somewhere else in Lou's book, he mentions how the technology present in the sample was something that absolutely could not have been manufactured even in 1996. and maybe possibly could be manufactured today with like many billions of dollars. So like there's no way that, 6 samples of that popped up into somebody's hands in 1996, and even less of a chance if it's the real deal and it came from 1947.
Yeah. Well, and there are so many convergences here. I mean, again, for me at least, Arts Parts could offer some validation for Jack Sarfati's work with metamaterials. It absolutely dovetails back in with Mark's work with dynamic nuclear polarization, right? I mean, so you've got so many interesting possibilities there. And then, Jared, I know you've been exploring this idea of quasi-crystals also, right? And, so there's a lot there.
What you got, Curtis?
Jared, so we should probably talk sometime, because when you're describing these frequencies and the trouble with finding them, that's something very similar to what we have in terms of when we're doing the experiment of the Mega Drive, because really for us at least we're really trying to match a mechanical and electrical resonance for that to happen, and a lot of that has to do with like the structure, the internal structure of the material, and all sorts of stuff. So fortunately for us, it's in a range where we can sweep through frequencies, we can measure these things, but it sounds to me like for yourself, I mean, really trying to figure out an empirical method of finding out where resonance is and where what you're trying to get at and what that looks like, because
Mm-hmm.
they could be putting in a complex waveform.
Yes, that.
And
So
by
in
the
our,
way, as just to let you guys know, I have no idea what Arts Parts are, but I'm surmising that they're claimed pieces that were from some crash. Okay. Thank you.
I don't know.
So we were just talking.
Layered stuff, right?
It's the bismuth, magnesium, zinc stuff. Yeah, we were
bismuth. Sorry.
We were just talking in our meeting about it this week, about how for our terahertz source, you don't necessarily want continuous wave. In fact, I've heard that there's a specific waveform that you need to be able to make this thing levitate. And so we're trying to make sure that the source that we source for this is going to be able to perform with the very specific waveform that we need at the speed that we need it to perform at. So yeah, you need a source and you need a detector, but that source can't just be an on-off source. It has to be a controllable source.
Yeah, and if you look at Jim's equations, it's the change in mass is proportional to dP/dt. Not that theory has all of it, but just there's something to be said about that. And I would say the more empirical you can get, the better in this case, right? The theory stuff, it can be guidance and maybe what other people did, but you want to empirically know that material and how it responds, and see what you can do. That would be my recommendation.
I'd like to bring it to the more artistic and kind of pattern recognition part of this, because I don't know if you guys are aware that like there's always this crossover between consciousness in control and of ships and things like that. So terahertz waves are the one thing that ties all of this together, because terahertz waves are found being produced in the brain. Microtubules seem to be resonant with it, and there's there's been these findings that microtubules can do some superconducting at high temperatures. As there's it ties together all of these weird little niches. Just
Stuart Hameroff has a new video out about that. It's really awesome.
Well, so then that would, I mean, that raises a lot of strange questions. What I understand is that terahertz are very difficult to generate because the emitters tend to reabsorb them, right? So you can't get the waves out of the packaging very well. And that's what the electronics industry is having problems with. But if that's present in the brain, then I guess that like, if we're working with that, would that potentially cause health issues. You know, I mean,
There is some possibility of that. Like it actually can interact with the skin, and it can change certain molecules that have to do with vitamin D absorption. So that's actually kind of dangerous. So there is some reason for concern about a lot of dose, but it's the depth of penetration is really very low usually. It's like it almost doesn't penetrate at all, and so there's kind of this
okay.
debate about how dangerous it could possibly be with how little it penetrates. So yeah, it is interesting, but there was this MIT paper about terahertz being able to cause cancer. You can find that, just MIT terahertz cancer. You'll probably bring it right up with the review. But there's also the different frequencies can go from it's what it is. It's resonating the actual biological molecules. In other words, there is a size relationship of the size of a terahertz wave and the size of certain biological molecules, and then those molecules can actually resonate in certain ways, and then set up things like Froelich coherence is something that I know that Jack Sarfati bit too, and which is is also implicated in this whole terahertz regime. So you were gonna say something, Jared?
Yeah. So Shiva, so there's a couple of things on that. The health ramifications that you're talking about for those terahertz, those are higher frequency terahertz than the ones we're talking about. A lot of those health implications are somewhere between like 10 to 400 terahertz. A lot of the infrared, when you hear terahertz, think infrared. A lot of the infrared stuff out there is at 1500 nanometers or 1.5 microns, right? And we're talking 60 to 70 microns, right? 60,000 to 70,000 nanometers. So it's a lot longer wavelength than what a lot of people are talking about. But here is something that a lot of folks may not recognize. When we go from a state of order, perfect order, to perfect chaos, it's not a linear transition in complexity. There's actually a really weird thing that happens where your complexity amplitude, starts going down in complexity as you start going towards chaos. But then right on the threshold of chaos, you get this asymptote. And that asymptote there is where these quasi-crystal things happen, where these aperiodic things happen, where you get some really weird fractal stuff happening. There's a bunch of really cool stuff that happens when you're on the threshold of chaos, on the threshold of maximal entropy. So what I've seen is that this concept of the nanotubules in the brain, the microtubules in the brain, so that isn't just in humans, it's in anything with a cytoskeleton structure. So plants, animals, even some bacteria, like they all have some of this resonating with some unseen field type thing. Taking that further, these amorphous structures, these highly complex structures seem to exist in a lot of disparate areas of our physical reality, such that it's almost as if this is a piece of code that has been reused multiple times in multiple disparate areas. Quasi-crystals, for example, DNA, for example, seems to possess some quasi-crystalline nature to it. There's a mathematical and a physical side of quasi-crystals, and on the physical side, it's DNA. But on the mathematical side, it turns out prime numbers, beads on a string, right, of different spacings, prime numbers have a similar quasi-crystalline, mathematical quasi-crystalline structure to them. It seems like there's actually a relationship between prime numbers, DNA, music theory, particle physics, material science, like all of these different things. There's some recurring piece of code that happens over and over and over, and it's really weird.
Yeah, it's resonance. It always comes back to, it's just we didn't really understand how, like for instance, a quasi crystal can that looks somewhat disorderly at one scale. At the higher scale, can create a diffraction pattern that is perfectly orderly. And so that's it's that just at the edge of chaos that there is with what you're talking about, and it's really neat how there are these additional ways in which we typically think of resonance as like, oh well, you have a certain space and it resonates between them in a straight line, and if you can fit it with that. But no, there's other ways that resonance can follow more complex patterns and go, it's going back and forth in a kind of a not in a straight line, and so you can actually set up patterns of resonance in structures that you wouldn't expect. And there's other ways in which resonances come into play, and once again we find that Tesla knew what he was talking about.
Also, one final thought there on that threshold to chaos. So Ed Teller has a really good paper from 1974 where he's talking about using superconductors that are right on the edge of their state transition, right? And it just so happens he's not the only one. There's a few other UFO documents out there which suggest that the reverse engineering efforts were utilizing superconductors right on the threshold of their superconductivity state. That is interesting because Bose-Einstein condensates, which superconductors model, when those are at that threshold of like crystallization, right, of swapping over into that superconducting state, they are reaching that asymptotic maximal, or I should say minimal entropy state.
Yeah, that basically comes back to, like, for instance, in cellular systems, you've got this this ability to use what they call as Gibbs free energy, but it's basically a system where the shapes of the molecules themselves are such that they can resonate with randomness and collect heat energy and turn it into usable energy because of it, going to that more kind of a crystallizing state. In other words, it's actually the ability for it to turn randomness into order is what's actually happening in harvesting what was just heat and would normally be lost. And instead, your cells can use that heat for real actual work. And so you've got this, they call it a local reversal of entropy, and so that it's theoretically not global. But I don't want to go too far in the weeds there. But there's some really interesting stuff right there.
So, in terms of the crafts and the frequencies and these, so what are the chances that we're not dealing with something, the interaction between the frequencies and these materials and the arts parts? Is it possible we're dealing with some kind of internal communication system for the quote unquote brain of the craft to deliver these charges to the surface skin versus direct levitation? We're kind of trying to take a cudgel to it too quickly.
There was a really interesting paper that just got published from some studies that was done like 2 years ago over at Moses Lake Park in New York, and what they did over there was they tracked these orbs during this event, and they had some good EM stuff coming off these orbs, and I tracked down those EM frequencies that they were using. And it was fascinating. These EM frequencies are specifically utilized for satellite communication. It was like 1.79 gigs and like 4.066 gigs. And I tracked down as best as I could what's using that and what can you do with that, because different frequencies for different amounts of data that you can do. Also, it said it had a 40 kilohertz blank spot or pulse width between the communications, right? So it gives you an idea as to the data, the amount of data that was being able to be done. At the 1.79, I came out to somewhere around 800 kilobits a second, which, I mean, at that point, you're just talking controls, maybe a little bit of like low quality video, but you're not going to use low quality video if you're flying a drone like that. So it was mostly navigation and communication to the craft. And then the 4.066 was more likely to be the higher frequency, higher data control. But this is weird. Okay, why in the heck?
1.6 and thereabouts is the signal that they keep detecting at Skinwalker Ranch, and that's also very close to what the military uses for GPS. So
yes. So if you look at your FCC chart, there's a couple of different interesting frequencies. Let me turn my camera around maybe and I can show you. If you find yourself your FCC chart here, some of these are called fixed satellite space to Earth, and then other ones are called, what was the other one? Like meteorological satellites, right? So it depends on the kinds of satellites that these frequencies are associated to. But here's the thing. If these spheres are shown to be operating on satellite frequencies, that does not necessarily mean that they are human craft. Like you immediately think, oh, they're using the human satellites, they must have, no. There's a lot of other stuff that's been around a long time that suggests that a lot of these craft have AI qualities to them. So if some of these craft are hijacking, and this is obviously all speculation, but if these are non-human craft, some of them at least are non-human craft, and they're utilizing the human satellites for communication, that's messed up. That's messed up for like 15 reasons. That doesn't make sense for 15 different reasons, because they should have some kind of quantum communication thing set up between them. They should have some kind of, you know, other weird stuff, higher quality stuff. No. So if they're utilizing our things, then maybe, speculation, maybe it's not them necessarily using the satellites to communicate with each other. Maybe instead it's them utilizing the satellites to hack the satellites to be able to monitor other things, similar to how they were able to monitor the Nimitz incident in order to identify the cap point, which that cap point location, other than being known by the people on board the fighter planes, it was also programmed in prior to the mission. It was programmed into the planes. Not the first time that we've seen the UFOs being capable of hacking into systems. They hacked into the Russian nukes. They hacked into the American nukes. They can hack shit. If they're hacking shit, they're AI. If they're AI that's hacking shit, that's freaking scary.
So they're using this, possibly using these signals to do code injection on our systems, more or less. That's bizarre.
Yes. Yes.
That's some deep speculation. I love it, dude.
Stop vindicating the threat narrative, Jared. I want it. It's magical space people, and they're here to teach us love, and that's that.
I will
That
not stop. I will not stop with the threat narrative, because there's a lot of stories out there of them helping people, but the fact that they have abducted people against their permission, that's not great. That's not ideal. The fact that they have messed around with nukes and specifically target nuclear related equipment regularly, like that's their number one MO.
That's to keep us from blowing ourselves up, stupid monkeys that we are.
No. Because it's not just like the nuclear weapons that they're targeting. They're targeting everything nuclear. There was another good story back in the 80s, I think, where these UFOs were chasing a train over in Russia that was moving along these rods, these spent rods. And I think, this is again speculation, I think that might be where Lou got the idea for being able to try to like get them all together with Project Interloper. Although Project Interloper was incorrect in that he was trying to, you know, have all of these military equipment with all the good stuff like set up in the water area. If instead he would have been able to just arrange for when the spent rods get transported, that's an already happening thing, right? And it doesn't have all the military equipment attached to it. So once again, you can show, well, wait a minute, why are they even following this?
You know, there's two other things I'd say to look up, Brennan there. Look up Colaris and then human mutilations. There is something to the threat narrative.
Well, yeah, I mean, it's yeah. If you're going to be realistic, nothing is a monolith, and like treating if they're a species that's not some sort of perfect hive, then of course there's going to be units. At the very least, some of them are going to be nefarious. Some of them are going to be criminals.
Right, and some could be rogues or pirates.
Right, the very best.
Also, I mean, I've looked at some of those human mutilation stories, and some of it just seems like it could be crabs or ants or different.
Same thing with the cattle mutilations too. But there's some that are.
There's been more than one military human mutilation.
Yep.
So there was one really good story. These two guys were out somewhere. I think it was one of the secret test area ranges, like Nevada test site or something like that. They were out there. These two guys were out there looking at the missile silos or whatever. And UFO comes, swoops down. It sounds so fake, but this mechanical like octopus arm comes down, grabs one of the two guys, snakes it, and pulls him back up into the craft. And his buddy is freaking out. The craft leaves. The dude is gone for like 5 days. Okay, so like his buddy comes back, and like there's this big hunt for him, this big man search. The body is found days later, 3 miles away from where he was nabbed. And like the only way that they were able to identify him was with a couple of his remaining teeth.
Man, that's crazy. You know, the one thing that we haven't addressed here is that if there is some sort of like, you know, what's it called, the prime directive or something like that, then our entire contact profile would be criminals. In other words, the only people of the advanced civilization we are interacting with are in one way criminal or another. In other words, they're either scientists who are doing shit they're not supposed to be doing.
Renegade biopirates.
Right. Exactly.
Well, if we're kind of going off that zoo hypothesis thing, though, I think a really good real world case study scenario for something very similar to that is North Sentinel Island. I mean, are you guys familiar with that? So there's this, it's called North Sentinel Island. It's in the Indian Ocean. Technically, it's owned by the Indians, okay? But you have this island of people. They've been uncontacted for like 50,000 years, and there's this whole mandate around them to just stay away because the people that have tried have all gotten killed by them. And so there have been some criminal contacts with them. You know, people kind of going out of the way, breaking the law that they're not supposed to do with them. But now that being said, there have been some peaceful interactions between them. With them and some of the other islanders there that are more modern. Where those only happen, though, are on the water, where they go out in their own boats and they're meeting on a mutual territory, which is, you know, if we're using this whole thing as our model, I think that would be a really good case for us, where if we can make our own craft to meet them, you know, on a more level playing field, you know. Does that make sense where I'm going with that?
I like that idea, Dan. That does actually make a lot of sense.
Isn't that sounds a lot like CE5 a little bit.
CE5, but on another technological level.
There's another document that I would point people towards. It's called the White Hot Memo by Twining, back from like July 9th, 1947, just days after Roswell, right? The White Hot Memo, it's on that Majestic document site. It's pretty well regarded. The dad that started the site just passed away a couple of days ago, but his son, Ryan Wood, is still running the site. Anyways, in the White Hot Memo, they talk about what they found on board the craft, and it's really interesting. They go into like very good detail on the radioactive stuff that's found on board. They talk about finding uranium tetrafluoride, uranium hexafluoride, some deuterium. Everything about it looked like they were doing regular matter fusion reactions, no antimatter fusion reactions, which is really interesting because when we look at the Faraday rings that have been found around the edges of the craft, for those things to be at, 10 kilotesla or more, like to be able to get that kind of magnetic field strength with regular fusion is like, that doesn't make sense. Like you need like antimatter levels of energy release to be able to be making magnetic fields of that strength.
I think that Sarfati's probably right in the whole idea of doing a skin thing. In other words, because the metamaterials, you're not having to generate as huge of a, anything when you're just doing it at just tiny levels and then spreading it out over something. It really makes sense.
Something that I've really compared this to.
Shiva, that's exactly it. I don't know if you saw my first talk, but like when I'm talking about splitting up the background pairs, when you do that, you're doing that for a volume, you're doing it at the surface of the volume. So because the background is not stationary with respect to anything, once you start doing that splitting, that's all you have to do. That volume will end up, evacuating out, and then your mass goes to almost zero. So that's a consequence of Sachs's theory. It's a consequence of if the Mach principle, if the mechanism for the Mach principle has anything to do with a background media of some type, then that is and that has nothing to do. See, we got to be clear here. That has nothing to do with quantum. So the danger here is a lot of these things are based that Jack talks about are based on QED. He brings that in, but he's also just replacing, C as being okay. It's the epsilon mu, etc. And that's you can't we have to know a mechanism for this, right? We have to figure that out because there's like I said, without knowing, we can do things empirically. But to really do the real thing, it's new physics, okay? And we do have to understand where quantum mechanics lies, and if it is fundamental, or if it isn't, that's a big deal. A lot of people, myself included, were taught quantum mechanics is fundamental. It applies to everything, all matter, no matter what the energy. That's not necessarily the case. We're finding that experimentally. So taking a step back and understanding that, okay, there might be a bigger picture where, okay, yes, everything in quantum that we've discovered and our, things work, that is a certain regime. Outside of that, there's an underlying layer. If that's there, really we need to kind of slow down, figure out the physics, and be able to do something there, right? We can't, when it's like that saying, when you only have a hammer, everything looks like a nail, right? No, we cannot. You can say, okay, there's a hammer and here's a screwdriver, right? We can think of other tools, and that's the thing at this point. And by the way, I'm not interested in UFOs other than, I think that if we can figure out some fundamental way and we do discover background pairs and we can do this kind of travel, I don't see why someone else wouldn't have already done it, right? It's definitely plausible. So I'm not a skeptic in that regard, but my motivation is the physics.
Go back to the thing you were talking about with the Mach principle. I would just say, think of the Faraday paradox in terms of the Mach principle. It's an interesting thing that I haven't seen many people connect. But Dan, you were trying to say something after we talked about the whole skin effect. I thought you were about to say something.
Yeah, and it kind of, I guess this will kind of build on your comment about this whole thing with Sarfati and the permeativity, like the epsilon mu there. I didn't get the chance to say this earlier during John's talk, but it's not just Jack's work that this stuff kind of speaks to, because he's not the only one that's talked about this whole epsilon mu modification. You got Harold Papineau, you got Sal Pice, if you actually look in his papers in depth, like he's doing the exact same thing. Harold White's talked about this a little bit, Chance Galan. I mean, like, there's actually quite a half dozen or so people that have all kind of been looking down this same route, and I think that's a good sign. And so kind of going off what you were saying on the skin, diverting kind of what I was saying about Pice, when you go and you read his papers, not the patents, the papers he gives quite a few more details. He specifically says that the emitters on this are going to be spread out on the skin in a phased array type system, which is so, that's a beautiful comment that you made about it, having to be all the whole skin.
Yeah, exactly. That's how you create the bubble, instead of trying to just add just gargantuan amounts of energy to to these field effects that are spread out. If you can somehow have something that allows you to make something that's a very, very just super thin skin, then the total amount of energy that you're going to have to use to manipulate that space versus over this this gargantuan space that you're normally dealing with. Yeah, I could totally see what they're talking about. That would be the superior way to do it.
By the way, Shiva, you I think you weren't at the APEC when this was discussed, but when we were talking with the team that has that that electromagnetic very thin film, right? Andrew's team. I mentioned to Andrew, one thing you might test is making a cube or a sphere out of that material, and seeing if you get putting a mass inside and seeing if you get a weight reduction. Because if what he's doing is expelling background pairs or weakening the strength or whatever it is, right, in terms of like the technical nonlinear effect that whatever we would name an analogy with mechanical fluid mechanics, whatever that is, if he's doing it right, and if that's why there's thrust, and we can get it in the volume, then you can and show a reduction in mass, then Bob's your uncle, right? We found something that is doing
the way I'd see it is basically creating like a laminar flow layer. In other words, there's like whenever you've got laminar flow layers, you usually have like a separation between them. Now there are kind of, when you look at it, at a microscopic level, there's sometimes these kind of idler wheels, but I think that's kind of you can see that at an atomic level from what from the way that I see the atomic physics in ether theory, and then taking that concept and just simply making it freaking huge, and then you've got this basically what's like a laminar flow layer. There's a separation between the ether in one area and another, such that they can just flow against each other in a way that is not how it would normally do. It's the best way to put it.
That's right. Yeah. But he's been too busy to do that experiment, so maybe in a couple years, I don't know.
Something worth adding. So if we did want to look at the UFOs and try to compare it to known technologies for the propulsion, on the underside center of some of the UFOs out there, you can see like a weird circular structure there. And you can compare that structure to known structures. It looks, to me, it looks a lot like a fusion reactor, a specific kind of fusion reactor, which is really interesting because Winterberg's idea for the Daedalus drive was to eventually, for the version 2 or 3.0 one, was to have these little feeder pellets of fissile material that you put right in that spot, in that center spot. You ignite that, and then there is a plasma sheath inside here that is capturing the majority of the neutrons as well as the thrust coming from that thing. And so you're pulsing it. So the whole thing is sitting there and it's being pulsed continuously to sit there. There are videos out there where you can see some of the craft, especially the triangle craft, where in the center underside, there's a little like oscillating ball of white light, as if it's like a cavitating, pulsing plasma ball that is being ignited at about once per millisecond to once per second, somewhere in that range. So if we're looking at known technologies and we look at the UFOs that are currently already out there, not all of them have this, but some of them have it. I suspect that those some that have it might be relying upon Winterberg's ideas. Just something worth considering.
Yeah, that's pretty neat.
Yeah, Jared, that's a good point. And the thing about, I mean, I would put it simply to say that if the background pairs, if we discover that something like that in ether is really there, right now, the basic way we have of interacting with that ether is electrons, you know, basically gamma rays making proton, antiproton, or electron and positron pairs, or proton antiprotons, however much energy you put into that. That's kind of like the, you know, we're the caveman level of technology of understanding that, right? So really, that's like a next level of physics that is unknown. You know, there's theories that touch on that have that as a possibility, and those theories are not popular. Almost nobody knows about them. And so if it turns out that those are right, we'll be looking back and giving credit to guys like Sachs and other people. He's not the only one. There's other people that were, doing that stuff, and that's a whole new realm. So the nonlinearity of the interactions is probably where we're going to find some benefit to it in terms of, do you have to actually split up the pair and use that kind of energy level in a shell to do this, or is there nonlinear interaction where you can actually expel them in some elegant way, where you're not necessarily splitting up the pair but still interacting in such a way where you can directionalize and take into account or take advantage of some symmetry breaking of some type, right? So we don't really know, and a lot of it I think has been blocked by the idea of quantum is fundamental, because if you take that, then you can't talk about the other stuff because there's nothing there to talk about, right?
Well, one of the things is that you're talking about particles, and it's because they're useful. And if it turns out that the universe is more continuous, in other words, there are useful transition levels, or useful, a wave has, when you look at the resonance of a wave, the peak and the trough can end up creating a sort of discrete situation, but you're actually dealing with a continuous phenomena underneath. And so, whenever we're talking about these, particle pairs and things like that, are we actually talking about something that is a more continuous phenomenon, that those are useful quantities that are correlated with real effects, real transition levels, things like that, but we're missing some of the continuity aspect of it that is a little more mixed and hard to reach with our current model, which is what I'm hoping to provide is like, maybe if we start over again, we can get up here and see what it is we're looking at with this math.
Yeah, definitely.
So kind of like two-part question here. They're kind of related to each other. So when you guys are talking about the ether, I assume you're talking about like the vacuum background pair production of the vacuum, something like that.
Well, that for me, that could be an indication that there's something there.
Okay.
Right. And
So are you
for me,
guys considering this ether, this dark energy, whatever terminology we want to use for it? Are you guys considering it as a constant in your models, or have you guys considered it being a variable?
So I'll answer for the SACS model. Basically, when in Sachs's theory, when you have particles are basically matter fields. They're not particles, so they're matter fields, and they have multiple aspects to them. So there's an electromagnetic aspect, there's the gravitational inertial aspect, and so when two particles come together in that theory and electromagnetically couple, the inertial aspect is still there. It does not get canceled. And basically that solution is what Sachs terms the background pairs, is that you have a solution of a certain density in your volume, and that he's able to use a molar volume and a molar mass of background pairs to basically derive the mass of an electron. So that's where, and so that becomes a mechanism for the Mach principle and for the discussions we're having. So in that theory, there's a degree of freedom there where if you lower that density, potentially you can lower that mass of an electron. And I will say, Sachs was, smart enough to generalize the Mach principle to be what he called the generalized Mach principle, because you can't just do this to mass, right? We know out there that the ratio of mass to charge and all that stuff is something that, that's there, right? And that's what's interesting about Eric's work, is that he brought up those ratios, right, from that earlier presentation. So in Sachs's work also, it's not, if you lower the mass, you're also lowering the respective ratios. Okay, so I'll answer for that. So Shiva, I guess you have your own.
Yeah, from the 19th century perspective, what we're talking about is that there's a fundamental fluid-like substance that is more rigid than steel. In other words, that's why we've got such a high speed of light, is because it is related to the rigidity. It's related to what we now call permittivity and permeability. There is a translation. It's not direct to to rigidity and density and things like that we would normally talk about. There's no direct translation, but there is a translation. So the point is that variations of the medium is what leads to things like like the bending of light. In other words, whenever we think of space as bent in the ether model, that's just another way of, you can think of air as bent if you look at the fact that there's a gradient, of how the gravity is causing air to be more dense lower down, and then that causes light waves to curve as they're encountering that. Well, you have to understand that there is with ether, you have to think of matter as kind of like a matrix. In other words, like literally like like cubes with space between them, and that ether would be much smaller and could flow through matter, because matter itself, the actual atoms would be they are effects where you're kind of crossing transition points that cause it's a phase transition. In other words, the ether itself becomes different in that local area of rotation that is crossed the threshold. In other words, because there is so much energy in the form of actual kinetic energy, in other words, rotation, it causes a change to the substance. But it doesn't cause a change to the substance just in the place where it is, but near it as well, and that's why you get this sort of inverse square law always showing up, because there is the requirement in a fluid that you don't typically have any break between things. If you do, it's usually because there's a space. And so being able to create spaces where the fluid is not present actually allows the fluid to behave a bit differently than it would whenever it doesn't have that space. And so it actually gives an additional degree of freedom, which then leads to an idea of different ideas of entropy related to gravity as well. So there's a lot of ways that this you can reconnect all the pieces that we have to this ether model. And so the idea of it as a constant, no, there's not. I wouldn't call it that.
So So when I'm thinking about this whole idea of pair production background and fields, yada yada yada, I'm sitting here wondering, pair production in a vacuum. Obviously, if we're trying to boil a vacuum, right, like vacuum bifringence, just 10 to the 18 volts per meter. But if we're going to think about in matter, like we were talking about Sarfati's ideas earlier, right? If we're talking about in matter, well, you're already not at the ground state anyways, because you already have the fields already excited for various reasons there. And so that has me thinking, what would the pair production look like in the matter, when we're getting this kind of type of polarization? And I'm sitting here wondering, perhaps instead of electron-positron pair production in the matter, perhaps it's electron-hole pair production, and that could, to me, that could seem like it could offer up some insights as to like last year, I think it was a lab in Paris. They were able to induce electron-hole pair production in graphene at, it was like 10 to the 7 volts per meter instead of 10 to the 18. But do you guys kind of see where I'm going with this? Or
yeah, so Dan, I want to bring up an important point. So the making an electron and positron from gamma rays, that's something called the Brett-Wheeler process. That wasn't Jack Sarfati's. No.
Yeah, no, I'm not saying that was Jack.
There's the linear Brett-Wheeler process where you get two gamma rays hitting, and basically spontaneously in the quantum mechanics story, it's your energy is turning into matter. But there is also the nonlinear Brett-Wheeler process, where if you have let's say a high energy laser and you have one gamma ray, you can actually have that same thing. Now, how is that happening? Well, two things. One, from what I recall, I could be wrong about this, but it wasn't predicted by quantum electrodynamics. And there are quantum electrodynamics calculations you can do. The thing you got to keep in mind about quantum electrodynamics is it's quantum, so it's descriptive. So it can go in there, and calculate, and then you can do nonlinear calculations as well, right? You're using propagators that are equivalent to green functions, and you're doing basically E&M at that level. So now what we're talking about is a more, potentially a more elegant way of interacting with that background at lower energies, potentially, that we don't know, we haven't discovered. We don't have the idea, right, as the mainstream doesn't have the idea of that there is a background pair to explore these nonlinearities. We're dealing with a quantum theory. It's a linear quantum theory that you can extend it to nonlinear effects. But fundamentally, if you're doing a field theory, which is what Einstein was trying to do, you don't have those restrictions. And so that's where ideas like Sax's, and there's other work that I've been making some progress and finding other things out there, that those ideas are, there might be fruit there for us to find and actually explore that. And in matter, like you're saying, there are fields. And so there's energy, and there could be nonlinear effects close to the nuclei of matter that we wouldn't expect, right? We would only go backwards and calculate from, okay, no, someone told us, or we see these guys do it, so we can go back and calculate. But it's not descriptive. These other theories are more descriptive. They're making a claim about that we can test about what is fundamental in the universe, and actually doing something with it. So,
what's neat is talking about non-linearities. That kind of goes back to Eric was going to pop in here for a second. Sorry that he left, but the medium behaving in a nonlinear fashion at a quantum scale is actually what's required for a soliton model to be workable. In other words, you have to have the waves in the medium propagating at different speeds based upon their frequency for solitons to function. So whenever you're talking about a solitonic model of of how things like electrons and other energetic particles are existing in a more continuous fashion, that is very crucial. And I'd love to. I really want to understand Eric's work more, and I don't understand it adequately enough yet. And so I'm hoping he'll continue to work with us and tell us a little bit more about his experimentation.
By the way, he has a book. I'm blurred here, but Eric has a book, and in it is a translation of that 1911 paper by Max Planck. So I would recommend getting it because it's an interesting read.
I always get the sense that we're surrounded by the future Max Plancks and Niels Bohrs of the future world, with guys like Eric and Curtis.
You know what? Eric is still here. Let me bring Eric back in, and I'm gonna take myself back out while I eat my popcorn.
Oh, well, I remember, Curtis, you were saying about the charge to mass ratio, and it didn't sound like you understood what I was talking about. I'm saying that the ratio is always conserved.
Yes.
It's not, yeah.
Yes.
You can have less mass, but I'm saying if you take the idea of conserved ratios, then the charge and the action will follow with it.
Right.
And so if you do that, if you take that extra step, then you have this realization of what can transmit across space. You don't need to have the particle to transmit the identity of, let's say, an electron, because that's the whole trick. And then you could do the same thing with protons or whatever with the ratio trick.
Yeah.
So, right. I just one step at a time. I'm glad that you seem to have understood that part.
Yeah, I'm with you there, and that's why, I'm with this group especially. I mean, we're like stretching the limit in terms of like talking about theory, or you're bringing in UAPs and like speculative physics on that. And one of the things I loved about your work is like, one of the things I was concerned about is like, what do we know is fundamental? We just need to start there, because if there's really this phenomena that we don't, a technology, something we haven't discovered, let's go back and look at, okay, what do we really know? And like I said, I don't know if you saw my text. I brought a Carver Mead. I don't know if you saw his talk from that.
Yes. Well, Carver's into strings connecting all across space, which it's an act of desperation to me.
Yeah. Well, Carver Mead, I'm not sure if he's a string theorist. I know he's trying to use
his own kind of string.
Yeah, he's trying to use.
I saw a lecture on.
Right.
There's a Demystify Psi lecture. I saw him blabber about that before.
Yeah.
I just, that's just me. I see it as another act of desperation, along with parallel universes and stuff.
Yeah.
So,
well, setting aside the gravity stuff, right? Because we know Carver Mead. I mean, he's really the reason why we have, one of the big reasons why we have the computing revolution we did, right? He's the one that proved that as you shrink the device size, you get more efficiency and more computation. But his talk, I would suggest watching his talk where he gave that Kyoto Prize, where he talks about the engineering and the character physical law. It's very interesting. Now, I agree with you in terms of like he's trying to apply those principles to gravitation, but really he's, his message in that talk, and I know he went to that other with those guys and did a bunch of speculation, but it was really like, hey, let's look at what we know now experimentally. And one of the interesting experiments that he gave in that talk that you might like is it was a neutron diffraction experiment. So yeah, if you get a chance to look at that, I'd like to.
Well, look, I know about neutron diffraction. I've read a book on those things. I've seen some papers, and they invariably pull out the probability interpretation for it. I mean, it's straight out wave particle duality. How do you deal with that?
Yeah.
So,
and actually, I should send you. I'll try to find. Eric has some. Carver Mead has some talks that you might be interested in, because they, he's kind of like, working in semiconductor. Basically, they really weren't using quantum mechanics. They were treating.
Right, I've heard about that. A lot of people say.
So, for the big, a lot of times people in quantum says, they take that as a victory, and it's like you look at Carver Mead and you say, no, we didn't use quantum at all.
I've heard about that. That's right.
So it's like what victory, right? So in terms of like the stuff he did, like the stuff he knows, which is the electrons, right? He knows electrons, if anyone knows it. He treats them as waves, as fields. That's what the classical guys did, like Einstein.
That's a good step, but the trick is, how do you explain the particle properties? That's
Right.
always been the problem.
Right.
It's easy to see waves. Yeah. That's why I'm so excited to try to say what that ratio principle was
Yes.
about. That
Yes.
that to me is the breakthrough.
Yeah. Yeah.
I mean, that
and
happened.
it's really like when I mentioned Mendel Sachs, right? He's a theorist. One of the things he did is he took Mach's, because the Mach principle, there was a problem with it because people pointed out that, oh, well, if that's right, what about the charge, right? If you're getting mass, with that interaction, what about the charge to mass ratio? Because these ratios are something we know is fundamental, like you're pointing out. That's a fundamental thing that it's going to be hard for any like honest physicist to let go of. We know that. And so, that's the big question to me is like, okay, taking that, like, and Sachs, what he did is he generalized the Mach principle and said, if this is going to be right, it has to be those ratios, right? Have to be proportional.
You're losing me. I don't know how Mach's principle relates to charges. Mach's principle is some kind of cosmological thing. I just don't really know what you're talking about.
Right. Well, there's some depth to it, but I'll simply say that there was a counter argument to Mach's principle that because it was basically dealing only with mass. So the issue was that, if that was the case, what about the charge, right? And the ratios that we know that there's ratios, then that's what's conserved. And so and that that's where we find the symmetries. So that was something that Sachs took into account. So it's along the lines of what you're saying, is that the ratios are more fundamental than the individual measurements, because you have to do more than one thing to get that charge, right? But the ratio comes out of direct from experiments.
There is such a thing as the charge constant and the mass constant.
Yes.
And the action constant. It's just another way of looking at it as maximums instead of quantizations.
Yes.
And that was inspired by Planck's second theory, the way he did it with action.
Yeah.
And go ahead.
Yeah, no, that's great. I mean, that's the thing I think these guys need to hear, is that there's because a lot of us are trained in the quantum way, right? This is like a stretch, right? We're all trained, we're all taught that that's fundamental. And so it takes a step and a step back mentally to say, okay, question the things and then use that for these, what Jared is trying to do with these supposedly.
Look, these ideas, they're almost a dime a dozen. That's why I spent so much time nailing down the experiment in a way where I'm saying, look, if you disagree with the theory, go repeat the experiment, argue with the experiment.
Right. Yep. Yeah. And hopefully somebody will take that on, because I wish I had the capability now, but hopefully in a couple of years if no one else does. But I
made
really
it
love the work
easy.
you've done, Eric.
I made it real easy for you to find how to do it with the gamma spectacular thing that the spectrometer. You do need a larger detector, and I said exactly which radioisotope to get, what size of it, and there it is. It's a simple calculation once you do the experiment. Then that you let that convince you that, oh, well, maybe I'm not a nut. And then you try to do the 2 detector experiment.
Right.
So, Eric, are you familiar with John Stuart Bell's speakable and unspeakable in quantum mechanics?
Yeah.
He's got so many quotes. They're just so great.
Look, I have a slide about that, but let me just try to say what I know about Bell's theorem, just to get us started. There's a graph of angle versus coincidences, and then Bell does a straight line kind of triangle thing, and then let's see, let me get it right. There's it's a sine. The experiment looks like a sine wave. Are you with me? There's the angle between the two. Look at the experiment. the angle between the two detectors, there's something that happens in the middle, it goes out, and then they look at the correlation between these two detectors, just to get the starting point of all this stuff right. So Bell says that there's this triangle, a straight line part of the prediction of what should happen. The curve part is quantum mechanics, but it's also the experiment, and it's also classical theory. So all those three agree with the curve. It's only Bell's theorem that disagrees. So that's the start.
Yeah, the straight line is ballistic. It's particles only. It doesn't account for waves.
You're right.
So,
You're right.
Waves are gonna do that exact.
You're right.
If it's just a wave, it will absolutely do the quantum thing in the Bell's theorem. Yeah, exactly.
Well, look, you could put the wave into the probability wave if you want. What's missing in Bell's derivation is this preloaded state. It's the model of Bell is that the whatever hits there is prepackaged, and it makes it happen. All the arguments are about that amount, a particle amount, impinging ballistically, particle-like you say. It's that Bell's theorem doesn't include the preloaded state. What's confusing is that in this case, quantum mechanics actually gets it right. It gets an answer that there's no way to make it different. It looks like the right answer to me. But you see, that's a two-particle experiment. And so you see the difference between a threshold model and a quantum model if you go to the simple experiment, the one-particle experiment. So this is what I call the two-particle experiment. There's two whatever goes, and then it interacts, right? Two-particle. The one-particle experiment lets you see the distinction to see what's wrong with quantum mechanics. But you see, all these Bell arguments look at quantum mechanics and says it's right, and that the world is non-local. And then they go to Bell and they say, oh, well, this is a realistic theorem. And why is it that it disagrees with quantum mechanics? And they think, well, therefore, the world is non-local. See? So what I'm trying to point out, and it's hard to do, is that both Bell is wrong and quantum mechanics is wrong. Bell is wrong because it leaves out the preloaded state, and so does quantum mechanics.
Well, Bell completely went back on all of that. He said, look, he's like, why didn't anybody tell me about this? Let me find one of his quotes, because he really goes hard on saying, here, I think, is this it? Yeah. Let me read a couple of quotes from his book. It's like that the theory is supposed to apply fundamentally to the world as a whole requires ultimately that observers be included in the system. This raises no particular problem so long as they are conceived as essentially different from computers. This is a long quote. Let me skip to the more important part. That the guiding wave in the general case propagates not in an ordinary 3 space, but in a multidimensional configuration space is the origin of the notorious non-locality of quantum mechanics. It is a merit of the de Broglie-Bohm version to bring this out so explicitly that it cannot be ignored. And then the second thing that he says that's really very explicit, he says, but in 1952, I saw the impossible done. It was in papers by David Bohm. Bohm showed explicitly how parameters could indeed be introduced into non-relativistic wave mechanics, with the help of which the indeterministic description could be transformed into a deterministic one. More importantly, in my opinion, the subjectivity of the orthodox version, the necessary reference to the observer, could be eliminated. Moreover, the essential idea that one had been advanced already by de Broglie in 1927 in his pilot wave picture.
Following you.
Well, it basically. So he's just basically saying that in pilot wave you don't need any of this non-locality. That it's all completely. You know, he's repeated over and over throughout his through a variety of quotes and in that book that with pilot wave picture you no longer have this idea of the observer and the wave particle duality as it is, but instead there is a different version. So Bell himself rejected Bell's inequalities.
This pilot wave stuff is a way to explain the one way or the other in the beam splitter. I'm saying, no, it doesn't work that way. It's just noise that they think it works that way. Because I'm disputing the results of many experiments to make it look like it went one way or the other at a beam splitter. And then people make up things like the pilot wave to try to explain it. I'm saying, no, it doesn't do that in the first place.
Well,
that's what my experiment shows, that it isn't one way or the other at a beam splitter. You don't need to
it's
invent
completely
a pilot
continuous.
wave.
Is that
Huh?
basically you're saying that it is just completely continuous? There is no need for anything to be piloted because it is entirely just waves. Is that basically what you're trying to get at?
With light is just waves, but there are
Right.
properties in matter with the threshold and loading thing, both in the emission and the absorption, to give the illusion of particles, and that's for light. It's a little bit different for matter. So what loads up with light? It would be kinetic energy, and so then you could use Planck's second theory and all that, the modification I did for it. You could understand that light is just a wave, that there be these thresholds in matter that give it that snappiness, that discontinuity. And then, you look at the experiments and say, oh, does it really go one way or the other? Then you look at the experiments that are done. I'm repeating myself, like what Clauser did and Aspe did. And they say, oh, it really looks like that. But you see through the problems in their experiment. And then you look at my experiment and get the opposite answer. All right. Then there's matter. What happens with the matter wave? It's actual helium that loads up, that there could be a wave property of helium, and that it's not a probability wave. As soon as you get into a probability wave, you're in paradox.
No. So the probability thing is silly. But let me just what
before you guys get back into a rally.
Yeah.
Well, before you guys get back into another rally, kind of going back and forth like this, it occurs to me that, and I might be showing my relative ignorance here, but there's two major schools of thought around quantum physics. One is the Copenhagen interpretation, the other is the Everettian interpretation.
Oh gosh,
and I know I can feel your eyes rolling from all the way over here, but it sounds like you're and have you considered that this is less of a refutation of quantum physics altogether, more of a refutation of the Copenhagen interpretation, almost a vindication of the Everettian interpretation?
The Copenhagen and quantum mechanics.
No, they're not the same thing. Like Everettian doesn't involve a wave collapse. It's you're taking particles out of the wave. I know Dan is much more versed than me on this.
So what Everett's saying is it's just pure wave mechanics. That's all Everett says.
Hey, Jacob.
There's no collapse.
So it sounds like a lot what Eric is saying.
Everett is still different than what they're talking about. They're talking about variable theories, which is a different thing.
Mm-hmm.
It's an act of desperation to me. You have to invent infinite parallel worlds to explain and embrace the wave collapse. I'm saying there is no
Schrodinger called it as an act of desperation.
Get around, Schrodinger hated quantum mechanics, by the way.
Yeah,
and so there's a nice book
introducing the worlds, and the wave collapse is what gets rid of the other worlds.
That's right. So I brought that up straight away in my lecture, where in Bohr's book and Heisenberg and de Broglie, they recognize right away that there's this wave collapse, like entanglement, where if something happens here, it affects there. Well,
they're entangled because they're part of the same wave function.
What?
They're entangled because they're part of it. They're described by the same wave function. That's basically what entanglement is.
I know that, but still, that's the probability interpretation. How do you make that happen?
But quantum mechanics isn't pure probability. You're squaring you're taking the modulus square of the amplitude of the wave function. You're not just evolving a probability wave. You get nonlinearities that way. That's why you have to evolve a wave, and then you apply probabilities to the evolved wave at whatever point in time you're trying to make.
Whatever time you want to apply the probability, it doesn't matter to me. It's still entanglement. When something happens here, they say it affects there by some kind of probability thing. Like you said, the square of the wave function. I know all that stuff. But does it really happen like that? Does that make sense? I mean, people see that, because of the experiments that I pointed out by Clauser and his predecessors and Aspe, and they got it comes from these. I'm saying, look at the experiments that are telling you that it works that way, and I'm saying they're wrong. They're full of flaws, different ways it could be artifacts that they're seeing, and then
yes, Jared.
I got cut off the Brandon.
And then my experiments say the opposite. You see, then you don't.
Let me just ask this one thing before I forget again. Cloud chamber
Michael.
trails. What do you do about cloud chamber trails in a completely continuous theory? That was all I needed to say.
Well, first of all, you don't see trails with gamma rays. You only see it with charged or other heavier, with massive stuff. That's step one. Step two is it's very high frequency stuff. So it acts like a narrow beam. It's so you can explain it that way, even with a needle radiation kind of wave. So it's or the soliton, that it actually is a particle. There's a particle state of some heavier particle that goes across, and then there's a wave state in other kinds of experiments at lower frequencies, of lower momentums rather. And you can see electron diffraction and helium diffraction. So it matters what energy you're using or momentum you're using, and whether you're using matter or light. Like I said, light and gamma rays does not show up in the cloud chamber.
Jared.
So whenever a claim is made, like the first place I always go is like, can you look at something that's already been done in the real world that, enhances or refutes the idea, right? So when you're saying that entanglement doesn't exist, I can't help but think of quantum cryptography protocols where we are already utilizing this entanglement process for communication purposes.
They say that. I know they say that. And by the way, I'm giving a lecture next week for a quantum computing research group. It's at the top of my website. They've had me last month, and they invited me again. So the thing about quantum computing is they say it works, but does it really? It doesn't really work. They're trying to make it work.
But right now,
I don't think it works.
There's satellites flying over our heads right now that are using the entanglement quantum cryptography algorithms. Like it's already proven to work in use. So for your thing to refute that,
I don't believe
in mind that those are likely using optics. So the energy level is a regime where you would see quantum effects, and you're using light. So if you're talking about, because I know this is like the communication, decades ago, the banking system started to do quantum cryptography in the fiber communications. So they wouldn't, because you could do man-in-the-middle attacks with fiber communications. So that again, that's the regime where that works is not the regime Eric has done his experiments in.
Well, I did do it with matter as well. I did it with both gamma rays and alpha rays, which is a very high energy regime.
Yeah,
I did it in the highest frequency
quantum cryptography stuff is that stuff is in the light. That basically it's infrared and those kind of wavelengths.
Yeah.
Well, so how are we doing, guys? It's almost 6. So should we wrap things up for tonight? This has been an engaging debate.
All right.
I think we're all getting a little peaked.
Michael, did you have something you wanted to say?
Yeah, Michael Brown just came in. Last words or thoughts, Michael?
Brown?
Yeah. Well, yeah, I guess why don't we wrap things up? This has been APEC for August 31st, 2024. There's been an absolutely remarkable session. Thank all of you, and thank you for everybody who has attended virtually. It's
and thank
amazing.
you, Tim.
Amazing.
Yeah, thank you.
A round of applause for Tim hosting all of these. The glue that is APEC.